So, okay, I think we are ready to start. Welcome back. We have Konstantin Eder, who's going to speak about supercartan geometry and application to quantum supergravity.
Thank you very much. And first of all, thank you to the organizers for the invitation and for giving me the opportunity to present my work, which was part of my PhD thesis written by supervision of Hanno Salman, and which is about supercartan geometry and applications to quantum supergravity. But here in this talk, I will mainly talk about the classical theory, so I will not say something about the quantum theory. Just at the end, I will give some outlook on applications I have considered. And the results you can find in these papers. Now, so the motivation of my work was because I'm working in a field law called loop quantum gravity, and I intended to extend these formalism to supergravity. And in loop quantum gravity, we always are concerned with mathematical rigor. So I wanted to provide a mathematically rigorous approach towards geometric supergravity, because geometric supergravity turned out to be very useful in this context. And so to do so, I used and developed tools in supergeometry. But it turns out in the main formalism of supermanifold theory, there's some main issue which is actually rarely considered in the physical literature, mainly that the pullback of superfields to the underlying space-time manifold is purely commutative supersonics. So there actually are no fermionic degrees of freedom on the body of a supermanifold. And some nice resolution is given by studying so-called relative supermanifolds by adding some parametrization, and I will explain this in what follows. So at the beginning, I will give a review on supermanifold theory. In particular, I will outline the various different approaches given by the Beresin-Constant-Lattice approach, Rosser-Stewart approach, and also the Molotov-Sachs approach, which is a unification of all these approaches. And actually also then gives a very intuitive introduction to the definition of so-called relative supermanifolds, which are defined in order to restore this issue of non-trivial fermionic degrees of freedom. And then also talk about superconnections and the parallel transport, because these are particularly important in context of loop quantum gravity. And then I will apply these methods to supergravity. I will introduce the notion of supercartan geometry, apply this to the context of supergravity. I derive the so-called Holst-McDowell-Mansui action, which is a one-parameter family of generalizations of the McDowell-Mansui actions of supergravity. And then we'll also study the extension to extended supersymmetry. We'll also talk about the boundary theory, because the boundary theory in the context of supersymmetry is very special. And then also point out some particularities of the self-dual theory at the end. Okay, so at the beginning, give me a review on supermanifold theory, and then also discuss relative supermanifolds. Now, there are various different approaches how to formulate a supermanifold. And maybe the the best known one is the so-called Beresin-Constant-Lattice approach, which is an algebrogeometric approach, which uses techniques from algebraic geometry. And it's actually rather abstract, because it defines supermanifolds in terms of pseudo functions, sheaf of functions. And then this is actually hardly accessible to physicists, because physicists are used to points. And so one asks the question, what are actually the points? One is used in the ordinary smooth manifold approach. And so Rogers and David formulated a notion of supermanifold, which is also called the concrete approach, by defining supermanifolds in terms of topological space of points. But it turns out there are actually too many points, so there's some ambiguity in formulation of a notion of a point. And this has been then later resolved by Molotov in early works, and later also studied in more detail by Sachs, the so-called categorical approach, which then shows that the Beresin-Constant-Lattice approach and Rogers-Stewart approach are actually two sides of the same coin. And now at the beginning, let me motivate the definition of algebrogeometric supermanifold. So there one starts with the observation that the structure of smooth manifolds M can be completely encoded in terms of functions defined on them. So one defines an ordinary manifold in terms of a local ring space, consisting of a paracompact topological house to space modulus M and some abstract sheaf of local rings defined on it. And together with the requirement that this local ring space is locally isomorphic to a locally ring space given by the Euclidean space Rn and smooth functions defined on it. And based on this observation, one then can define a supermanifold, similarly by extending this to the supercategory. And here I actually have given a definition which is not the standard definition one is using in the Bayes and constant lattice approach. Here I'm using a definition given by the book of Carmeli, Rita Fioresi, and Caston, because this one has the strongest relation, actually gives a strong relation to the Rogers-David approach and the Molokov-Sachs approach. So there's a direct relation then, which you can provide in this formalism. So a supermanifold M is again defined in terms of a super ring space now, consisting of a paracompact topological house of space M and some abstract sheaf OM of local superrings on M. And with the additional requirement that a supermanifold M is locally isomorphic to a superspace Rm/n, consisting of the Euclidean Rm and some sheaf of superfunctions, which locally look like this. So they can be expanded in terms of a Taylor series, consisting of smooth functions, ordinary smooth functions, f0, fi, depending on some even parameter x, and some odd Grassmann variables theta. By cutting off all this nilpotent part of the smooth functions, of these super smooth functions, one gets an ordinary smooth function of the manifold. So one can divide out the subideal of nilpotent sheaves as sections of the sheaf, and then one gets an ordinary smooth manifold, which is called the body of a supermanifold. And using now its category of, because we can study supermanifolds, the objects and morphisms, we get a category of supermanifolds, and the group objects are then called super Lie groups. Okay, so far this was the definition of an algebrogeometric supermanifold. Using such a supermanifold M, one can naturally associate to it a contrariant functor on the category of supermanifolds by assigning supermanifolds T to the T point, so-called T point M of T, defined as the set of all supermanifold morphisms between T and M. And to morphisms between supermanifolds, the corresponding pullback. So any supermanifold induces such a contrariant functor. Now one can restrict this whole category to a subcategory of superpoints, consisting of all those supermanifolds T where the underlying topological space is just an ordinary point, just an any point. So the function sheaf restricts to a Grassmann algebra. In that case, when you prove that the lambda points of M is isomorphic to the set of superalgebra morphisms between closed sections of the supermanifold M to the Grassmann algebra lambda. And now all these sets contain the real spectrum by restricting this Grassmann algebra lambda to the ordinary real numbers. So it contains the real spectrum, and the real spectrum can be equipped naturally with a topology by introducing the Tversky or Gelfand topology. So then there's a topological space, and then one can, because any M of lambda naturally projects on the real spectrum, one can equip these lambda points with the closest topology with the requirement that these projections on the real spectrum are continuous. And this is the so-called Divid topology. So in this way, it follows that these lambda points carry naturally a topology, given with the Divid topology, and actually have the structure of a manifold, a supermanifold, which are the so-called Rogers-Divid supermanifolds. And actually, the choice of a particular Grassmann algebra is completely ambiguous. One actually has to, instead of considering one specific Grassmann algebra, one actually has to consider all possible Grassmann algebras. So one actually has to, instead of considering a particular lambda point, actually consider all possible lambda points. So actually, one defines a supermanifold in terms of a functor, mapping Grassmann algebras to corresponding topological spaces M of lambda. So this is actually the interpretation of a supermanifold in the sense of Molokov and Sachs. Instead of considering a specific Grassmann algebra, this is all possible Grassmann algebras. So interpreting supermanifold in terms of a covariant functor. And this then has the nice property that we can extend this formalism also to include infinite dimensional supermanifolds. And for instance, this has been considered by Holomorphic and should to extend this to include Banach or Fréchet supermanifolds by requiring these lambda points to be Banach or Fréchet manifolds. And also, and this can be used then, for instance, to study groups of super differomorphisms or supersymmetry transformations. Okay, so this Molokov-Sachs approach, it's a unified description of all these different approaches to supermanifold theory, but there's some common issue, mainly to the fact that the pullback of superfields to the body of a supermanifold turn out to be purely commutative. Because then this actually corresponds, roughly speaking, to setting all these Grassmann variables to 0, and then this function restricts an ordinary commutative smooth functions on a manifold. So actually there are no uncommutative fermionics of freedom on the body of the manifold. And now a resolution is given, a nice resolution is given by, instead of considering just ordinary superfields, now in terms of, by adding a parameterization to the manifold S. So instead we're considering now functions defined on a parameterized supermanifold by adding this parameterization. Because then the restriction on the body of a supermanifold are then functions, ordinary smooth functions, tensor global sections of the supermanifold. So now fermionic degrees of freedom are encoded on this parameterization. But a priori, as in the Molokov-Sachs approach, this choice of a particular parameterization supermanifold is completely ambiguous. So actually you have to require that physical fields do not really depend on this parameterization, so that it form, in a certain sense, covariantly under change of parameterization.
Bobby, can I just ask what the meaning of this parameterization is?
So the parameterization is used in order to encode the fermionic degrees of freedom, so somehow to switch on fermionic degrees of freedom. So for a trivial parameterization, you actually just get the bosonic degrees of freedom by going on the odd directions of your parameterization, you can switch on your fermionic degrees of freedom.
Okay, thank you.
I will give, later in this section, I will give a more physical interpretation of this parameterization, because actually that turns out to be some nice relation to a model fermionic degrees of freedom and perturbative algebraic quantum field theory, which naturally arises in this formalism.
Can you say, just for us laymen, a few more words about this? Because normally, I mean, lots of us are used to work with superfields, etc., and we don't have any idea about sort of the fermionic degrees of freedom being switched off. Fermionic derivatives, we can act on superfields and then restrict to the zero component this way, and I mean, they are there. So what is the problem?
Yeah, the problem is that actually some simple problems. So your fields, the functions here are ordinary smooth functions and then expand in a Taylor series of theta. Yes. And when you start to restrict to the body, you just get this field here, which is all an ordinary smooth function. So there are fermionic degrees of freedom and supergravity are assumed to be undercommutative.
But if you act with some derivatives first and then restrict, I mean, you get the other ones.
Yeah, this depends on, so this is what we born the super field approach. So here it's about, so this kind of geometric approach, actually it's just, it's a different viewpoint. It's a different viewpoint. Sorry?
This old argument, I don't know if this is a new absence of fermionic points, but just like supermanifolds don't have these fermionic points, if you want to think of a field as kind of a point in some space of fields, point is there are no fermionic fields because these spaces don't have fermionic points. I don't know if that's, I mean, it's one way of saying that there are no fermionic fields. I don't know if it's that way or if there's another way.
Indeed, yeah. Now, yes, so the choice of particular parameterizations are ambiguous, and we have to somehow ensure invariance or covariance under change of parameterization. And interestingly, this is nicely implemented considering so-called relative supermanifolds. So relative supermanifolds have been first introduced by Linie and also studied later by Huck et al. In the local approach to super quantum field theories. And also Kessler, Jost and Tolksdorf, and later by Kessler, Shesmani, and Xing-Tung Yao, in the context of super conformal field theories on supermanifold surfaces. So a relative supermanifold is the category of relative supermanifolds. It's described in terms of S relative supermanifolds given by tuples S times M, parameterizations S times M, together with the projection on the first vector, and together with morphisms between parameterized supermanifolds, which are morphisms between S times M and S times N with the property that they commute by projecting on the first vector. And now, due to this property that we're actually considering these type of morphisms, it follows that if one considers the change of parametrization, so one has some morphism lambda between parametrizing supermanifolds S and S prime, this then induces a morphism naturally on the set of relative supermanifold morphisms between relative to S prime and S relative morphisms between relative to parameterization S. In particular, I well-behaved under composition, so the commute with compositions of morphisms. So in this relative category, actually, a change of parameterization actually induces such a morphism, ensuring covariance under change of parameterization. Then you can also extend this to include principal superfiber bundles, so any superfiber bundle theory. So this is just one example of a principal superfiber bundle. So relative principal superfiber bundle is considered in terms of this bundle, consisting of the total space given by S relative supermanifold in the base. And now with the requirement some G-right action with G a super Lie group. Now one requires that these are all morphisms of S relative supermanifolds. So with the standard requirement of a G-right action. And then having this formulation of a principal superfiber bundle can then also define connection forms. And this is a definition of a relative superconnection one form. So one defines a superconnection one form in terms of an even valued one form S relative principal superfiber bundle, taking values on a Lie algebra of a super Lie group, and together with certain requirements. So the first one is just the RNA one extended to supercategories, so requiring that the connection maps fundamental vector fields induced by some Lie algebra element to the corresponding generator. And the second one actually has to reformulate it because the supermanifold theory doesn't have the notion of a point, but just has access to the topological points. So this one is this actually ensures covariance under G-right action. So this is for the topological points, and this is an infinitesimal one for going in the odd directions. So can all extend this naturally to the additive category. And this is one nice example, because so I studied this because in congruity and all this is concerned with paratransport map induced by connections. And this one shows very nicely the strong relation between this relative supermanifold formalism and the Holomorphic interpretation of supermanifold theory. So any superconnection induces naturally a paratransport, so actually there's a G missing here. So it induces a paratransport along parameterized paths. And then it turns out that the paratransport of a superconnection now is a isomorphism between sections of a pullback bundle. Because if you restrict the path on a certain point here, this turns out to be a morphism between the parameterization and the manifold. So actually gets here now a pullback bundle. So the paratransport map in this formalism now is a isomorphism between sections. And it turns out that this is now nicely behaved on a change of parameterization. So if one has a change of parameterization lambda between S and S prime, this then yields this commutative diagrams, which ensures covariance on a change of parameterization. And now one can consider certain consider the Wilson observables by considering closed loops, taking the supertrace. Then one ends up with these type of expressions where gamma now is an ordinary path on a manifold, on the body of a manifold, supermanifold. And now instead of just defining an ordinary group element of a supergroup, this is merely it's actually a morphism between the supermanifold S and the group G. And this is now very important, this parametrization, because in case you just use the trivial parametrization, this Wilson loop observer now sticks to the ordinary Wilson loop observer with the bosonic part of this superconnection. So the parametrization is actually mandatory in order to get non-trivial fermionic diisofreedom. And instead of ordinary group elements, these are defined morphisms on the parametrization. So these are elements of the generalized supergroup G of S, which has the structure of a Rogers-David supermanifold. Again, it's covariant on change of parametrization and also gauge invariant.
So psi is one form.
Psi is the one from the fermionic part of the connection, yeah. And in case you would just choose this trivial parametrization, this psi would be simply absent. Okay.
So psi is the fermionic one?
Psi is the fermionic part of this connection. Yeah. pull back now because I'm just considering ordinary path.
If you switch off the
I should be more precise. So actually, I'm considering here now an ordinary path on the body of a supermanifold. So I'm considering path on the ordinary body. And then if you pull back your connection on this body, the psi component just vanishes. If you have no parameterization.
Okay. Are you able to reproduce, for example, the Maldacena terms, for example?
Sorry, again?
Are you able to reproduce the Maldacena terms in this way? Or the super Wilson loops, for example? Are you able to reproduce the animal form, super Wilson loops in this way?
Yeah. So, no, they're not superphysical. So I'm considering a certain parameterization, but actually considering all possible parameterizations. Because actually we should not, So in this way, so this S ensures that this psi, if you pull it back, does not vanish on the body. But instead of considering such a particular S, you actually have to consider all possible S.
You should look at your formula more precisely. I don't understand the formula.
Yeah. Maybe it comes now clearer because now I want to. Because now I want to. Because actually you have to ensure this covariance and change parameterization. Then and actually I would like now to give some physical interpretation of this problem. So now in order to explain this a bit more how this parameterization can be interpreted physically, we now I would like to consider some S-parameterized field theory described in terms of a gauge field on this sort of principles of file bundle. Yeah, sorry,
another question. So when you define a connection or a super connection, in order to define a super connection, in order to reproduce a correct gauge field plus plurinos and all the super partners of the group, you have to impose some constraints. So you cannot. It's not just enough to define a super connection or just an extension of the connection to get the correct physical object. You have to impose some constraints.
For instance, you mean for instance Riemannian conditions, or
Riemannian condition, or are called conventional constraints in superspace. So there are, different ways to express this factor, because otherwise this object contains so many parameters that do not reproduce the correct degrees of freedom.
This is ensured by this covariance property. So you do not introduce superfluous physical degrees of freedom by this property. Because you're not restricting a particular parameterization, but actually consider all possible parameterizations. And you have to require that these are well behaved if you change parameterization. And this way you do not introduce superfluous.
You have to impose these constraints. Otherwise, even though you have a correct reparameterization of this object, it doesn't describe the correct physical degrees of freedoms.
You actually do not introduce new physical degrees of freedom by this procedure.
You introduce new degrees of freedom?
No, new degrees of freedom in this way.
Unless you fix some constraints on the connection.
This is actually ensured by this property, that you require that these commute with these projections. If you would just consider any possible morphism, you would actually include new degrees of freedom. But you're now requiring that these actually are well behaved if you project on this first factor. So actually this means that you do not introduce new physical degrees of freedom in this way. And this is connected with the requirement that actually this should be covariant parameterization in order to ensure this property.
I would like to see it. Okay. Maybe I read your paper. Okay, then you explain it. Okay, thank you.
Yeah, thank you. Okay. Now in order to get some physical intuition of this, so I consider a S-parameterized field theory given by some connection A. And so in this case, it turns out that the configuration space is given in terms of even one forms of the S-parameterized manifold onto the adjoint bundle. And then this is actually isomorphic to the even part of a OS super module. So OS the global sections of the parameterizations, and F some infinite dimension super vector space given by restricting to the trivial parameterization. And then if you consider a change of parameterization, this naturally induces a pullback from the configuration space with respect to the parameterization S prime to the configuration space with respect to S. So actually one can get any configuration here by putting back configurations on this S prime parameterized field theory. So actually there arises a question naturally whether there exists some universal kind of parameterization S such that any field configuration with respect to some finite case parameterized field theory can be obtained via pullback. And this question has been first considered by Schmidt in early papers, and I have now considered this in the context of relative supermanifolds and using this Molokov-Sachs approach to manifold theory. And then it turns out, indeed, there exists some universal parameterization satisfying this property. And actually, I cannot explain this now in detail, but in this formalism, it turns out that using this universal parameterization in this context, fermionic fields can be described in terms of functionals on configuration space. So in this framework, it follows that fermionic fields are described in terms of functionals in the configuration space. So it's this fermionic field on the odd part of the configuration space to real values, just evaluating configurations on the point. And this is exactly the interpretation of fermionic fields in context of perturbative algebraic quantum field theory. So this interpretation of fermionic fields in terms of functionals and configuration space naturalizes in this relative framework. This is how they are interpreted in this approach. So if you have questions for this, you can ask me afterwards. Okay. Now, so far this was the mathematical methods. I would like to apply this to the context of supergravity. Therefore, at the beginning, I would like to review the interpretation of gravity in terms of a Cartan geometry, and then apply this to the supercategory. Now, Felix Klein, in his famous Erlang program, studied the idea of classified geometry of space by the Erlang group of symmetries. For instance, you consider Minkowski spacetime, and consider the isometry group is given by the Poincare group. Then you can fix some event, a spacetime event, and consider the subgroup of isometries which reserve that point, which is given by the Lorentz group. Then if you take the quotient between the spacetimes, between the isometry group and the Lorentz group, this turns out to be, this Closset space turns out to be diffeomorphic to Minkowski manifold again. So you can recover the Minkowski spacetime by the underlying group of symmetries. And so this leads to the definition of a Klein geometry in terms of a pair GH, where G is a Lie group and H is a closed subgroup, together with the requirement that the Closset space G model H is connected. So it follows that a flat Minkowski spacetime can be described in terms of a Klein geometry. And this, then based on this idea, then Cartan formulated a theory which is now known as Cartan geometry, which can be regarded as a deformed version of Klein geometry, just as flat Minkowski spacetime is just as gravity is the deformed version of flat Minkowski spacetime. And this is the definition of a Cartan geometry. So a Cartan geometry is modeled on a Klein geometry GH. GH is the flat model, described in terms of a principal H bundle, given by some principal bundle P, which can be regarded as the deformed version of your Lie group G. And the degree of deformation of this group G is encoded in terms of a connection defined on this bundle, which is called a Cartan connection, which takes values in the algebra of the H group G.
Sorry, I didn't understand it acoustically because there is an echo. P is G, or what is P?
P is a principal fiber bundle and can be regarded in terms of deformation of this group G. So
okay, why deformation?
Yeah, because we'd like to somehow deform this flat initial data, which is given. So this actually is called the homogeneous model, GH, and this should be somehow deformed in a certain sense.
Okay.
Mm-hmm. Yeah. And this deformation is encoded in terms of a connection, which one calls the Cartan connection. And this deformation is encoded in these properties of this Cartan connection. So the first one just means that if you project on the subalgebra of the Lie group G, you get an ordinary gauge field. And now the second one, this is the one which encodes this deformation, which is called the Cartan condition, which means that the Cartan connection is an isomorphism between tangent spaces of the deformed group to the tangent spaces of the Lie group G. So this deformation is encoded in terms of this Cartan condition.
I have to ask once more. So if you get rid of the super situation, if for instance G is a simple Lie group, you cannot deform it. Is this correct? Then you have G itself.
This is the ordinary category. At the moment, this is the ordinary category of smooth manifolds.
Ah, yeah, okay, but what is a deformation of G? Let's say G is SO, not this Klein situation where you have this extension with the reals, but same simple case. Can you deform this? No. So usually I know this P is G. So what do you mean by deformation? Give me an example.
Deformation. So what is? Maybe you should not consider this as too too formal notion now. It's just would like to illustrate this. How can this be interpreted? So just an example would be Minkowski spacetime and a curved supermanifold you consider in gravity.
But it isn't in this case you mentioned above P equal to G?
No.
And H is the subgroup of translations?
H would be the Lorentz group, for instance. And G would be the Poincare group.
Yeah, if you take the Lorentz group, M would be the Minkowski space or whatever the real space, whatever. Yeah, okay, yeah. But in this case, P is G. So I do not understand what the deformation is coming from. In the classical case, I'm not familiar with this. This was the question.
Yeah, the deformation is meant in terms of this condition here. So you can locally identify tangent spaces, so the linearization of your curved manifold. This is this principal fiber bundle in terms of the tangent spaces of your group G.
Yeah, this is the definition of a Cartan geometry. 1 and 2 is a connection which has this property of isomorphism and so on. But the space P, this was the question. Is it G or what is it?
It's not G.
Okay.
Yeah. Sorry?
And usually one way to say it is M is locally G mod H. Right?
Yeah, indeed.
And locally M is G mod H, and the sense it's a deformation. Example, I don't know, in Riemannian geometry, the curvature measures the deviation from flat space, and so here you...
Okay, I see. You look at a more general situation where you have a principal bundle and embed it into... Yeah, but then you embed it in you take... you have an action of G on P. What is the map from H to P? You have a map from H to G, but you don't have a map from G to P. You can map it to one fiber. Is that the meaning, or?
So you map a map of H on P naturally in terms of a H bundle.
But what is the map from G to P? G acts on P then.
There's no action of G on P.
Okay, that's a very general notion I'm not familiar with. Thank you.
Okay, so this now here to illustrate this example in context of gravity. So now you could consider Cartan geometry modeled on an entity space, described in terms of the isometry group of the entity space and the Lorentz subgroup. So this is the client geometry. And then you can take the Cartan connection and decompose it by rejecting on the translational part, which gives some soldering form E, called coframe. And this coframe field now induces by this ordinary Cartan condition a soldering, so local identification of tangent spaces of your curved manifold to the tangent spaces of your flat model, which is given by the entity space. And also another part given by the projecting on the Lorentzian part, which gives some Lorentz connection omega. And now using this connection A, Cartan connection A can formulate an action principle, and this I would like to illustrate in context of entity space. So in that context, you can use the fact that the isometry algebra can be identified with the Lie algebra of the symplectic group. In that case, the Lorentz algebra is generated in terms of generators Mij, which can be expressed in terms of gamma matrices. And then you can define an operator on the Lie algebra in terms of an operator P, which are called P infinity. And the reason why conic P infinity becomes clear in a moment. So this is in terms of I half gamma 5, the highest Clifford algebra element, mapping from SO3 to SO3. Then this can be used in order to define a product on the Lie algebra by contracting this with the trace. So this now defines an inner product on the symplectic Lie algebra. And then using this inner product, you can formulate an action principle, which is called the McDowell-Mansui action, which is a Young-Mills type action, but only like Young-Mills, so it's not only a Young-Mills action, but it has the form of Young-Mills action. So you take the curvature, the Cartan curvature of the Cartan connection, and then contract it with the inner product. And then by expanding this, you get indeed the first order Einstein gravity action in context of a non-trivial cosmological constant plus Power terms. This is how you can recover gravity by turbulence in terms of a Cartan geometry. And now I would like to extend this to host gravity, because now the host action of gravity is a alternative way of writing down Einstein's field equations. So the host actually encodes the same equations of motion as first-order Einstein gravity, but has some additional parameter beta. So it's a one-parameter family of deformed actions of first-order Einstein gravity. And this is the form of this action. So you get, at the first part, you get the ordinary Einstein Palatini action, E wedge R, epsilon I j k l. And you get some additional contributions, which depends on some parameter beta, which is called the Emisi parameter. And these terms turn out to be pure topological. So this is the reason why actually this has the same equations of motion on the bulk as Einstein gravity.
The second term is topological?
The second one, yeah, this is topological, yeah. If provided that omega satisfies its field equations. And then it turns out, if you use the canonical formulation, that the canonical symplectic phase space is described in terms of a SU2 gauge field A beta, which is the 3D spin connection plus beta times intrinsic curvature. And these are the so-called Ashtika-Bavera variables. And due to the fact,
did you say the second term is topological, or the difference between the two terms is topological?
No, this term. So this one is the ordinary one minus 1 over beta, the rest. And this is the topological term. So everything which is proportional to 1 over beta.
I thought it was the difference, so it was topological. Okay.
The first one is the ordinary term, and the second one then gives a topological term.
This is, here you have no cosmological constant, or do you have?
Yes, here in this context, yeah, sorry. So I actually should add here some, this would be just the ordinary cosmological term, then E wedge, E wedge, E wedge, E.
So you can write like as a differential of E wedge omega. This is...
But that's what it is, right?
This is what it is?
E wedge omega.
D of E wedge omega. Is the D of?
Oh.
I think. It should be.
I mean, it's E wedge omega with two different contractions, right?
Yeah.
No, but you need an additional differential. Because otherwise you don't get, I mean, the Einstein term is E wedge R.
Right.
And then if it is topological, it's D of E wedge omega. Something like that. Understand?
No, we're not looking. I'm missing the cosmological term in this.
Yeah, I'm considering here this flag.
No,
Cosmological term is not there.
Right.
Yeah.
Yeah, so I could add this here, and it would be just the ordinary E wedge term.
Right.
Yeah, so this would not be alternate, not changed then. Yeah, sorry, this is now in the context of Poincare gravity. And now if you do the canonical formalism, you find that the phase space described of a SU2 gauge field, and based on this fact that you have this gauge theoretic structure of the canonical phase space, you then try to formulate quantize the theory using techniques of lattice gauge theory, and this leads to the quantum theory of gravity, which is called loop quantum gravity. So this action plays a major role in this context. And then you can actually also describe this action using this Cartesian geometric interpretation. And here I describe it using this beta deformed inner product. So I introduce a beta deformed inner product in terms of an operator p beta defined on the Lorentz algebra, which is now some beta dependent Clifford algebra element. And in case that this parameter beta is equal to infinity, this reduces to the standard operator p infinity. So now we have some beta deformed parameter, beta deformed Clifford algebra element, and you can use this in order to introduce an inner product on the algebra by just contracting this operator again with the trace. And again, you can formulate an action principle, which I now call the host McDonald-Sui action, by again using an R-wedge R-type action and contracting the internal indices with this beta deformed inner product. And then you find by expanding this, you get the beta the host action of de Sitter gravity plus boundary terms. Okay. So far this was ordinary gravity and the host equivalent description of gravity. Now I would like to extend this to the supercategory and describe
this host term just changes the boundary condition. So it changes the boundary terms only.
Yeah, it changes just the boundary terms. Yeah. Now apply this to the supergravity and turn supergravity into supergravity geometry. In this context, I also talk about the boundary theory because the boundary theory turns out very special in this context. So here I now define a supergravity geometry, and in order to incorporate consistently the Fermi degrees of freedom, I now define this in the context of isolative supermanifolds. So define a supercardinal geometry model on a client supercardinal geometry model on a superclient geometry GH in terms of S relative principal superfiber bundle, H principal fiber bundle together with a supercardinal connection defined on this bundle, and with additional requirements. So the first one is again the one requiring that after projecting on the Lie algebra of H, you get an ordinary connection one form. So, and the second one is now the supercardinal condition. This now has to be adapted in order to ensure covariance and change in parameterization. So here is the definition. So you can always embed, but just to embed this principal fiber bundle, ordinary principal fiber bundle, super principal fiber bundle in this parameterization, and then require that by putting back this connection A on this bundle P, that this provides again isomorphism between tangent spaces of the principal superfiber bundle to super lambda modules of the algebra G. So here actually I'm using this Rogers-Leavitt approach of supermanifold theory. Actually can always interchange from one approach to the other. So this now is just gives some simpler interpretation of this. So this is now the supercardinal condition in the S-relative category. And then if you do not require this condition, you can call this a generalized supercardinal connection. So this is the definition of a supercardinal geometry in the S-relative category. And actually can also add additional structures on this. For instance, you can define a supercardinal connection to be reductive. This is the standard one you're using in context of in physics, by requiring that G splits in this form, can be split in this form with H, this superalgebra of the Lie group G, of Lie group H, and some closed space G model H, which is required to be invariant in the joint H of H. In this case, you call this cardinal geometry reductive. And you also can impose a metric, so we call the cardinal geometry reductive. If it is reductive, metric if it is reductive, and with this requirement you can define a metric on a closed space G model H. This is a joint invariant. Now, in case that your cardinal geometry, supercardinal geometry is reductive, you can use the supercardinal condition in order to find isomorphism E by projecting on this closed space of the Lie algebra, and this then provides an isomorphism in tangent spaces of your principal superfiber. Actually, this is not true. So this is the tangent space of the supermanifold M to the supermodule corresponding to the closed space. So this leads to local identifications of the tangent spaces of your manifold to the tangent spaces of your flat model. To this property, you can call this a supersoldering form, or you usually call it superfield line in context of physics. And then you can use this soldering form in order to lift this metric S on your metric cardinal geometry to a metric on your supermanifold. So this so you can define a metric G of smooth vector fields X and Y in terms of the metric on your Lie algebra in terms of S of EX star. So E maps the horizontal lift of your vector fields to the bundle, and then maps these to the algebra, and then you can apply this metric S. And this way, because you acquire a joint invariance, this defines a well-defined metric on your supermanifold. So in this way, it turns out that the manifold M naturally carries the structure of a superremaining manifold. So a metric reductive supercardinal geometry induces naturally the structure of a superremaining manifold. This is just one example where you can use the structure. So this interpretation yields a nice interpretation of a geometric interpretation of killing Spinors. So killing in terms of killing vector fields of the induced Riemannian manifold. So killing vector fields are defined in terms of vector fields whose corresponding flow preserves the metric. And then using again this soldering form, you can actually identify these killing vector fields in terms of sections of the spinor bundle. So all killing vector fields naturally interpretation in terms of spinors, and these are indeed the killing spinors you're considering in the context of supergravity and studying supersymmetric black holes. And these have the interpretation in terms of killing vector fields using the connection between metric cutting geometries and supermain manifolds. Okay. Now I would like to apply this in the context of supergravity. And actually this is the Castellani-Doria-Free approach to supergravity. And now I extended this, studied this in the context of S-relative supermanifolds, so in order to introduce properly the Fermi degrees of freedom. So I define now a supergravity in terms of a supercardial geometry, which is modeled on the Klein geometry corresponding to super analyticity space. So the superalgebra or super Lie group OSP14, OSP1/4, and this spin algebra spin group. So you have a spin principal superfiber bundle and some supercardial connection A defined on this bundle. And then you can again decompose it by projecting on the even part, which gives again the soldering form and the spin connection omega and some additional spin-free half field called the Richter-Schwinger field. And now this field is non-trivial if you pull it back on the body of the manifold due to the choice of non-trivial parameterization. And now again you can formulate an action principle, and now I would like to do this in the context of host supergravity. So you actually can also formulate an action, host type action of elemental 1 supergravity. And again, I do this introducing a beta deformed inner product. So in that case, you can use the fact that the Lie algebra of the orthosymplectic group decomposes in terms of the even part and some odd part, which naturally defines the Clifford module. So you can naturally extend this operator B beta, depending on this emissivity parameter beta, to a operator on the superalgebra, which is adding additional copy of this operator. Then again, this induces in a product on the superalgebra as a beta deformed inner product, but just contracting this operator with the supertrace. And then again, you can formulate an action principle, which is again the R of HR type action with R the curvature of the supercardial connection contracted with this beta deformed inner product. And by expanding this, you find that this indeed yields the host action of d equal 4r and 1 ADS supergravity plus some additional boundary terms. And these additional boundary terms now turn out to be very special in this context. And I would like to explain this in a bit more detail. So when we ask the question, what is special about the boundary terms which are contained in the superhost reaction? And therefore, when we write down the most general possible form of the boundary terms which are compatible with the symmetries of the bulk Lagrangian. In that case, we find that this most general form of the boundary terms is given by the sum of 4 individual terms, with the first one given by the Euler-Bonnet term, Gauss-Bonnet term, and the second one by the contracting term, which are topological, some additional fermionic boundary terms. And these seized arbitrary constant coefficients. And now, by having this most general form of the boundary Lagrangian, you may ask the question, by adding this boundary term to the bulk Lagrangian, that the full action is still invariant under supersymmetry transformations, in particular under supersymmetry transformations at the boundary. And this question has been first considered by Andrianopoli and Dorea, and also by collaborators, Andrianopoli, in a series of papers. And therefore, one uses the Castellani-Dorea-Frey and Dorea-Frey interpretation of supersymmetry transformations in terms of superdifferomorphisms. Supersymmetry transformations in this framework are described in terms of superdifferomorphisms, which are actually directed in the odd direction of the manifold, so the contraction with the soldering form is 0. And if you then, study these type of hypersymmetries, you find that if you require supersymmetry invariance at the boundary, this imposes an additional boundary condition, requiring that by contracting the full Lagrangian with this superdifferomorphism X is actually 0 at the boundary. So you get this additional boundary condition. And then it turns out by studying this condition, this actually uniquely fixes the constant coefficient Ci in the general expansion of this boundary term. And we have studied this in the context of host supergravity. In this case, you have these additional contributions. And then again, it turns out these coefficients are again fixed unically. And in that case, you end up with this boundary term. And interestingly, by adding this boundary term to the full action, this exactly reduces the superhost McDonald action. So imposing supersymmetry invariance at the boundary uniquely fixes the boundary terms, and by adding this boundary term to the bulk action, this reproduces exactly the superhost McDonald action. Yeah.
Sorry, I'm a bit confused. So you were saying before, if I start with a bulk action, I mean, this is just something that does not depend on this seniority parameter beta.
Yeah, and
there's a unique solution for the coefficient Ci, and now you have something which has a free parameter beta at the bottom. Is this
So this beta term is topological only in case that you impose field equations of omega. So the bulk action would be just the ordinary host action without boundary terms. So host action on the bulk And then you introduce additional boundary contributions, which a priori do not depend on beta.
Okay, so beta is also the bulk part.
Yeah, yeah. And then these coefficients also turn out to depend on beta. And then you find this supposed McDonald's reaction. Yeah, and then you can ask the question, can this also be extended to extended supersymmetry? And the answer is yes, and we have considered N=2 supergravity. In that case, the Cartesian connection has additional contribution, given by U1 gauge field, close to gravity photon, and two multiplets, two spin-free half multiplets, spin-free half vector Schwinger fields in the multiplet. And again, we make the most general form of the boundary term, ansatz for the most general form of the boundary term, and require by adding this boundary term to the full action, to the bulk action, that the full action is again invariant supersymmetry transformations at the boundary. And again, this has been considered by Andrianopoulos et al. Here extended this to the context of host supergravity. In that case, one finds that the superhost McDonald-Mansur action for N=2 supergravity can be again written in this McDonald-Mansur form. So again, you have some beta deformed in the product by having this operator B beta, introducing this operator B beta. So B beta is now a operator on the space of OSP 2,4 value 2 forms, which has now this additional space-time operator here, depending on this Hodge-Star operator, and some additional term here. And if you now expand this, you see this term here, because the ordinary Maxwell kinetic term is actually this Hodge-Star term, FH Hodge-Star F, but you get an additional contribution, which is the topological term, which is actually known as the theta term in quantum electrodynamics. So, and actually this depends now explicitly on this Barbera-Misi parameter. So in this context, it follows that this Barbera-Misi parameter can be interpreted in terms of the theta parameter of the theta ambiguity in QED. Now let me say something briefly about the chiral theory. Now, a priori, I've discussed this for arbitrary Barbera-Misi parameters beta. So beta could be a real value, could be also infinite, or could be also imaginary. Now, in case that this Barbera-Misi parameter is imaginary, this action has some very nice properties. Because a priori, this operator does not commute with supersymmetry transformations, with gauge transformations seduced by the. Sorry, yeah?
Yeah, so I have some questions. These actions that you wrote down are just on the bosonic word sheet here. I mean, word volumes are purely bosonic ones. So you have fields that have a supergroup target space type of fields. I mean, these are elements of, a representation in the superalgebra, okay, fields. So the fields are mapped from a bosonic manifold M into superalgebra. And then this is super trade. So you don't have any superfields in the sense of a word volume theory.
You have, due to this non-trivial parameterization.
Where is it there? I mean, in M, there is nothing. M is not the super manifold.
Yeah, so it's the body. So you actually consider this as no. So the function sheaf is the function sheaf on the supermanifold M tensor function sheaf on the parameterization, and you're just integrating over the degrees of freedom on M. So this functional is a functional on the parameterization.
So M is the supermanifold.
M is the body. So the bosonic part of your supermanifold.
The bosonic part. So it's just purely bosonic manifold, and you map the fields into a superalgebra. That's it.
Yeah.
Okay. But what is new with respect? I mean, these things have been done several years ago. I mean, what is different from? I would like to understand what is different what you're doing in respect. So I know this action. I mean, okay, maybe you have the modification of all terms. Okay, that I agree. But I don't understand what is. I mean, I suppose that the p is equal to 1. So what is different? What the people know? I mean, I know this action. I mean, it's Mac-Mansur reaction for RDS4.
Yeah. So this is a mathematical. To find a mathematical framework of this. So to somehow relate this to the supermanifold theory and to incorporate this framework of freedom. So they get some interpretation in terms of parameterized supermanifolds and
But if I don't know the mathematical structure, I can write down this superconnection. I mean, if you give me a superalgebra, I can write down superconnection, and then I automatically can write down the X action. So what is the new information? So why I should do that? I mean, I will be happy to understand this point because I mean, you built up a very nice mathematical structures. I want to understand what is more what I know about this action from your mathematical framework.
Yeah. So first of all, it does on classical theory, but in the context of quantum theory, you have some nice relations to this. So I don't talk about this, but in loop quantum gravity, you describe the configuration space in terms of inductive families of Hilbert spaces. So this is how you define how you quantize gravity in context of loop quantum gravity. And now you have the inductive family. In addition, just ordinary errors, you now have that have squares. So in this context, you have some nice relation between change of graphs and parameterizations. So and this structure somehow gives you a nice, or naturally the product of the Hilbert space. So there's a nice relation between parameterization and the construction of Hilbert spaces. Yeah, I didn't talk about this, but also we applied this in the context of cosmology, quantum cosmology, and then we have studied invariant connections, and there this parameterization turned out very important, because in this context you could indeed derive a invariant connection, which is the one which was considered by Heath and Hawking. And this you get very naturally in this parameterized formalism. So you can everything study rigorously, mathematically, and then you get structures you observed in physics using this structure.
Yeah, so beta is still a real parameter, or does it get complexified?
Beta could be any, so beta could be real. Normally in loop quantum gravity, nowadays you're assuming beta to be real. Apart from zero.
I'm asking from supersymmetry point of view, because theta usually gets complexified in the context of supersymmetry, right?
So this action is still invariant in the supersymmetry transformations, also for real beta.
Is there a way, so I guess you have some kind of the supersymmetrization of this Holz term or something like this involving the Rabi-Dershowitz field. Was it somewhere on your slides? I'm sorry.
Maybe I should have written it down, yeah. So you get the beta deformed bosonic part plus some beta deformed fermionic contribution, which actually is the ordinary one by just inserting this where is it? This operator before the covariant derivative for the Rita-Schwinger field. And then if you study supersymmetry variations, all these terms cancel exactly, and again the action is invariant in the same supersymmetry transformation as ordinary supergravity.
This was the bosonic part, right?
Yeah, this was the bosonic part. So you get so if you do supersymmetry transformations, you got contributions to the bosonic part, you get also contributions depending on beta, and variations of the fermionic part depending on beta, and these terms are cancel exactly.
I was actually going to determine the action that supersymmetrizes this whole stuff. Not the boundary terms, but
yeah.
I mean, this whole thing was this E wedge omega, the different contraction, which was topological. So what's the supersymmetrization of this? In terms of the Rita-Schwinger.
So this would be
the component, just the component formulation.
It's the same. It's the same Rita-Schwinger field term again, just that I don't know whether it's with gamma star, just removing or adding a gamma star. So it's some some axial contribution.
You have to be very careful, because actually this is not really word volume supersymmetry. It is a supersymmetry. It's a superspace supersymmetry. So namely, it's just the fermionic transformation of the superalgebra. Okay, and so it doesn't really mean that these terms is supersymmetrized in the usual way. Okay.
Not in the usual, but in some way. I mean.
Yes, but it is not in the supersymmetry as we are used to in the supergravity.
So I was also talking about this imaginary beta now, maybe. So You could also choose imaginary parameter, so beta equal to plus minus I. In that case, it turns out that this action has some nice additional structure, because now this operator P for beta equal minus I now becomes a proper projection operator onto a proper superalgebra of the orthosymplectic algebra, OSP12. So it maps the Barnes generators to chiral components Ti plus and the fermionic generators onto the Ryle components QA. And then these form a subalgebra, which is given by this so-called orthosymplectic algebra OSP12. And then due to this fact, it turns out that this action now is indeed manifested invariant on large gauge symmetry, so the OSP12 gauge symmetry. And something similar happens also in the N2 case. Now you can use this projection and apply it on this supercartesian connection A, and then you get this superarchetype connection, so we call this the superarchetype connection A plus, which contains the ordinary self-dual archetype connection A plus some fermionic contributions given by the Y components of the Richter-Schwinger field. Now, using this superarchetype connection, you can use this in order to reformulate your action, and you find that for both cases n equal 1 and n equal 2, this action can be split in this form. So the bulk term is the structure for BF, super BF type action, with E the superelectric field, which together with the superarchetype connection builds up some gradient symplectic phase space, plus some additional boundary term. And this boundary term now has the structure for OSP N2 super-Chern-Simons theory, and with some complex Chern-Simons level. And also get some, if you study the equations of motion, you get also some additional boundary contribution, and this is the one which couples the courage of the archetype connection A plus on the boundary to the superelectric flux in the bulk. And which is a complete analogy to classical theory, if you study isolate horizons in the context of loop gravity. So again, studying boundary terms and requiring consistency with the supersymmetry transformations at the boundary uniquely fixes the boundary terms in the context of imaginary Babin's parameters yields a boundary term which is given by OSP into super-Chern-Simons theory. Okay. And now based on this, we have studied the quantum theory, so also for real beta, but also for imaginary betas, because this superarchetype connection now turns to be a natural candidate to quantize supergravity in the context of loop quantum gravity. And we have seen that it also exists in context of extended supersymmetry, and by its very definition, it contains both gravity and matter degrees of freedom. And based on this, we have quantized the theory using standard techniques, and found some relations to the standard quantization scheme of fermions in LQG. And it turns out the boundary theory is described in terms of Super-Chern-Simons theory, so it actually is also a natural candidate to study inner boundaries in the context of loop quantum gravity, study, for instance, PPS states in the quantum theory or supersymmetric black holes. Interestingly, there is some nice correlation with the distribution of boundary theories in string theory in the newer works of Mikhailov and Witten, because they consider certain brane and string configurations, and they also encounter Super-Chern-Simons theories on the boundary described in terms of orthosymplectic groups, but also super-unitary groups. And something similar now happens, of course, in a completely different scheme, but we also observe this orthosymplectic gauge symmetry on the boundary. And so we would like to learn from these, because they also consider complex groups and complex Chern-Simons levels in order to better understand supersymmetric black holes in the context of LQG. Okay, so to summarize, there are many different approaches to supermanifold theory, given by the Bell's and Konstantin lattice, the Matthias-Stewart approach. A multiple-successive approach shows that all these different approaches are actually the same, just different sides of the same coin, and it leads to a unified description. But there's some common issue related to the lacking of uncommuted fermionic degrees of freedom of the body, and a nice resolution is given by adding a parameterization supermanifold and study parameterized supermanifolds. But the parameterization a priori is completely arbitrary, so we have actually require covariance and a change of parameterization. And studying this covariance property, one finds that this actually is a universal parameterization, and this leads to a description of unaccumulated fermionic degrees of freedom in the context of perturbative algebraic quantum field theory. They then also studied defining supercardian geometry in this relative category and interpreted supergravity in terms of supercardian geometry. Then we also derived the host McDonald-Mansui action for n equal 1 and n equal 2 extended supergravity, and also discussed the uniqueness of boundary terms in this framework if one imposes supersymmetry invariance at the boundary. And the beta can be interpreted in terms of theta ambiguity. This is some nice result in this extended context to give some interpretation of this beta. And we also studied this self-growth theory, and this theory has also such properties. It can be recast in the form of constraints from the F theory in the bulk, and the boundary theory is the structural solution Simon's theory. And we have also studied the quantum theory, so we have studied quantization using this self-truth theory, and we find some very strong relations to the quantization scheme of fermions and Lucon gravities. That's also some nice result. And we also applied this context of cosmology, and there this parameterization turned out to be very useful because it gives us a nice structure of the reduced connection, which is the one used by Deeth and Hawking. And now for in the future work, we'd like to apply these terms to study charged supersymmetric calls, and for instance, compare the conscription of supersymmetric calls with energy computation with string theory. Also, we'd like to extend this to extend supersymmetries with n greater than equal to 3, study the boundary terms, and ask the question whether the boundary terms are again fixed uniquely, and whether this leads to a Cartan-like description of gravity theory, so geometric interpretation of gravity. Also, we'd like to relate this to the integral form formalism studied by Castellani, Grassi, Catenacci, and Catenacci, Grassi, Noia. And also we'd like to, because so far we have applied this in the context of ADS supergravity, so we'd like also to remove the cosmological constant. And these are some works of Concha, Ravera, and Rodriguez, so we'd like to consider also the limit L to infinity and study the host variations of this. Yeah, and many other works such as coupling matter to Lucon gravity and so on and so forth. Yeah. Thank you very much.
So, are there any questions?
I have a question concerning these resolutions. So you used them, as far as I could see, to do a relative theory over S. What helps the resolution, or is it necessary? Why couldn't you just work relatively over some base without using resolutions? Can you explain why they are essential?
So what do you mean by a base?
You just consider the category of superspaces over a base S, which means you have a map of the supermanifold to S, and morphisms are just maps between supermanifolds which commute with this map to S, in the sense of Grothendieck, relative theory over a base.
Yeah, so this you could, actually there's some more generalization of this formalism, so you could consider these product supermanifolds, S times M with S some parameterization, and M a supermanifold. But you can consider this more general slice category. So you, as you say, maybe so having some morphism from supermanifold to this parameterization of some base supermanifold. Yeah.
Yeah.
You can study this more general category, and actually you find that this actually is equivalent. Can be reduced to this example. Where
this I can imagine. Yeah. I believe this indeed, because the superstructure is that complicated in a sense. So, but it's a technical trick to make computations then in a certain sense. Yes, I understand. And the second question I have is, you mentioned at the end reality conditions and difficulties. Can you just give a very short idea what is going on there?
Yeah. So in the context of chiral supergravity, you mean?
Yeah.
Because in chiral supergravity, we are actually working with complex supergravity. So actually, we want to cover ordinary real supergravity. In order to get this, we actually have impose some conditions to ensure that the equations of motion resulting from the chiral theory actually equivalent to the ordinary real supergravity theory. These are the reality conditions, and they are highly nonlinear. And this is the issue of the chiral approach, that you somehow have to solve these reality conditions, highly nonlinear conditions in the quantum theory. And the quantum theory is some linear theory actually, so this is a very complicated issue. But you can solve this partially if you consider, for instance, cosmological models. So we have considered in this context cosmological models, In that context, we have encountered that this chiral structure, this large gauge symmetry structure we have in the theory, can be used in order to get nice symmetry-reduced connections. And in that context, this parameterization turned out very useful. And then in this symmetry-reduced setting, we were able to solve the radiating conditions and also to formulate the quantum theory. And at the end, we find similarities with models considered by Deeth and Hawking.
Ah, yeah. Thank you.
Other question?
I have a question about something you had on your outlook, or I mean, the very last slide related to the entropy calculation. So if I remember correctly, in the bosonic context, I mean, people have compared the quantum gravity entropy calculation to, let's say, Schwarzschild, Bekenstein, Hawking, and this fixed the Barbero-Mirzi parameter. Do you expect to find?
No, so we are working in the chiral approach. Yeah. So there's two different viewpoints. So actually three, or now even other ones. But if you consider real Barbero-Mirzi parameter as one approach, which then shows that if you compute entropy, these are indeed proportional to area, but not going to get the right factor 1/4, you have to fix the Barbero-Mirzi parameter. Yeah. But there's also another approach, a new approach in this real framework to study this beta, interpret this beta in terms of a renormalization parameter, and then this beta just disappears. So there's a new development. So just to get rid of this beta dependence. And in the context of the chiral approach, so beta equal minus I, beta is fixed already. And then you can actually show in a certain context that this exactly reduces the Bekenstein-Hawking entropy in highest order. So this dependence on beta now disappears in this chiral approach. And we are in this setting working in the chiral approach.
So, sorry, I have to understand. So if this beta disappears, the entropy turns out to be correct?
Yeah. Mm-hmm. So in this real case, you interpret beta because this is what you would like to study in AQG. You would somehow recover ordinary supergravity, in supergravity or ordinary gravity. And because we are working on discretized spacetimes, we would like to recover continuous spacetime, and then there's some new idea to get this in order to interpret by performing coarse graining, so a renormalization of discrete gravity, and then in order to recover continuous spacetime and so on and so forth. In that context, beta can be interpreted in terms of a renormalization parameter. So this beta disappears in this context because beta should be something non-physical. And if you have this beta fixed to some specific value in the entropy computation, beta becomes something physical, which should not be the case.
So you said that beta could be thought of as a theta parameter.
Yeah.
And actually, there's a question there, which is what are the analogs of instantons?
Yeah. Yeah, to study the boundary theory and the interpretation of beta as this boundary term, I'm not completely aware of at the moment, but yeah, this would be some interesting question. Yeah.
It's not black holes.
No. Yeah, this beta. Maybe you could discuss this. I'm not really aware of the question now, but yeah.
Any last question?
If I can ask another very quick one. So all the things that you were doing were very much tied to 4 dimensions. And can you make any comments about other dimensions?
Yeah, this is some new development of Thomas Thiemann and collaborators. So Thomas Thiemann succeeded in extending these Ashtika variables, which you can formulate, which you can find in this canonical description of host gravity, now also host supergravity, now to extended spacetime dimensions, so higher spacetime dimensions. So these variables you cannot find in the level of action principles, but you can find them by performing a certain applying symplectomorphism on the ADM phase space in higher spacetime dimensions. And then you get variables similar like to the Ashtika variables, also depending on some parameter. But you can find these variables also in context of higher spacetime dimensions. So this is possible. But at the moment you cannot, at least for spacetime dimensions, 3 to 5, I'm not sure. But you can, at the moment, not derive them from action principle, similar to host action.
Supersymmetrization.
Also, yeah, okay, this has some, it's not that beautiful at the moment because you can derive that geometrically, but you can also extend this to a supersymmetric context. But it's then actually a bit, it's not that, it's somehow you have some ambiguities in this framework, but at the moment you can at least prove that you can, or at least show that you can find these type of variables also in context of higher space dimensions. And you can also use this in the context of supersymmetric field theories.
Okay, so I think again the speaker. Thank you very much. So we are a little bit late. I would say that we're back at 11:15. Cyril Closset. You have to remind me what your questions are. I don't believe you're still. Yeah. So welcome back. We're very happy to have John Huerta, who's going to speak about bundle gerbs on supermanifolds.
Hi, thanks very much. It's really nice to be here. Thanks very much to the organizers for inviting me. It's really nice to be in this lovely city, this lovely university, and to interact with people in person. Where's the shot?
You have enough? It's budget cuts. I can get one. You need one?
No, I think it's okay. I mean, there's a bunch of little pieces, so we'll see how it goes. All right, so actual title is bundle gerbs on these supergroups, which are particular kinds of supermanifolds. Before I get into the meat of the talk, I'd like to give a little motivation, which is about the Western-Witten model with target G, an ordinary, compact, simple, and simply connected Lie group. E.g., G equals SU2. So, the Western-Witten model is a sigma model, so it's a theory of maps from a surface into G. And the point of the motivation is that WZW is controlled whatever that means, by a bundle gerb let me say WZW at K is controlled by a bundle gerb script G sub K on the group G. And to say how this works, I'll just draw some pictures. So here's the group G. Here is the surface sigma being mapped into G. The surface may have some boundary, and that boundary will then be restricted to lie on a particular submanifold of G. This is called a deep ring in the Western-Witten model. And what the bundle gerb allows us to do is to take this data GK takes this data and computes an amplitude for this configuration. That is a unit complex number. And it does this by defining a quantity called the surface polynomial. These amplitudes, you then feed them into the physicist's greatest tool, which is the path integral. Which, since I'm a mathematician, I'm just going to draw literally as a black box. and you get out a conformal field theory. A 2D conformal field theory called the Wess-Suminer-Witten model at level K. Are there any questions about this motivation? So,
sorry, are there any constraints on the brain? What kinds of brain you consider?
yes. So I probably want to consider, I think in principle this could work for any kind of brain, but the kind of classification theorems that I'm trying to reproduce in the supercontext work for what are called symmetric brains, or Cardi brains. And that requires that the brain be a particular submanifold of your Lie group, such as a conjugacy class. So the key point is that there exists a unique bundle gerb G on G called the basic gerb. And GK at level K is just a tensor product, a tensor power of this bundle gerb. So there's one bundle gerb that generates everything. And the question that begins my talk is, so the overarching question is, can we construct WZW with G a Lie supergroup in the same way by finding a bundle gerb and defining the surface holonomy of some surface being mapped into G. And if so, step one, which is the point of my talk today, define the basic gerb on G for G Lie supergroup. Okay. So that's our setup. For the rest of the talk, will be organized as follows. I'm going to give you a gentle introduction to bundle gerbs. tell you what this thing is, or at least any properties that it has. Then I'm going to tell you about bundle gerbs on supermanifolds in particular. Then I will specialize in the case where that supermanifold is a Lie supergroup. And if there is time, there will probably not be, but if there is time, I will do some wild speculation about brains in Lie supergroups. Okay. So what is a bundle germ? So here's my slogan. This is that bundle gerbs are line bundles plus 1, where you add 1 to everything. So here's a picture on a manifold M. A line bundle is a topological space over M. A bundle gerb G, in terms of spaces, there's more data, but in terms of spaces, it's a line bundle on a certain fiber product or a topological space that covers M, that is subjective submersion onto M. And to data like this, I can associate a characteristic class for a line bundle. That's called the first Chern class. And it's a class in the second integral cohomology of M. For a bundle gerb, this characteristic class is called the Dishmir-Jauji class. It's a class in the third integral cohomology of M. In physics, we want to equip our line bundles with connection, and I can do that. And so line bundles have connections, I'm not going to name it. They have connections which are locally one forms. AI for some patches, for some open sets covering. A bundle gerb, there's also a concept called a connection, and that's locally given by two forms on open sets for some open cover. Okay. When you have a connection, you should think about the curvature. And if I take D of these two forms, it turns out that's a globally well-defined two form. That's the curvature. Bundle gerbs have a curvature 3 form given by taking D of these two forms.
Excuse me.
Yes, please.
What would be the conditions such that F is not globally well defined as the two form? Could it happen?
Such that F would not be well defined?
Automatically that F is globally well defined?
Right, so basically the condition is that the difference of AI and AJ on the overlap, D of that has to be 0 for F to be well defined.
Sure, but could it be something pathological such that you cannot do it?
Not that I know of. And finally, this 2 form, this is closed. Obviously, D of it is D squared as something else, at least locally. So it represents a class in de Rham cohomology. And that class in de Rham cohomology is the same as the class, the characteristic class in integral cohomology. So once you map this into real cohomology, these have to agree. We say that F represents this class. And the same equation holds for bundle gerbs. But in degree 3. Yes?
I have a question.
Please.
So I've thought about that for many, many years. So if you have a 2 form, and I believe one DB2 is fine, and you say B2 is a 2 form. Now, of course, as you know, we like to add to DB2 a Chern-Simon. If we have a 1 form, an abelian one, the ADA is 3 form.
Yes.
Chern-Simon. Yeah. And then we use in practice G3, which is not going to be a 3 form because it's DB2 plus Chern-Simon.
Oh, okay.
Now, in this case, you have a way to
do like a
to explain what is B2. In the past, I had many discussions with Singer about that. And
so, like your question, so it sounds like you're asking about sort of a secondary characteristic class.
I say that in this language, indeed, you can describe very well what is a 2 form. And then D of the 2 form is a 3 form.
Yes.
But now, you can add to the 3 form a Chern-Simon ADA plus 2/3 of AQ. Right? And then the question is, how do we interpret the sum of DB2 plus Chern-Simon? And B2, and this field B2 occurs in physics, of course, because it's that's the way you couple in supergravity. As soon as you want to couple QED to supergravity in 10 dimensions, then what we call the curvature of the 2 form is not DB2, it's DB2 plus Chern-Simon. So it's an object, which makes a lot of sense for us.
So I think, I don't know, but I can speculate that you can interpret that as being itself data coming from yet another object called the Chern-Simon's 2-gerb. You add 1 to bundle gerbs, you get things called 2-gerbs. And I suspect that this is the kind of thing you're talking about.
And is it a new object or something very old?
So after bundle gerbs were defined by Murray, like Like people talked about gerbs a lot in the 90s, and Murray Stevenson defined bundle of two gerbs around 2000. So it's it's middle age for a mathematical object, I guess. Okay, so the theorem about line bundles due to Konstantin, which I will state very informally, is all of this in this column works for M a supermanifold. And the theorem that I proved in my last paper is that the bundle germ version likewise works for M a supermanifold. Okay, so before I get into the details of supergeometry, what kind of thing works? So the main construction for this talk is that if H, omega 3 of M is closed and integral. So this means something completely different than what than integral forms on supermanifolds. It refers to the classical notion of integrality, which is that the class of H lies in the image from the integral classes to the real classes. Then there exists a bundle germ G with the curvature of G equal to the three form H. So this construction, so for line bundles, this is something that you would say about two forms. That if you have an integral two form, then there's a line bundle on M whose curvature is that two form. For bundle gers, this is something you say about three forms, and my point is that the way I've written it here, it works equally well in geometry and supergeometry. This statement applies. So in particular, we can get our hands a little more on the basic germ. Basic germ. for G compact, simple, simply connected, we could define the following freeform. H equal to the trace of omega paired with the bracket of omega with itself. Here, omega is the Moyer-Cartan form. And trace is an adinvariant inner product, like a Killing form. And the key thing is that this is defined only up to rescaling. So we can rescale trace so that H is integral. And not just integral, it turns out, for this case, this cohomology, third cohomology of a compact simply connected Lie group, is just the integers. And the real version is just the reals. So you can rescale H so that the generator of this cohomology, which is just 1, goes to the class of H. The smallest scale it can have and be integral.
So my question was about adding to this H dB2. dB2, and
dB2.
define what is B2 such that H is a screw form. Omega, 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 of course, is, you know.
So the way I'm talking about it here, H is dB2. But, yeah, I don't know, maybe we can talk about that later. So I have the statement that if H is integral, then there is a germ whose curvature is H. And here, this, for G simply connected, the statement is even better, which is that there exists a unique G with curvature equal to this 3. And yeah, it's the uniqueness part that's better, because this is a result on the topology of G. And moreover, any other gerb, bundle gerb, on G is a tensor power. So if I take my G, my basic gerb, and look at its tensor powers, I get all of the possible bundle gerbs on G. Any questions about this example? supergeometry yet. Let me do that now. Remember this statement. This is going to be the key to the final construction. I have an integral freeform on a supermanifold, and there is a bundle term at curvature. So I'm not going to get too deeply into the technicalities of supermanifolds, but I will use what Konstantin was calling the Constant lattice formalism, which is the one that most mathematicians use. Which means that a supermanifold and a supermanifold is an ordinary manifold equipped with a sheaf of supercommutative superalgebras. So this ordinary manifold, I'm going to call this the body. I'm going to steal DeWitt's terminology and call the ordinary manifold the body. And this is a sheaf of Z mod 2 graded commutative algebras. That's the formalism I'm working in. Although hopefully you won't see much sign of it. So, the statement I gave before is still true, but I want something distinctly, I want to say something super about bundle gerbs on supermanifolds. So, let's try to talk about things that are specifically super. So the body is always included canonically into the supermanifold. But for some supermanifolds, there's a map going the other way. It's called the projection. Actually, it's not called the projection, it's a projection. And it has the property that if I do first I and then P, I get the identity. So, projections may not exist. But they exist in lots of special cases. So, Vera, this theorem is often attributed to Batchelor. For smooth supermanifolds, P exists. Batchelor proved more, but I'll take this implication. And Batchelor's advisor Constant proved that for G, the Lie supergroup, but it doesn't need to be a smooth Lie supergroup. It could be a holomorphic Lie supergroup. It could be in lots of categories. It could be algebraic. P exists. So, and for me, because I'm interested in supergroups, and I'm going to work in the smooth category anyway, I'm going to assume P exists. That there is a projection map on my supermap.
The omega, Cartan would have a partner in this.
Yes. Yeah, there's a more Cartan form on supergroups. That's right.
Is it going to be something like what we call the Fedayef-Popov groups?
A what? Sorry?
Fedayef-Popov groups of a connection.
Fedayef-Popov?
Fedayef-Popov.
I don't know. It works very much like in the classical case. It works by basically the more Cartan form. The theorem is that the left invariant vector fields define a basis for your, they completely frame your supermanifold. The more Cartan form is encoding this.
When you have written this free form, you have it on purpose that you omitted to say, explain how it transforms under some gauge symmetry?
So, right, I didn't say how invariant it is, but it's actually, for this case, I would say it's as invariant as you could hope, which is that it's invariant under the left and right actions of the group independently. That will also be true for the supercase. Okay, so having these P,
John?
Yes.
Should I read Constantin's theorem as in the category of supergroups, so P is a homomorphism?
No, P is not a homomorphism.
So it just follows from Bachelor. I mean, Constantin proved it first, this result first maybe, but does it just follow from Bachelor's?
Okay, so actually I don't, Constant constructed, so P's existence is a consequence of the supergroup being split. And Constant constructed a explicit splitting of any supergroup. Bachelor's theorem follows from showing that the obstruction to splitness. Bachelor proved that all smooth supermanifolds are split, which implies the existence of P. And that follows from the fact that the obstruction to splitness is that's computed by C infinity sheaves, and those are all solved. So obstruction actions. And I view Constant's theorem as following from another result, a nice paper of Kozul, where he proved that these splittings exist if and only if you have a linear connection, just an affine connection on your supermanifold. Then you can think of the more Cartan form as defining your affine connection on a super Lie group, and that defines the splitting. That's all I like. So to your question, P is not a homomorphism, but it should be invariant under left or right translation, depending on whether you're taking the left or right more Cartan.
That's the extra bit that you want. That's what makes it different than the bachelor's thing. It's this extra invariance that wouldn't make sense in the general.
Yes. Yes. Somewhere in the statements I'm going to write down, that's going to be used in the proof. I don't think I will get to that specifically. Okay, so the existence of P gives what I like to call body and soul decomposition. Again, stealing terminology from DeWitt, but using it in the Bears and Konstantin Eder's journal. For example, for any degree k in the Durand complex on my supermanifold, I can pull back to the body and get an ordinary k form. It turns out this map is surjective. So I get a short exact sequence. This is just the kernel. Of I star. But the existence of P splits this short exact sequence. So this implies that the K-forms on the full supermanifold decompose into K-forms on the body and K-forms in this kernel. K-forms just pull back to the body is 0. So any K-form, this is not the Morikaton alpha, has a body part and a soul part. So what do these maps look like in coordinates? Just to quickly give you a handle on this, I star always looks like set theta, set your odd coordinates, equals to 0. So for example, x, the even coordinates just go to x under I star. dx just goes to dx. But theta and d theta, those both go to 0. So in that direction, that's what this map looks like. But P is a choice, and you can choose different P. So I could choose, for example, P star that sends x. It can go to any even element. So I could send it to x plus theta 1 times theta 2 if I'm working in this number of dimensions.
May I ask something?
Please.
I'm trying to follow.
Please.
So you have coordinates x mu, right?
Yes, exactly, yes.
And you have coordinates theta.
Yeah, theta elements.
And you have a d theta which commutes.
Yes.
Theta commutes. Now,
yes, exactly.
Now, at some points, I guess you have to introduce a gauge field. Which is a connection, mu dx mu, mu dx mu.
Yes.
Then you will get a guy, a theta.
So, like, yes, that's right.
A theta, d theta.
Yeah.
Now, as a physicist, I claim that this a theta is the Fedorov ghost that you use to expand, to get rid of Fedorov determinant when you do something about the gauge field. So I claim that a theta, which is the generalization of the gauge field, is.
So you're doing super gauge theory? Is that what you're
doing? No.
So you're doing ordinary gauge theory on a super base.
And I want to, the goal of older people, older than me, was to really understand the role of your three form was written in terms of one form.
Right.
Okay. And this one form will be related to the a theta.
I didn't know that. That's interesting.
Yeah, it's something like that. So in a sense, for physicists long time ago, there was a hope to formulate ordinary Young Mills, coupled with John Simon and all that, in that kind of superspace.
Okay.
It failed.
Okay.
It deeply failed because, but still, there are, all little things that you define here, they can be transcribed in the language of quantum field theory for the Young Mills theory.
So yeah, I don't know. I don't know much about the quantum version of this story. But I find
it's really, actually it's classical because you write a Lagrangian and after that it's up to you to try to define a path integral out of it. Before doing the path integral is purely classical. So what we call the ghost is a purely classical object.
But the data pop-up isn't that for it's a tool to do a gauge fix, is that right?
Well, use it for the gauge fixing.
But the BRC symmetries comes out of geometrically. So what Laurent says is that indeed if you extend the space, you can create the BRC symmetry come out of this geometrical approach. Okay. So
sure.
It's not related to gauge fixing. You fermionize the symmetry and that gives you the geometrical thing. Then afterwards you can do gauge fixing.
So this is the ghost. This is the ghost of the
C, right, the ghost, right.
Yes, okay.
And the mystery at the end of the day, I'm sorry I interrupted you, I'm really sorry about that, but the real mystery which has been floating around since Chaplin-Menton defined the coupling between the two form and the Chern-Simon, that was the nightmare is that we don't understand what is the two form when its curvature, what we call it the curvature, is dB2 plus the trace of omega, d omega that you had before.
Okay. Yeah, I don't know. It would be nice if we could sit down and write down some of these expressions.
Very simple.
But something I want to say is that, so like introducing these ghosts and thinking of that as an aspect of supergeometry, I absolutely support it.
Yes.
But this is not what I'm trying to do here. Here I'm trying to write down a supersymmetric field where the fermionic fields are going to be, they're going to sit in degree zero.
No, but what he was saying that this supersymmetry is BRST symmetry.
Yeah.
So its squared is 0.
Yeah. But just to get back to this example, if I have, so I could choose P to just take x to x, but I can choose it to take x to any even element. And if I do that, then dx has to go to d of this thing, dx plus e theta 1, theta 2, plus theta 1, e theta 2. So when I'm applying P, I can pick up some things that have thetas in them. So there might there might end up being some thetas in this when you're viewing it as living on the supermanifold, because you're doing P, you're applying P to lift this up to the supermanifold. It depends on your choice. Okay, any other questions? Okay, so now what I want to do for my bundle chirp story is I want to do the body and soul decomposition for H, for this 3 form. So I can split this 3 form, both of these pieces, into body and soul. DH is closed, and H is integral in the classical sense that it represents an integral class. So, and that implies that both of these are closed. HB and HS are closed. And in some sense, they're both integral. But the class that this represents turns out to be 0. It turns out that this complex the complex K, the kernel of I star, is exact. So this is HB, so this is that HB, sorry, H is equal to HB, the body part, plus D of some beta, some 2-form beta, where beta is some 2-form on the supermanifold such that it lives in this kernel, which remember just means that pulling it back gives you 0. So setting theta is equal to 0 in beta gives you 0. Okay. So now, the question then that I had is, can we decompose G with curvature of G equal to H in a similar way? And the theorem is yes. Because this is integral and this is integral, there's a bundle germ G with this curvature, and there's a bundle germ GB on the body, totally in ordinary geometry, with this curvature. So here's the theorem. Given G on M, a supermanifold, G is equivalent to the pullback using P of some ordinary bundle germ on the body tensor is something that only depends on this choice of 2 form. And what this is doing, when I do this tensoring, this is just notation that means take these BIs defined on patches and shift them by adding theta to all of them. basically shift the connection two forms of your bundle germ by adding beta. Where, in this decomposition, GB is a bundle germ on MB with curvature equal to HB. And beta is a T-form such that d beta is equal to the sole part of your original curvature. Any questions? So what this theorem says is that on a supermanifold, if you're considering gerbs, most of the gerb is just contained on the body, but there's a two-form correction. So for these supergroups, we want to try to do the obvious thing. And just replace H by its supergeometry version. And I want to take G to be a simple, compact is more complicated, simply connected is a little more complicated. So I'm just going to take it to be a simple Lie supergroup. I'm going to do the easiest possible case and work over C. So does this work? So the first question is, all right, so what we need here is that we need omega Moyer-Cartan 1 form on G. That always exists. You always get the Moyer-Cartan. We need this supertrace pairing to be an add invariant pairing on the Lie algebra of G. This does not always exist. There are simple Lie superalgebras that don't have any add invariant pairing. So, and then we want to rescale. If this exists, we want to rescale so that H is integrable. And this, yeah, it almost works. It works, when this exists, it works with one exception. Actually, a large family of exceptions that all look very similar. So I'm almost out of time, but let me just give the result. So here's the Lie supergroup. Here's its body. And here's GB, the body of the basic germ on it. And in all cases, this beta, which is what I need to apply to the basic germ to get the germ on the Lie supergroup, has the same form. Beta is going to be the supertrace of the odd part of the more Huertan form with itself. So having beta, I can take this body and I get my bundle germs on the supergroup, uniform. But these GBs are different in each case. Okay, so results. SLM/N, comma C. That's a Lie supergroup, the supertraceless transformations. Well, that's the Berezinian determinant 1 transformations of CM/N. The body, well, this is the weirdest one in some ways. This is the hardest body to write down. It's a fiber product. 2 copies of GLM. It's all the matrices, pairs of matrices, with the same determinant. But the bundle germ is just the basic bundle germ on one factor, tensor, the basic bundle germ on the other factor. Dual. So when M and N are equal, this group has a quotient, and that quotient is simple again. Now the body is easy to write down, it's just SLN cross SLN. And the body of the bundle germ is again the tensor of the 2 factors with a dual on one. Alright, this pattern does start to break in the next example. OSP M/2N C. That has body SOM complex times SP 2N complex. All of these are complex. And the bundle germ is G on SOM squared tensor G on SP dual. So now I'm ready to talk about the exceptional cases. And here, this is the one case where not every one of these works. This is the one exception that I mentioned. This parameter for this exceptional family has to be rational for there to be an integral form. So then the body is just 3 copies of SL2C. And the bundle germ depends very strongly on this parameter. So it's SL2, the bundle germ on SL2 to the p kind times q power tensor SL2 to the negative P plus Q tensor, the same thing, the P and Q switch. And there are two more exceptionals. The exceptional Lie group G3 and the exceptional Lie supergroup F4, totally different than F4, the exceptional Lie. This has body G2 cross SL2, C. And this is body SO7, C, cross SL2, C. And the bundle germ in this case is G2.
What's the difference between G2 and SO7C?
SO7C?
Yeah.
They're totally different. Well, this is a subgroup of this, but.
Yeah, I know. And is it very different?
And what?
When you look at the details.
Well, for example, I'm going to write down the basic germ,
Yes.
and these powers are totally different in these two cases. For here, it's 4 and negative 3. For here, it's 3 and negative 2. All right. That's a lot of data. I apologize for dropping that all on you. But the point is that these basic bundle germs exist. You get these interesting numbers out of their classification. And so the next stage of this program is to do something with them, such as classifying brains inside of these supergroups using these geometric objects. Yeah, I think that's a good place to stop.
Any question? Yes, Brian?
For the D21 alpha case, the thing you wrote down is beautiful, the associated germ.
This one? Yeah, you like this, it's good. I like it too.
But, so would you think that for irrational, so the condition was that alpha was rational?
Alpha has to be rational for this germ to exist. So,
and that has to do with the existence of
it has to do with the integrality of that form. So I've written down all of the simple Lie supergroups that cats discovered have an ad invariant form. But then you have to rescale that form to see if you can make it integral, and you can only do that for this family if alpha is rational. And then these numbers come from the rescaling. But I can wildly speculate that for alpha irrational, there might be some kind of right. So in this whole story, the level has been an integer.
That might not be that might be like a square root or something.
This level?
Well, the SL2 germ. That's not necessarily an integer.
Right. So I do wonder if like the irrational alpha correspond to like fractional level. And now I wonder if perhaps perhaps this is already seen some fractional level. I don't know.
Any other question?
I don't know if this is a question. There's a hand next to focus on error.
But I think that's just the.
No, I think I can add a comment. I agree with your classifications, okay, and I can do the proof in one line. Actually.
Which one?
I can do your proof in one line. The proof of your theorem itself. The proof of your theorem you can done in one line, really. Okay. And actually, the fact that you're indeed looking at just at the body, it's very simple to see it. Okay. And indeed, actually, there are corrections. It's very easy to show. I mean, and I agree with your classification, but it's very easy to see it. Yeah.
With this classification.
Yeah, the body.
Okay, I'd be interested to see a more efficient.
Yeah. Maybe a half line.
Okay. Maybe one more.
Even better. Okay, I have a curiosity, very kind of question. Any insight or expectation about jerks in the holomorphic category, so on complex algebraic supermanifolds?
So
clearly the difference is that you cannot assume to have pi.
yes, you still, but for holomorphic supergroups, you still do get you still have P. So you still have some kind of body and soul decomposition. And I would honestly suspect that you can get all the same jerks. It's just that yeah, the connection data, the curvature data, that might not be holomorphic. Like to write down a holomorphic connection, just like for line bundles, holomorphic jerk connections are generally obstructed. So, yeah.
But there exists a holomorphic splitting?
There exists a holomorphic splitting, that's for sure.
For any smooth complex supermanifold.
For any holomorphic supermanifold, for any holomorphic super Lie group, because it's a Lie group.
But not for holomorphic.
Not for any holomorphic supermanifold. That's the big case where they don't exist. But when it's a Lie group, you know, it sort of.
It's is not basically.
Yes, exactly.
Any further question? Okay, so if there are no further questions, I will thank the speaker again. Thank you very much.
this is why my questions are what you add to this formulation. So I'm interested to see what you can go.
I think there is also invasion of systemic transformations. You can also study this. So, because if you have nice category, you can describe systemic transformations with change of organization. So there's relation.
Actually, in a small paper, the Castellano, so we were studying super qubits. Super qubits. Okay, so qubits are just a state 0 and 1. Right? So what is super qubits? Okay, so and you can sometimes so the problem is always either in zero states or with negative states. So there's no way to go unless you add as a hidden superalgebras in such a way to provide a way to do it. And those are intrinsically not inferred. Effectively, in the states they come because there you pair two Hilbert spaces which has a fermionic evolution, and then the tensor product gives you effective boson. We can think of this boson object, but indeed it's coming from the mind. So the fact that you have this subspace S to parameterize is intrinsically you see this string theory. It appears absurd. Of course, it's very intrinsically because you need the value. But the two-dimensional theory you can create in different way because you have the bosonization and fermion. So therefore, you can create fermions out of bosons. So string theory essentially it doesn't have the fermions, but the two fermions produce fermions, and then the Hilbert space produces exactly the bosons which are exactly kind of the fermion. I mean, the function, the computing function that we've done is perfect. So intrinsically, string theory does exactly that. Because you can start from a purely bosonic strings, still you can have fermions. Through the boson, you have to add chiral bosons. Once you have a chiral boson, then these chirals can create a fermion. Correct? And then the Hilbert space is the Hilbert space. Correct? And then in terms of this, you can build space fermions. Right. So if you have a chiral bosons, you create a fermion. I mean, a fermion means because you have to. This works at quantum function. It doesn't work at
D1 alpha has
double quantum operation.
but it can't be all. But it can't be normal.
Can't be normal. They're not like a chiral bosons. Which plays each of the chiral boson plays a role in the fermion. Once you have that, you strength because then you have the photon which allows you to introduce fermions.
Maybe the infinite dimensional ones.
Also, if for example, if you start from topological strings where there is no fermion, without any fermions, then you can create a fermion. I mean, a fermion which looks like a spinor even. Because the fermions are there, but then you can create fermions. There are ways of so maybe I can write to you.
That would be a drum.
So,
thank you. That's cool. Yes. Some of the things I was talking about the first time, so something really up here. Connections that sort of algorithms certain sections that are not I would say oh, okay. That's unknown. Yeah, this is another thing that there's some pressure. And that's, I think that's also cost. Yeah.
Natürlich nett. Also das ist ungemein. Mango-Suppe kommt bei Google, meinten Sie Mango-Suppe? Was? Das kennt man nicht. Mango-Suppe. Ja, aber das ist auch nur Spaß. Sie müssen auch mal mit Mango-Suppe. Ja, das schreibe ich dir. Aber nur das drin für Konsistenz. Genau. Aber man kann auch das durch Mehl oder Stärke. Ja, dann ist es eine Mehlsuppe. Du kannst dich einfach eine Suppe nehmen und ein bisschen Mango machen lassen. Oder Süßkartoffeln.
Hi Cyril, are you here?
Yes, I am. Can you hear me?
Keine Massensuppe.
Can you hear me?
Okay, so we're good to go, more or less. Guys?
First of all, sorry for that late.
So the last talk of this morning is Cyril Closset, who's going to speak about the U-plane of rank 1 4D n equal to KK theory. Thank you.
Thank you. Can you hear me well? Okay.
Yes, very well.
So thank you for the invitation to this nice conference. Yes, today I would like to report on this work that appeared in the summer with my student at Oxford, Oria Magoreanu, about indeed what we just said, the U-plane. So I will explain that in detail, but let me maybe take a step back and talk a bit about the motivation. We have a mostly mathematical audience today, I believe. But well, clearly this is a more physics talk among the others of the conference, but I'll try to make it interesting to various people. And please interrupt me to ask questions at any time. So there are essentially three strands all related to this talk. The first is about elementary Sieberwitten theory, the physicist version, which is the n equal to supersymmetric gauge field theory, essentially on their Coulomb branch. And we will consider so-called rank 1 Sieberwitten geometries and some of their interesting arithmetic properties. Those are like, I mean, the Sieberwitten geometries are well known from almost 30 years ago, but we will still explore some new aspects of them, which has to do with the global form of the favor symmetry group. So, in fact, I mean, it's a recurring theme in recent years in theoretical physics that until recently, even like 10 years ago when I was doing my PhD, often we would just, you know, when physicists would say SU2, they might mean, they really mean typically the Lie algebra, not the group, and so the group could be SU2 or SO3 and so on. But and in QFT, it makes sense because often at a first pass, you only consider local operators and then you only care about the Lie algebra, the Lie action on various fields. But for a more refined question that have been more and more explored in recent years, both by physicists and mathematicians, it's important to know which flavor symmetry group we are actually talking about. And so I'll discuss that in quite a few details in many examples. The motivation also comes from 5-dimensional physics and their embedding in string theory. So I will discuss that in the second part of the talk. And then a related question is about certain very interesting Calabi-Yotri algebras that comes from Curve representations and the category of Curve representations, which are related to these 5D superconformal field theories. So the plan of the talk is as follows. I will have a large preamble where I really do some detailed review of the pseudo-written solution for SQCD, and then introduce some additional formalism, discussing those theories in terms of rational elliptic surfaces and their sections. And using that, we will revisit the space of rank 1 supersymmetric field theories, as we will see. And from there, we will jump directly to 5D physics and what I will call 5D BBS quivers. So, as I said, we start with basics. That was those beautiful pair of papers from Seber and Witten in '94. So what did they do? They were interested in 4D n equal to supersymmetric gauge series, and in their first paper, and I mean in those two papers, and in this whole talk also, I will focus on just the simplest gauge theory, non-abelian gauge theory, which is an SU2 gauge group. And so we have n equal to supersymmetric vector multiplet, where on top of the gauge connection mu, we have some adjoint scalars and then some gaugino superpartners. And the scalar potential of this series include then this term in the vector in the scalar potential, such that you can diagonalize the adjoint scalar. And on top of the gauge group, we'll also introduce hypermultiplets, so-called flavors, in the fundamental of the gauge group, so that those are like the matter fields, like quarks and their partners, in the fundamental. So if we have NF fundamental quarks, I mean hypermultiplets, we would then have a flavor symmetry algebra, which is SO2NF. In the massless theory, I could also turn on generic masses. If all the masses are equal, I would have only UNF flavor symmetry, and in general, I would have U1 2DNF for generic masses. I have NF independent masses. And finally, asymptotic freedom in this gauge series implies that NF should be less or equal than 4. So in the limiting case, NF equal 4, the flavor symmetry is SO8, and the theory is actually superconformal. So the gauge coupling is exactly marginal. So we then go on to a generic vacuum of the theory, which is the so-called Coulomb branch. We can, as we said, diagonalize phi in this way. Then semi-classically, we have the X mechanism. SU2 is broken to U1. And the physical question then is, what is the low energy theory? Well, at the level of the, so we just said there is a U1 theory by the X mechanism, but then the details of the theory and their interaction with the various partners will be dictated mostly by supersymmetry, but there will be essentially an overall function here. For instance, like in the standard Maxwell term, there is a gauge coupling here, 1/g squared, which is then complexified to this parameter tau, which depends on where you are on the Coulomb branch. So this complexified gauge coupling, it's an holomorphic function of the Coulomb branch parameters, and by supersymmetry is actually the second derivative of the so-called prepotential of the theory. Then the Coulomb branch is parameterized by actually not A itself, which is not a well-defined concept beyond the semi-classical analysis, but by a gauge invariant parameter, which is the expectation values of a trace of I squared. So that's the gauge invariant operator. You take its VEF, that's called U. We see that semi-classically just A squared up to some sign and so on, which are just convention. But then there will be quantum corrections to this expectation value. But U then is just a complex plane at this level. And so that's my Coulomb branch is the so-called U plane. And we see already from this analysis that there is at least one important point, which is the point U equal infinity, which is the weak coupling point. At this point, this whole semi-classical analysis is valid. There's a one loop prepotential, and that's it. If you are at the generic point on the Coulomb branch, there is a further ambiguity in the low energy description, which is electromagnetic duality. So that's this very old story from the heavy side in the 19th century. We realize that if you write the Maxwell equation in a nicely covariant way, there is a complete symmetry by exchanging electric and magnetic potentials. And the same is true with supersymmetry. For the full vector multiplet, I can introduce the dual vector multiplet, dual photon, in particular dual field AD. So yeah, I should forget to mention I call that the wave of phi, but as usual, I also call A the small fluctuation around this wave. And so A and A dual will be literally scalars for U1 photons, for U1 vector multiplets. So we then have a relation between A and its dual and the dual photon A dual, which are just like this in terms of the pre-potential. So in fact, electromagnetic duality in terms of the low energy effective action is a Legendre transform. So okay, so then there is a duality group SL2Z with a standard basis in terms of generator S and T here, which acts on my two vectors A dual A in a standard way like this. And then the physical question is what happens well on the U plane. The point is there is an ambiguity. In principle, I could start at a point, choose an electromagnetic basis, go to a path, and then come back to this base point U0, and I get a dualized photon. So that can only happen if you take a path that goes through a singularity. So your path could go through infinity, then we understand very well what's happening from semi-classical physics. It's the so-called Witten effect. But more general SL2Z transformation can happen from strong coupling singularities. That is precisely which strong coupling singularities can appear was the physical fit and from the intuition of Seber and Witten that they determine in SQCD which singularities will appear. So in general, we will have some strong coupling singularities. Then you would have a monodromy, so you would have a U-plane with some puncture, and you would have a monodromy group of this U-plane. And well, there are basic conditions like the fact that if I go around all the paths, including the one at infinity, the product of all the monodromy should be in ET. And for SQCD, my key example here, I would have actually NF+2 singularities in the interior of the U-plane. And in the following, I will often think of the U-plane as just a projective line, but still with a distinguished point at infinity. So it's really just a plane. So the Seber-Witten solution goes as follows. So remember that we want to determine the effective gauge coupling, tau of A here. So tau of A must have an imaginary part which is positive, just because it's a kinetic term. And it transforms naturally under SL2Z. Tau of A itself will transform as a bilinear partial transformation. So one geometric object that transforms similarly, of course, is the modular parameter of an elliptic curve. And so we could postulate, as Seber-Witten did, that there exists such an auxiliary geometry, the Seber-Witten curve, or a one-parameter family of elliptic curves, really, over the U-plane. And if you have if you're given such a geometry, then you could declare that your gauge coupling is the modular parameter, so the ratio of the A and B period of the holomorphic one form on the elliptic curve. So such vibration are well studied, of course, mathematically by going all the way back to the Kodara classification of complex surfaces. We know that it necessarily has singular fibers. So physically, we know, as we said, the singularity at infinity, it will have a monodromy at infinity for SQCD, which is minus t to the 4 minus nf. So recall that t was this standard t transformation here, this t matrix. This is determined just by the one beta function of SQCD. So this is the so-called I star 4 minus nf in the Kodara classification of singularities of elliptic fibrations. We could have other so-called simple singularities, often called Seber-Witten singularities, which was what happened in pure SU2, for instance, which are I1 or more generally IN singularities. Those are the so-called multiplicative fibers of the Seber-Witten fibration. These are just t to the n monodromies, or in general, the monodromy matrix will be actually conjugate to t or t to the n. So physically, what happens is that you could have a single dion of charge, magnetic charge m and electric charge q, so dion of charge mq, which become massless at a given singularity on the Coulomb branch, at a given point on the Coulomb branch, and you get a singularity in the low energy physics. And then that's the monodromy, so just conjugate to t, as we said. So those are the standard, well, the standard story, but actually we know that there are slightly more interesting singularities that can appear from the quadratic classification, which will be monodromies which are of finite order. So those are T, so they are infinite order. But you also have these elliptic elements of SL to Z, like ST and S and their inverse. So there are 6 possibilities here, which are the so-called type 2, 3, 4, and 2 star, 3 star, 4 star in Kodaras classification. So for mass SQCD, this is the picture. So I write my U-plane here with always the point at infinity here, which is determined, as we said, by the beta function. And then you need to somehow guess or derive in one way or another what are the strong coupling singularities. So this is the famous solution for pure SU2. So NF equal 0, there are 2 singularities only, type I1, where a diane and a monopole and the Y1, 2 diane become massless, respectively. And you get slightly more complicated singularities when you have massless flavors. The global symmetries of this theory is as follows. So here, by global symmetry, by global symmetry group, by definition, we mean the group that acts effectively on gauge invariant states. So in particular, we have to quotient by gauge redundancies. So in the case of SQCD, then the group is SO2NF mod Z2. So the SO2NF is the one that rotates the 2NF half hypers, but there is a Z2, which is a gauge symmetry that just gives a sign to all the quarks. So then the global symmetry is, I can write the SO2NF minus Z2 like this. So of course, for NF equal 1, that's just SO2, so that's a U1, it's abelian. But for NF equal 2, for instance, it's SO4 mod Z2, which I can write also as SU2 mod Z2 times SU2 mod Z2. And similarly, for NF equal 3, it will be SU4 mod Z4, and for NF equal 4 is spin 8 mod Z2 Z2. Those are always actually the simply connected group modded by their center. So those are then the centerless groups. And finally, for pure SU2, NF equal 0, we don't have a flavor symmetry because there is no flavor, but we have a one-form symmetry, which is a Z2 symmetry that acts by a sign on the Wilson lines of the theory. So we would like to determine this. So this, of course, this is just classical, semi-classical physics because we have a UV Lagrangian. But we like to determine this directly from the infrared because that will then help us to generalize to theories which might not have a Lagrangian. So let me start with the partial answer. The partial answer, which well, you can justify in various ways, mostly from string theory, but I will not give actually a complete explanation in this talk. The partial answer is that if you consider first the flavor symmetry, the non-abelian part of the flavor symmetry algebra, just remove any U1 factors. It is given by the Kodaras singularities directly in the interior, by just assigning to each Kodaras singularities the corresponding Lie algebras as follows. So in particular, to IN, you associate an SUN symmetry. More interestingly, there is those exotic case 2 star, 3 star, and 4 star, to which you associate the Lie algebra E8, E7, and E6 respectively. And the I star singularities are SO. So in particular, I star 0, that was for instance for NF equal 4, the I star 0 here in the interior, you associate an SO8, as we said. For NF equal 3, that's SU4, sorry, and indeed it was SU4, and so on. This is SU2 times SU2 for I2 star. Okay, so that's part of the answer. But we will want to know the global form of the group and also how to see the abelian factors. So any question about this review of SQCD? Okay, so to go a bit further, we need to introduce slightly more explicit parametrization of the Seber-Witten geometry, and we'll do that as follows. So as we said, the Seber-Witten solution, the Seber-Witten geometry is just a one-parameter family of elliptic curves, and we can always then bring them to a standard Weierstrass normal form, which reads as follows in some local coordinate xy. So you'd have y squared equal 4x cubed minus g2x minus g3, when g2 and g3 are just polynomials or rational function, well, polynomials in all these examples of my parameter u, and also of the various masses. So for SQCD with generic masses, well, for any masses, really, it's a polynomial of order nf plus 2. And for generic masses, it will have nf plus 2 simple roots. And those simple roots are precisely, the discriminant here. So given the Weierstrass form, I can compute the discriminant delta, which is written here. And this is a polynomial. And so, yeah, you can look at this root and you can determine the type of singularities from that. Here I'm just giving, for SU2, the explicit form of the curve, that's the standard self-written curve, which has discriminant here. You see here there are two roots, u equal plus and minus 2 lambda squared. So from colorized classification of the singularities of elliptic fibration, we can then determine the singularities. Here, this is a standard table. So you just look at the order of vanishing of the discriminant at various points. You also need to look at the order of vanishing of the G2 and G3 function themselves. And that way you determine which type of fibers, which gives you the type of the conjugacy class of the monodrome is, and the associated flavor symmetry that we just mentioned. So from that you can also compute the period. In principle, you would have the geometric period. In principle, you have to integrate them with respect to u and to get the so-called physical period, which are my A dual and A, the physical fields. And again, in principle, you can compute those periods by solving a particular Picard-Fugge equation for any family. This is not how we are going to proceed today, although in many cases, if it's simple enough, for special parameter, you can do this computation explicitly. So let's then consider the full one-parameter family as here. So my elliptic curve E fibered over the Coulomb branch. I call B bar here. But as we said, it's really just a projective line with just the point at infinity, which we single out. But so if we look at elliptic fibration over pi1, then those are, by definition, rational elliptic surfaces. So we will assume that my elliptic fibration has a section, which is always the case in this, well, in today. So those are rational elliptic surfaces. They are very well studied mathematically. One nifty mathematical fact is that any such rational elliptic surface can be obtained by blowing up the projective plane P2 at 9 points. So it's what physicists often call del peso 9 or half K3 surface. And the deep fact is that rational elliptic surfaces have a homology lattice, so the lattice of two cycles with their intersection pairing, which is generated by the zero section of the elliptic fibration, the elliptic fiber itself, and then so-called horizontal sections, which form a E8 lattice. So in general, this geometry, the way I'm writing it in the Weierstrass normal form here, will actually have, so the total space, which we see as rational elliptic surfaces, the total space over U with fixed masses, so it's just a surface. It will have singularities which are canonical, AD type, in fact, in 2 dimension. Well, then we have a standard correspondence, as we said, which is very familiar in string theory between those AD singularities and the AD flavor algebras. So these AD singularities admit standard resolution, where you replace some singular fiber with a bunch of pi1s, which intersects, forming the Dynkin diagram, the extended Dynkin diagram, or the Dynkin diagram of the extended flavor symmetry, the corresponding extended Lie algebra. So for instance, here at the bottom, you have the E8 type, so the type 2 singularity, and you would resolve the singularity, you would get 8 pi1s that intersect in this way. Right. So where well, the extended node will really be the what we call θ0 here, which will be what we'll call the trivial fiber. Now, if you take then this elliptic curve at the generic point, remember also that the elliptic curves are additive groups. So in particular, well, so you can take a point on elliptic curve, add it, you get another point. You can do that all over the base, so you get a section. So there can exist non-trivial rational section of this elliptic fibration. So those are just solution of the Weierstrass equation, x of u, y of u, such that, well, x and u are rational function of u. And so those famously form a finitely generated abelian group, the Mordal-Val group, which by the Mordal-Val theorem is takes always this form. So there is, well, it's abelian, so there is just the so-called rank phi. Phi is my Mordal-Val group. I have rank phi generators of the free part, so that's by definition the rank. And then I could have also torsion elements, zk torsion. So there could be some element where I take k times the element. So k, for instance, the Z2 torsion, I would have one torsion section plus itself gives me back the trivial element, which is a zero section. In the xy coordinate, the zero section is just the point at infinity in x and y. So rational elliptic surfaces are fully classified by a paper by Persson in 1990, and followed by a paper of Miranda that checked the same result using slightly different methods. There are exactly 289 such surfaces, so it's a rather small set. They are fully determined by their set of allowed singular fibers, so you pick a bunch of fibers that could happen, and by the Mordal-Val group. In fact, in most cases, just choosing a set of singular fibers, which are allowed, determine the surface. And there are a few cases where you could have the same set of allowed singular fibers, but different surfaces, which are then determined, distinguished by distinct Mordal-Val groups. A basic global constraint is that if you sum the order of the vanishing of the singularities on the rational elliptic surface of the discriminant, you would always have 12. So you see directly that then there will be a finite set, and there are a few other slightly less, more involved constraints that tells you that only the following 12 Kodara singularities can actually appear. And then you need to combine those to get unallowed rational elliptic surfaces. And as I said, there are only 289 possibilities. So given that, we can revisit the story of SQCD and more generally rank 1 supersymmetric field theories.
Can you repeat? So this final number is when you have a fixed number of singularities.
When I have yes, sorry, say again.
What is the you have a fixed number of singularities. You have 3 singular fibers. So what is it? I mean, they come in families also. I mean, there's a lot more rational elliptic surfaces. Right?
No, actually, they come in.
I mean,
no, there are no rational elliptic surfaces with a section. The important thing is that they have a section, but those are there is a finite number. There are a few which come in one parameter family, actually one that I remember, but yeah, they are actually rigid in terms they have no complex structure moduli. So those are just the fibration over pi1. So you need to choose a bunch. I will give you some example, but you need to choose a bunch of singularities, right? For instance, let's say I would like to have 12. Well, there is a generic one which will be 12 I1 singularities. So I saturate this bound, and that's it. That's one rational elliptic surface. I could have one when I have a type 2 singularity and 10 type 1 singularities, for instance. And you can try and mix and match, but then there will be a few more constraints. And in the end, there are only 289 possibilities.
So the singular fibers, but they could still have parameters, right?
It depends what you mean by. Here I'm talking about as complex surface. As complex surface. So there are things that we would call Kähler parameter, maybe in string theory, or so you could move them. But as complex surface, most of them are unique. Yeah. All right. So indeed, there are parameters like precisely in physics the mass term that I will describe. But here I'm thinking in terms of as complex surface, then they are unique. So yeah, let's use this classification then to study the physics of rank 1 theories. So the basic idea in terms of this goes to an idea I think of Corsi and Ceccotti that we generalize in our paper with Oria. Which is to first fix what we mean by the UV supersymmetric quantum field theory by fixing the fiber at infinity. So in terms of rational elliptic surfaces, it's just a fibration over pi1, so I have a bunch of singularities. But here I say that physically I want to fix the point at infinity on the base pi1. So the U equal infinity on my U plane. So I will fix which singular fibers I have at infinity once and for all. That's what I will call F infinity. So that will, I claim that this defines which supersymmetric field theories I'm talking about. So for instance, if I fix I4 star, that's precisely pure SU2, the standard Sylor-Wheaton solution. And I3 star, it's SQCD and F equal 1, I2 star and SQCD and F equal 2, and so on, up to and F equal 4, I0 star. But I could pick some other singularities at infinity, and those are all the possibilities. I just said there are only 20 possibilities here for singularities we can choose from. So here what I'm doing is fixing one singularity at infinity, for instance, I1 at infinity, and counting on how many in the Pearson classification, how many surfaces do I have. Here I have 227. So this is a subset, of course, of the 289, such that I have at least one I1 singularities that then I can choose to put at infinity. Okay. And so we can see what are those singularities. Okay, so in red are what are those theories? Sorry. In red we have SQCD, and then we can see the number of what I will call Coulomb branch configurations. Those are the possible singularities in the interior. So there are 19, for instance, for an F equal 4 SQCD. There are those where we take type 2 star, 3 star, 4 star at infinity. Those are known, of course, and those are the so-called Argersilas theories that you can obtain, as we will review in a second, as particular limit of the SQCD with an F equal 1, 2, and 3 flavors. There are these other things on the left, which are when you have a type 2, 3, or 4 singularity at infinity. Those are the so-called Mina-Nemeshansky theories. So those are interacting superconformal field theories that do not have any simple embedding in terms of UV complete theory in 4 dimensions, but they do have an embedding in 5 dimensions, which will be what we discuss in the rest of the talk. So you can ask what happens in the first line here, where my singularity at infinity is so-called multiplicative fibers, type I1 to I9, and that's what I will explain later. Yeah, so that's what I said in words. I should mention that this table, it includes 7 superconformal field theories in 4 dimensions. So there's been a lot of effort in recent years to classify superconformal field theories. And in rank 1, there is classification now due to Argyres, Martin, and collaborators. It has about, depending on how you count, it has about 20 to 40 things. Here there are only 7s, but those are all the SCFTs in 4D that have a so-called trivial Coulomb branch. So here what I'm doing is considering only Coulomb branch where at low energy I only have a photon. There is a slightly more involved story where at low energy you could have hypermultiplets on the Coulomb branch, and that's something that I will not discuss today. Finally, you could have asked, what if I put I0 at infinity, meaning the trivial fiber? So that's a generic rational elliptic surface. The answer is that the physics of that is the so-called E string. So it's a theory in 6D, and probably I will discuss that a bit later. Okay, so given that, I can go back to my computation of the flavor symmetry group. I claimed above that the non-abelian part of the flavor symmetry was captured just by the type of Kodara singularities. The second claim is that you can also count the number of I1s in just looking at Sylor-Wheaton geometry by looking at the free sections. So if you look at the free part of the Mordell-Val group, if each free generator is a generator U1 flavor symmetry. So that then gives you the full flavor symmetry algebra. Yeah, so there is one generator for each free section and then one generator for each Kodara singularity. The rank of the flavor symmetry is given by 8 minus the rank of the flavor algebra that you would associate to the fiber at infinity. That's just a mathematical fact from rational elliptic surfaces. So for instance, for SU2 and F equal 1, we said that, let's show it again. And F equal 1, we had only I1 singularities here. This is this picture here. So this is a nice rational elliptic surface. It turns out that it has also a free section. So the Mordell-Val group is just Z. And so indeed, it's an abelian symmetry in this case. No, you can also compute the global form of the flavor symmetry group, and that's one of the results in our paper. By analyzing the full Mordal-Val group, including the torsion section. So for simplicity, let me consider the cases where I don't have abelian part. If GF is semi-simple, then let me consider G tilde F, which is the unique simply connected group, such that its Lie algebra is the curly GF associated to the quadratic fibers. Then I will define the subgroup of the full torsion part of the Mordal-Val group, which are all the torsion section which intersect the fiber, all the fiber in the interior trivially, meaning that it intersects the θ0 element, the one that you would get even before you resolve. So this means, this means that, in other words, torsion section that only intersects non-trivially the fiber at infinity. So that's Z1 here. And then we can, so that's a subgroup, obviously, of the torsion, of the Mordal-Val group, the torsion Mordal-Val group. And I can then consider the cokernel of the inclusion map of Z1 into phi torsion, which I denote by curly F. And the claim is that the flavor symmetry group is the simply connected group G tilde F mod F, this cokernel here. So that's the claim. The second claim is that the subgroup Z1 actually is the one-form symmetry of the theory determined by this fiber at infinity. We see that by definition here, this definition of Z1 does not care what exactly are the fiber at the interior. And indeed, I can vary the masses, and then the fiber in the interior can split and merge, but you fix the fiber at infinity once and for all. I'll give some example in a second. So to prove this above statement, that we won't have time today, but we can really borrow a lot of results from the F-theory literature. So the proof actually goes through local mirror symmetry. One complementary way to understand maybe this is by taking the Coulomb configuration with generic masses. Then if you take generic masses for a theory, then you would have only abelian symmetry. So you break this particular theory, the maximal flavor group that you would have, for instance, in the massless theory in SQCD, down to a U1, a bunch of U1s. But these U1s are generated by a bunch of sections, but there is a natural lattice associated to this section, the so-called Mordal-Val lattice that was introduced by Huerta in a series of papers in the early 90s. More precisely, in this case, what we care about is the so-called narrow Mordal-Val lattice. And there is, well, it's easy to argue from this local mirror symmetry picture that this Mordal-Val lattice, or the narrow Mordal-Val lattice, will be precisely the weight lattice of the flavor symmetry. So that's one way to compute it. There are several complementary ways to arrive at this claim here. All right, so let me give you an example of this. Again, in our standard vanilla SQCD. So if you have an F equal to 0, the several-written geometry is an I4 star I1, I1. So when I say 2I1, it's just two different I1 singularities. So it's I4 star I1, I1 rational elliptic surface. There is a unique such surface, and it has a Z2 Mordal-Val torsion. So that's in agreement with our claim here, because here in that case, Z1 equal phi torsion. And we know that NF equals 0, so pure SU2 has indeed a Z2 one-form symmetry. If I put, okay, the second NF equal 1, we said before, this is Z torsion, so it's just a U1. For NF equal 2, it's an I2 star at infinity and two I2s in the interior. There is, here we're looking at the massless curve again, the massless theory. So there is one such surface, and it has Z2 times Z2 Mordal-Val torsion. And that agrees again with our thing that we saw from the UV. It's SU2 times S2, mod Z2, Z2. Similarly, there is a Z4 torsion for NF equal 3, and a Z2 times Z2 torsion for NF equal 4. So that reproduces non-results. Actually, it's interesting that even this is well known in a sense, but we hadn't seen the claim about the global form of the flavor group for SQCDs, because if you look at the original papers, well, they would claim that they would say, for instance, that the flavor symmetry group of NF equal 4 is spin 8, and it's true in the sense that if you look at low energy excitation on the Coulomb branch, they transform non-trivially under spin 8. but those are dyons. So dyons are not gauge invariants. But if you look at gauge invariant states, such as captured by various indices like the Schur index and stuff like that, you would see that actually you get spin 8 mod Z2 Z2 confirming this claim. But as I said, this claim is obvious from the UV. So you can get less trivial results, I mean new results, by looking at those SEFTs. For instance, if I have the rational elliptic surfaces, which is 2 star, 2 stars, so I can put the 2 at infinity, the 2 star, for instance, at infinity, then this is the Argyros-Glass theories H0, and there is no flavor group. So in that case, there is nothing to talk about. There is no Mordavile torsion. If you put f equal infinity equal 2, we have the E8 Minaminsky theory. There is no torsion here. So again, the group is the full E8. Well, okay, E8 has no center anyway. But you can do the same for 3 star, 3 star. Then you get either the Argyros-Glass theory with SO3 with A1 flavor symmetry. But here there is a Z2 torsion, so it's actually SU2 mod Z2, so you get SO3 flavor symmetry. And similarly, if you pick the type 3 at infinity, you will get the E7, sorry, it's a typo, E7 Minaminsky theory, where the flavor symmetry is E7 mod Z2. So here we get a new claim about the Minaminsky theories. Well, actually, it was not new because we got scooped on that by Bardouage like a month or a couple of weeks before our paper. But he has a completely different way of computing those global form of the flavor symmetry group from class S, which of course agree with those results. Similarly, the result here for Argyros theories was also obtained by different methods. For the SO3 flavor symmetry by Buiken and Jiang a few months ago. And I believe the result here for the other Argyros theories with SU3 mod Z3 flavor symmetry was a new result. I don't know of any other way to obtain this result. All right, so that's one thing. Now, using the Pearson classification, we can also map out the full set of Coulomb range configurations. For instance, NF equal 3, SU2, we fix the I star 1 fiber at infinity, then you just list all the possibilities. In that case, there are 13. And you can check, of course, from the explicit form of the Sebovian geometry that you can obtain all of those by moving parameters around. An interesting ingredient in our analysis is that in many special cases, almost, I mean, it's almost a miracle in a way, but it's very useful in many cases, is that it might turn out that this U-plane is not just any elliptic vibration, but it's also called modular rational elliptic surfaces, which means that the U-plane is a modular curve. That means that I can obtain the U-plane as a quotient of the upper half plane by some modular subgroup of SL2Z. If that happens, then there is a map. I mean, there is always a map from the upper half plane, which is my gauge coupling, tau, to where I am on the Coulomb range, U of tau. But when the U-plane is modular, then this map is an isomorphism. Then the function U of tau, inverting the function tau of U, that we would ask physically, the function U of tau is then a so-called up module of the group gamma. When this happens, then the singularities on the U-plane are in one-to-one correspondence with cusp and elliptic point of the modular group. And so you can think of the celebrated geometry more as in a group theory setting, just in terms of modular groups. Even if I should mention that there is some nice paper by Atzmann, Feurer, and Manschott in the last year, where they consider this map from U to the upper half plane, even when the Coulomb range is not modular. And then you can still find a lot of interesting things thinking in that way. It's just that now you would have various branch cuts in this map instead of having an isomorphism, a bi-holomorphism. All right. That's an example of modular function. So it's for SQCD, again, it's known that for the massless curves, for NF different from 1, we have modular curves for NF equal 0, 2, and 3. So it's the standard gamma 04 curve for the Sebovian solution for pure SU2. But also it's slightly less known, but it was, I think, first shown by Nam in '96, that for NF equal 2 and NF equal 3, we also have a modular curve in the massless case. So we can then write my U-plane. Let's write the U-plane on the upper half plane using this. So for instance, this is standard pure SU2, right? So we have two singularities for the monopole and the diane. This is gamma 04 fundamental domain. So that's my U-plane on the upper half plane. And so you see that here you see literally you see with naked eyes the cusp of the gamma 04 at tau equals 0 and tau equals 2. You can check the map explicitly that corresponds to, of course, the monopole and diane singularities. Writing this U-plane in this way makes it more direct to, if you given if you can determine the fundamental domain, you can see directly which monodromies are associated with strong coupling singularities. Essentially, for instance, here, right, we know what is the monodromies around this cusp here because it's just the S transform of the point at infinity. So indeed, you conjugate T by S. Similarly, if you want to get the cusp for the diane here, the monodromy for this cusp here, it's a diane. You need to do T2 and then S like this. You can see with naked eye that you need to do this conjugation. So this often gives in more complicated theories, this gives a simple way to see the monodromies of the theory. Here is one slightly more complicated theory for SU2 and F equal 1. In that case, there are two configurations. One which is massless, or well, it could be the massless or the generic mass case. It's the same. It has 3 I1s. And there is one case when you sorry, you tune M1. You tune M1 to be in the strong coupling in this particular here, M equal lambda QCD essentially. Then in that case, the U-plane is actually modular. And this is a fundamental domain. It is modular for gamma 03. In that case, there is again a particular cusp here, but there is an elliptic point as well. This elliptic point corresponds to the type 2 singularity on the U-plane, and that corresponds to precisely the appearance of the Argyres point on the U-plane of SQCD with n equal 1, which is something that is known from the 90s, but it's a nice way to see it in this language of modular curves. All right. So with all this, I guess I have how much? 15 minutes left or 10 minutes left?
Yes, 10 minutes left.
10 minutes? Okay. So with all this, let me move on a bit faster, maybe to, well, some highlights from application to 5D physics. So by 5D, I mean the following. We can consider type 2A string theory. So shifting gear a little bit, we consider type 2A string theory on the R4 times some Calabi-Yau manifold. So of course, in general, I would have been low energy, which is in the far IR, it's a supergravity theory. But if my space X, my Calabi-Yau is non-compact, I would have just gravity decouples and have a quantum field theory. And it's a long sentence and dense, but there is many ways to engineer interesting gauge theories and superconformal field theories using this kind of picture. There is an interesting plot twist there that if you compactify type 2A on a non-compact Calabi-Yau, typically you actually do not get truly a well-defined 4D theory. What you always get will be a 5-dimensional theory. And the reason is just because type 2A is dual to M theory. So you can think in that way. I would have M theory on some Calabi-Yau times a circle. In type 2A, it just looks at the same Calabi-Yau on R4, but it's really then a 5D theory on the circle. So what we should really consider is M theory on the same Calabi-Yau. We will be interested in particular in canonical singularities, which are expected to always define a superconformal field theory in 5 dimensions. And then by taking the type 2A limit, so to speak, we are considering Kaluza-Klein theory, which is the 5D SCFT on a circle. Well, a 5D theory on a circle, 5D SCFT on a circle is just a 4D n equal 2 theory. It's just that it has this KK tower, so to speak. But apart from that, it looks very much like ordinary Sylor-Witten geometry like this, right? The standard thing. There are a few slight differences. Let me go through that quickly. So here I'm only interested in rank 1 theories. So that means that my Calabi-Yaus will have only will be a singularity which I can resolve with a single exceptional divisor. That will having a single exceptional divisor means rank 1 in this case, and that means that the exceptional divisor is a del Pezzo surface or a Fano surface. So I just blow down this Fano surface. I get a 5D SCFT in M theory from the fact that if I have a delta surface, the homology lattice naturally has a En structure, I can wrap M2 branes on 2 cycles, then it tells you that the SCFT actually has a En flavor symmetry, at least at the level of the algebra. So this is the famous 5D SCFT, first discovered by Seiberg in '96. They come then in this small family of 10, starting from E8, which is DP8, going down to E7, DP7, and so on. And I can essentially blow down the surfaces. And that corresponds to mass deformation from some E8 to E7 to E6 theory and so on.
Where is n coming from in this?
N
Little
in
n?
that case is the number of, it's a del Peso n, so it's a number of exceptional curve on a blown up P2. So I just have a Fano surface, which are either del Peso n, so it's a P2 blown up at n point, or it's F0, which is pi1 times pi1. So there are only 10 possibilities to have a positive canonical line bundle. Okay. So yeah, so in that case, n is just my del Peso n. It goes all the way. So the En series are like this. So En means E8, E7, E6, and then E5 is E5 is D5 and so on. E4 is A4. E3 is A2 times A1. And goes all the way to P2. Local P2 means it's a so-called E0 theory, which, well, that's it. We can think of this series, except for the E0, but all the starting at E1, we can think of all these series as some so-called UV limits of a 5-dimensional gauge theory. So 5D gauge theories with supersymmetry, or without supersymmetry for that matter, are never UV complete, right? It has because the gauge coupling is the inverse gauge coupling has dimension of mass, so there is a Landau pole kicking in right away. But you can embed those gauge theory precisely in those superconformal field theories here. So it corresponds to taking these En theories. There is a particular mass deformation that breaks En to SO2NF plus U1, which is the symmetry of just an SU2 with n fundamental. So in 5D, then you would have NF equal n minus 1 fundamental all the way to NF equals 7. Right. So in this gauge theory approximation, for simplicity, we can see what are the low energy scalar in 4D. So when I compactly find a circle, in 5D there is a real scalar, but then there is also the holonomy of the 5D gauge field on the circle. So it complexifies in the usual way. That will be my A. Now, because I come from 5D, I have additional gauge transformation, which shifts A by integers, which are just large gauge transformation over the circle. And so the gauge invariant parameters, instead of being like A squared in SQCD, you would get something slightly more complicated, which is just you need to exponentiate A, right? Because of the large gauge transformation. And there is still the SU2 Weil symmetry that send A to minus A. So this is the minimal gauge invariant combination. This is actually the semi-glacial expectation value of a Wilson line, supersymmetric Wilson line of the 5D gauge theory. And by definition, this expectation value is what I will call my parameter BQ. So that's my U-plane in 5D on a circle. And like in SQCD, there will be instantaneous correction to this statement, which are the so-called mirror map in string theory. And this is what you need to compute or determine in Sebovitan theory, like this. So you determine it if you can find a particular one-parameter family of curves. Those curves was determined first in a paper by Gaynor, Morrison, and Seiberg in a massless case, I believe. And with all the En mass parameter turned on, it was first written down by Egoshi and Sakai. Actually, mathematicians, including in particular Huerta, determine around the same time or slightly later this kind of rational elliptic surfaces. I mean, these particular En families for completely different reasons, and then they realize that physicists beat them to the punch for these families. So they also these En families also appear very naturally from the completely different arithmetic reasons in mathematics. So the Sebovitan geometry here, that as I said, is just a one-parameter family of curves, but you can also think of it as local mirror symmetry when you have a mirror threefold. But those mirror threefold are essentially elliptic curves. I mean, there is you can all the physics boil down to this elliptic curve. And so there will be the exact expression A of U that I mentioned before. So that just you invert this, right? A of U, and you have many corrections. So this is the mirror map in local mirror symmetry in type 2 string theory. Okay, so going back to my classification, Pearson classification, quickly, we said we wanted to interpret the line above here. Well, now the claim is that when you have the multiplicative fiber, sorry, ik at infinity, in at infinity, what you have is precisely if you have a I9 minus n at infinity, you will get an En 5D theory on the circle, a 5D SCFT on the circle. So that's the interpretation of this line above here. So you can see that explicitly by just looking the same way that in 4D, in SQCD, you would look at the beta function. It's kind of similar here. You look at the one loop prepotential of the 5D gauge theory with NF flavors. Now, instead of having logs like in the prepotential, the one loop prepotential in 4D, you get trilogs because you need to reach some KK modes. But apart from that, that's the same story. And then you can look at the large volume monodromy. And what you get is indeed T to the 9 minus n. So that's I9 minus n singularity. If you have generic masses, you have I1 at the interior, but again, now we can tune the masses and so on and see what's going on. There are a lot of interesting analysis to be done there that I will skip. One interesting thing is to look at the Mordal-Weil groups for all these surfaces, these rational elliptic surfaces associated to the 5D EN theories. They have non-trivial Mordal-Weil group, which are shown here. That will directly imply that the flavor symmetry is En mod the center, because in each case here it will be the center of En. So Z2 is the center of E7, Z3 is the center of E6, and so on. So that determines the global form of the En flavor symmetry group. Again, this was determined also a bit before our paper by this other group in Oxford using different arguments in M theory. Let's skip the rest. You can play various games when you go from 5D to 4D, for instance. That's just checking, well, known result, essentially. One interesting new thing that we elaborate on in the paper is, again, that in many cases, the massless curve for the EN theory is actually modular. So here is the list for the massless curve for E7 all the way to E0. So except for E8, E2, and E1 tilde, all the curves are modular, and that's the modular group here. So that's one example here for the E1 theory, which is essentially the strong coupling limit of SU2 in 5D. Here it has 3 cusps. So it's I1, I2, I1 singularities. In terms of the modular group is gamma 08, and that's the fundamental domain for gamma 08. And then you can read off what are the monopole, dions, and so on, and their monodromies just from this picture. Finally, I think I'm out of time, but maybe in 1 minute, I will mention another motivation of this work, which is BPS quivers. So an interesting question in any 4D theories is to compute the BPS spectrum. We can typically do that in 2 ways. So BPS spectrum meaning what are all the possible extramatic charges which are populated over a given point on the Coulomb branch. Okay, so one way to do that is to to first identify a larger category, which is called the BPS category, of all possible charges that could appear for any point on the Coulomb branch. And then at a given point on the Coulomb branch, you will have an additional stability condition. And so you would have some stable objects. So this is a standard F-term, D-term dichotomy in QFT, in supersymmetric QFT. In the case of our 5D theory in a circle, the corresponding BPS states can be seen in string theory as essentially wrapped M2 branes and so on a circle, and it will just become bound states of D0, D2, D4, which are captured by a DT invariant of some resolved singularity in type 2A. Then the BPS category is a derived category of current sheaves, essentially. Well, exactly. Compactly supported current sheaves. In many cases, this category can also be captured by a quiver, the so-called BPS quiver of the 5D theory in my language. It's more often known as a fractional brane quiver of the resolved singularity. So this will be a Jacobian algebra coming from a quiver and superpotential, such that the derived category of A module, where A is the Jacobian algebra, is precisely my BPS category. And in this case, it will also be the derived category of the corresponding singularity or resolved singularity. Okay. So in general, we want to then determine this quiver given a theory. So if you start from singularity, there are many techniques, especially in the toric case, but it's interesting to also compute it from the mirror, so from type 2B, in other words, from the Seymour-Eaton geometry. the basic idea is to look at the cusp in the case where, well, we can do that easily in the case when all the cusp, we have only cusp, no elliptic points. So in particular, well, if we have only IK singularities, let's say, then you conjecture that all the BPS spectrum is generated by the light states that become massless at those various cusps. So those will be the basis nodes of your quiver. So to each such cusp, you associate a node in a quiver, and then you compute the arrows of the quiver by looking at the direct pairing between these BPS states. So this is a very pedestrian method that you can do in many cases. It doesn't give you the superpotential though, so that's something we cannot do with current techniques. Anyway, in many cases, the one nice thing is that if you look at the U-plane, you're literally looking at the space of stability condition in mathematical language, and you can show that there exists actually a locus in which the quiver description actually exists, meaning that the central charges of all these BPS states, those light states, align exactly in this case. So to conclude with an example for my E1 theory here, you can look at there are three cusps, as we said, that correspond to Dian 1, 0, -1, 2, and 1, 2. Those are 4 nodes in the quiver. My 2 nodes, 1, 2 here. That's a block of 2 nodes that behave the same. And the direct pairing gives 2 arrows and 4 arrows. So that's a quiver, which is a well-known quiver for the so-called local F0 geometry. You can do other things, for instance, for the E8 quiver. There is a slightly more complicated rational elliptic surface of I1, I6, I3, I2. That's a particular configuration, tuning some masses. So those are the corresponding Dians. You can look at the electromagnetic pairing, and that's a quiver. In that case, you can also check that this is known also from B-brain configurations. So here we derive it from the mirror picture. And in that case, it's also interesting because you can remove one node of the E8 theory in 5D and go to the E8 Mina animation-ski theory in 4 dimensions, and that's again then a 4D quiver. So that concludes it. Sorry for going slightly over time. So to conclude, I revisited the general approach to rank 1 supersymmetric field theories in terms of rational elliptic surfaces, and we saw that there was a very nice classification that saves you a lot of work physically if you want to look at what are the Allot Coulomb range classifications. Using this geometric picture, we could determine the flavor symmetry group as not only the algebra, but the group of these theories. So we can also discuss many aspects of the Coulomb range physics. I only alluded to it very briefly, like Argyros-Douglas points on the Coulomb range and so on. And the key role was played by modularity in a very special value of the parameters. And finally, I discussed quiver points, but as I mentioned, there are many things that remains to be done, like computing superpotential in this language and so on. So this is all work in progress. So thank you for the attention.
Thank you very much. Any question from the audience? Right, so if there are no questions from the audience, I thank again the speaker. Thank you very much, Cyril.
Thank you.
For lunch, see you back at 3:30.
I had a question, Cyril. After the fact, it's okay. It's okay. Did you try to look at these quivers from the point of view of the spectral networks?
Sorry,
I mean, there's one way to derive. We study these quivers using what we call exponential networks several years ago. Did you try to look at this? Or?
No, I did not. It would be interesting to do. Actually, I discussed slightly, briefly at some point with Pietro Longhi about this. I mean, certainly there are interesting configurations on the Coulomb branch. What we can do by looking at the U-plane explicitly is that there are nice configurations, especially very symmetric ones, where you need in principle then to run the exponential spectral network algorithm to try to derive the quiver from that perspective, that would also give you this potential.
Because that actually that does include the superpotential.
Yes, exactly. Yeah, that would be very interesting. We haven't looked at it.
Thanks, nice talk. And yeah, because you mentioned, I mean, at the beginning you mentioned arithmetic properties of these curves. So by that you just mean the Mordau-Val group.
I just meant the Mordau-Val group, yeah.
Were you interested also in, like the location of these singularities and things like this? Or, I mean, are other arithmetic properties of these rationality surfaces?
No, I mean, there is indeed more that can be said about those familiar surfaces. I said there was this very interesting work of Huerta that somehow independently derived those what you call the multiplicative and additive EN exceptional families or something. So those are essentially the EN SCFTs in 5D and the E-string theory as well. And in that case, they have motivation that I myself don't fully understand about Galois group action on those families and so on. That I have no idea what would be the physical interpretation, but that would certainly be very interesting to look at.
Because actually, I mean, when I asked about other rationalistic surfaces, there's something called the Beauvais classification of rationalistic surfaces. Rationalistic surfaces with 4 singularities. And that has, I mean, one of them is this, the one that appears in the Apéry story, for example.
The what, sorry?
The Apéry story is the derivation of the rationality of the 3. So there is a rationalistic surface that, right? Because the Picard-Fuchs equation, coefficients that appear in the Apéry story are the coefficients of the solution of the Picard-Fuchs equation. This doesn't play a role for you.
I don't think so. I mean, yeah, we look at them as complex surfaces. Then we have, yeah. I mean, as I said, you can tune the mass, and then there is, you transition from one surface to the other. So that's like, morally speaking, changing Kähler parameters. But yeah, as complex geometries, those are like, I think they're unique. I mean, that was my understanding. Except there's one case which is not unique, which corresponds precisely to the rational gauge coupling, to the marginal gauge coupling for SU2 with Stock-Savers. Then there is a type 2 star, I0 star rational elliptic surface, which come in one parameter family. I probably misunderstood your question.
That's why I didn't ask it on the record. It's a question that you're supposed to discuss over lunch now, unfortunately.
Yeah, I'm sorry, I cannot be in person.
No, I know, I understand. I'm just saying, it's the kind of thing you're still, I mean, that's so missing when you have this hybrid thing. So nice you could make it. I mean, it's still good to have you here.
For the invitation, yeah. Next time in person, hopefully. All right.
Thank you.
See you. Bye.
Bye. Bye, Cyril.
That's the zoom.
Yeah. So that's like that one is that guy over there. Sorry. Like that camera.
Yeah.
It's basically what you see.
People watching.
I'm watching, Brian.
It's exciting, but I think it's better. But I think it's best to use this side.
Owen, do you hear us well? Particularly,
It's a little choppy.
Can you hear me clearly?
Yeah, I can hear you clearly.
Good, because Brian is mic'd, so he should be clearer.
Yeah, exactly. Like top.
But don't go outside.
Yeah, also play in the video. We're ready, so we'll go ahead and start the afternoon session. We're very, very happy to have Brian Williams, visiting from Edinburgh. And he's going to tell us about what I understand is the simplest way to write twisted 11-dimensional supergravity. So take it away.
So the title is a play on words from a talk earlier this week. It's different from the one on the website. But yeah, thanks for inviting me to speak, and to the organizers for a great conference so far. Long overdue. Having a really good time. Yeah, so today I'm going to talk about 11D supergravity, but a simplified version of it, which is twisted in the supersymmetric sense. So I believe in Richard Egger's talk yesterday, he introduced this notion of twisted supergravity. And if you came to the extracurricular talk in the afternoon yesterday, you might have heard a bit about this as well. But I'll just remind you the slogan, which is it's supergravity in a background where the bosonic ghost. So this is a ghost for some fermionic symmetry. Takes a non-zero value. So I should list a lot of really great people who have been working on this. So first I should say this was introduced by Kevin Costello and C. Lee, this notion of twisted supergravity, which is compatible with the usual notion of twisting in, say, supersymmetric gauge theories. They also sort of use this perspective to do a lot of really cool stuff. So what they did was they gave conjectural descriptions of a lot of supergravity theories that you would care about in 10 dimensions. And I'll actually recall some of this in the middle of my talk because it'll be important. And there's a lot of really, really great work of people like Kevin and C, and also Natalie Piquet, Davide Gaiotto, and many, many others who I won't name all right now because I'll probably leave a lot of people out, that are using this to study twisted versions of gauge gravity dualities like holography and ADS-CFT. It's one of my main reasons for caring about twisted supergravity is to try to make concrete mathematical statements of these much simpler phenomena after you twist. But my goal for today's talk is to not get to any of that stuff, but is to sort of address a version of twisted supergravity that doesn't fit into Costello and Lee's description, which is 11-dimensional supergravity. So my goal is to formulate interacting models. An interacting model of 11D twisted supergravity. Okay, cool. So to begin my talk, I'm going to start with some objects that you'll find familiar from Martin's talk. And it was how Ingmar and I got at least the, not the interacting version of this 11D twisted supergravity, but just the free limit. And this goes through the world of pure spinors. So great. So right now, I'll work pretty generally. So here G is just going to be a supersymmetry algebra. Any dimension, any number of supersymmetries you care about. And Y is going to be the corresponding nilpotence variety. So these are going to be all of the X inside of the odd part of the supersymmetry algebra, which self-commute, anti-commute. So this is called the nilpotence variety, studied by many people in this audience. Ingmar, Johannes, Richard Eger wrote a really beautiful paper, connected it to a lot of really cool things in supersymmetric field theories.
And G's the usual thing.
G is the supersymmetry algebra, yeah. Is that what you mean by usual? Yeah, so super Poincare algebra.
So X is what? Is a generator of the algebra? Is an element of the algebra? Is a coordinate? Is what? Sorry.
So this is a super Lie algebra.
No, but the X there. X belongs to G.
It's an element of the odd part of this algebra.
So it's a generator. So it's
a
charge, Q.
Sure.
Okay, fine.
So there's a really cool machine called the pure spinor formalism, which takes in very geometric looking objects. So this is a nice sort of variety, and you can study modules for functions on this, or sheaves on this variety. And there's a very beautiful machine which, out of such geometric object, spits out a supersymmetric multiplet. And maybe for lack of a better term, I usually just refer to this as the pure spinor formalism. So I'm not going to be directly concerned with this construction here in this talk. What I'm really going to be doing is a simpler version, so a twisted version of this. So maybe we know how to twist a supersymmetric field theory. So there's this idea of twisting. At least in the case of supergravity, it might have been more familiar to you in the case of just ordinary supersymmetric field theory. There's a notion of twisting to get at these sort of twisted multiplets. Maybe the most famous example is the twist of supersymmetric gauge theory in 10 dimensions. Its twist has a beautiful description called holomorphic Chern-Simons theory. This is due to Laurent at first, I believe, in this audience. Maybe he's here today. That's my favorite example of this twisting construction. But it turns out there's a twisted version of this geometric construction involving the pure spinor formalism that also spits out these twisted multiplets in a way that I think is a lot more geometric. and actually a lot simpler. So, there's an object over here which also takes as input some geometric data, but now corresponding to a different variety called YQ. So here, Q everywhere here is a fixed twisting parameter, so Q is really an element of Y, just a point in this variety. It's a twisting supercharge because it squares to 0. And out of this, you can build a variety called Y of Q and study its modules, its sheaves. And it turns out there's a version of this pure spinor formalism that makes this whole diagram cute. And the advantage of this is Y of Q is a much easier object to understand, I believe, than this construction over here. So I'll tell you what Y of Q is.
So can I understand? I mean, so what is the difference between Y and YQ? So what is the main difference? So Y, I mean, if I understand it, X is one charge, one supersymmetry charge. You choose one supersymmetry charge, and then you find the pure spinor constraints because of the nilpotence of the charge. Okay. So what is the difference now with this Q of Y? It's the same object.
I'm going to define it.
Okay.
And I hope the definition is, yeah, let me define it. Okay, so before Y of Q, what I'm going to do is define a different Lee algebra. So given any Q, I can look at something called G. G of Q, well, what's the point of this twisting supercharge? Well, I can take my original Lie algebra, G. Another way of phrasing what the data of Q is it's the data of a Mark-Hartan element inside of G. So what that allows me to do is deform this super Lie algebra into a DG Lie algebra. So if you were to think in terms of the supersymmetric field theory and the twisting construction there, G is a symmetry of the original untwisted theory. Because the theory is supersymmetric, this is what the definition is. This object here, this DG Lie algebra, or I'm going to even do something simpler, I'm going to actually take its cohomology. This cohomology is going to be a symmetry of the twisted supersymmetric field theory. So it's the Q cohomology of the supersymmetry algebra.
And where are the fields?
No fields yet, this is just an algebra.
So you define your states, the universe space, as the element annihilated by Q. Okay, this is the usual procedure of twisting. Okay.
And you mod out by Q exact things, but yeah.
Yeah, okay. Yeah, because it's an input in the operator, you can do it.
There's still no Hilbert space. There's still no Hilbert space.
And how many twisted
generators?
generators?
Yes. Okay.
No, there's
how many twisted generators do you have in mind?
One.
This is a fixed Q.
Yes.
Q is fixed. Now taking its
nilpotent, right?
Yeah, exactly.
And, and there are other ones, I guess. And
yeah, so there's a nice classification of all such Q. They're filtered in a nice way, and I'll get to that in a second for 11-dimensional at least. Yeah. So far, this is very general. Nothing is about 11 dimensions. Nothing is about tautological twists or holomorphic twists. It's all general.
Can I ask you something probably very naive? So, is there any category on the right-hand side of that the diagrams? Like, is there a category of multiplets?
Yeah, for sure. You can put a lot of adjectives on that side. So maybe you just want sort of a bare bones multiplet. Maybe you want a field theory. For me, a field theory is a multiplet equipped with some action functional.
Okay.
You may want to put those sorts of adjectives in. But depending on what you want to tweak on the right-hand side, there's a corresponding thing you can tweak on the left-hand side. I'm being sort of vague about what I mean there.
So I need to bother you. So the Q is there, which is it is just a linear combination of the supersymmetry algebra, of the supersymmetry charges of the 11 dimension. So the pure spinor constraint is the usual lambda gamma lambda is equal to
absolutely, yeah.
That's it. Okay.
Yeah.
So this is the BRST done by Bertels for 11 dimensional superparticle.
There are two things that are happening. There's the thing which is above called X, which is any point in this space of square zero things.
What of?
Any point in this space of Spinors satisfying this constraint, if you want. So there's that whole space.
It's an element of the cone, yes.
You also choose a point. So Q is a specific point on that.
So the lambda are not dynamical, so fix the ones for all. Which are solution of Spinors.
The lambdas are still there, but you have also separately fixed a supercharge. That's what's being called Q.
Okay, so there is another charge with respect to X. So there are two charges, X and Q.
X is just a variable.
X is like a lambda, if you want. Martin would call X lambda.
Okay, so X, the Daniel was not a charger. When I asked before, what X is a charger, he says it is a charge. This is not a charge. X is an element of what?
This is called set theoretic notation, so it just means all X that are in the odd element of the...
But G is, you say the G is odd. I mean, the G is an odd element of the algebra.
G odd.
You can obtain it by contracting the Q with...
Write X as lambda, gamma lambda.
X is a charge.
Is that right?
So I wouldn't...
That I understood that. It's clear, okay. So the lambdas, the Spinors, XA are the Q charges. The supersymmetry charges, X alpha.
I don't understand the confusion, so maybe I'll let someone...
I think we can maybe move on for now.
So y of q is exactly the same definition. So y of q so it's the
Looking at the space of this charge.
There's a question of why. So Owen asks whether you take cohomology or whether you mean the chain outlines.
I mean cohomology, yeah. I mean cohomology. Most of these algebras are formal, so you're not losing much. There are some examples where it's not formal. But let me take cohomology.
So you fix a point in the Spinors, you just fix one Spinors, which is not okay. I understood that. Okay.
Can we go on?
I completely understood that. I'm going to understand.
Okay. This is all general. This is this object y of q. So it's the twisted nilpotence variety. This is the thing I want to call it. And out of this object, or rather, sheaves on this object, you can produce multiples in the twisted sense. So for instance, let me do an example.
Just odd, right?
What's that?
Just odd.
Thanks. So yeah, just odd. So I'll do an example of, so say G is the 11D supersymmetry algebra. I wanted to do this computation, but I don't have time. You can compute the cohomology. Sorry, I call it just G sub Q. So the cohomology with respect to Q. This is, let me just write it again. Of this DG Lie algebra. So this is the Q twist of the 11-dimensional supersymmetry algebra. And you get out something quite nice. So there's an odd part to this. So the odd part looks like, so let me say a few, let me preempt this a little bit. So here, just some geometric data. So Q is going to be a square zero supercharge. So Q is going to be in the original nilpotence variety. And they basically split up into two kinds. So there's sort of a minimal one. And there's, let me just call it non-minimal. You can call it maximal if you want. There's essentially two different flavors of Q here. So this is the stratification I was mentioning earlier. Not all the Qs inside of the nilpotence variety are equal. The distinguishing feature for me right now is going to be minimal and non-minimal. What minimal means is that the dimension of bracketing with Q, so this is going to be an element in the even part of the super translation algebra. And minimal means that this is 6-dimensional. Non-minimal means that this is 9-dimensional.
Do you need Q squared to be equal to 0 to do all that?
Sorry, what?
Do you mean that the square of Q is 0?
Yeah, so that's part of this condition here. So if it's in Y, it's automatically square 0.
Because for this model, which is supergravity in 11 dimensions,
that's right.
We don't know how to build such an object.
You don't know how to?
We don't know, no one knows how to build such an object, such that Q squared is equal to 0. Or except if you use, maybe you use the Vatelin-Vilkovsky formalism with antifields.
Everything for me is going to be in the PV formalism, yeah. I'll get to that in a minute.
But it's maybe important to emphasize that this Q is a supercharge. It's an element of a Lie algebra, so there's no problem building it.
This is just algebra. This is just algebra. There's no fields here. This is just algebra. Sorry, so there's this classification. I'm going to focus most of my talk on this minimal case here. So Richard Eger yesterday talked about the non-minimal case. His talk was about this Q. My talk is mostly going to be about this Q, the minimal one.
And he wrote down 2 varieties, like for the minimal and non-minimal cases, like 2 orthogonal or Grassmannian or something.
That was I'm not going to get an orthogonal one, but yeah.
Okay. So
I'll say what the one is, yeah. Okay. So I'm gonna just do the minimal one. If I don't say so, just assume Q is minimal for me. And this cohomology is going to be this result here is about the minimal Q.
So in the non-minimal case, why Q is a point?
In the non-minimal case, what? What did you say?
Why Q is a point?
Okay.
So there's some odd stuff, which is going to look like wedge 2 of, I need to introduce notation. So in the minimal case, such a Q determines an isotropic inside of R11. Really everything for me is going to be complexified. I'm not going to ever care about reality conditions. So such a Q fixes an isotropic inside of C11. So I'm going to fix that notation here. So this thing, L, I'm going to think about just as the fundamental representation for SL5. And this cohomology I'm going to decompose as an SL5 object. So on one hand, I have wedge 2 of the dual sitting in odd degree. This is actually all the odd stuff that's left over after you do this Q cohomology. And then in even degree, I have a copy of L. So you should think about these as the surviving translations, bosonic translations. I said the image of Q is 6-dimensional, so the surviving translations, no surprise, is 5-dimensional. And then there's a stabilizer part as well that I won't write down, but there's also a stabilizer of Q. So sitting inside of here is, for instance, SL5. So I won't write down that stabilizer. But that's the other part of the, so G for me was the super Poincare algebra. Okay. So that was just the cohomology. But I claim if you were paying attention in Martin's talk, you probably recognize this thing. So let me call an element here just generically psi. I'll call an element here just generically v. So there's a bracket here. There's a bracket here which is between 2 psi's. And that gives me, well, what I can do, I can wedge them together. So that's wedge 2 of the fundamental, wedge 2 of the fundamental, this is in wedge 4 of the fundamental. but of the anti-fundamental, but that's the same as the fundamental because I'm in SL5. So this is that's an element of V type. So there's an odd, odd, even bracket. But then Y of Q is at least it's the cone over GR25. Very nice variety.
And L, wait, L is this image? L.
This copy of L. So think about that as like translations that are holomorphic now.
And how many psi do you have?
Wedge 2 of L, so this is like the size of translation variant 2 forms on C5.
10. 10.
I won't do any more examples because I need to move on to what my talk's about. So this pure spinor formalism, this now twisted pure spinor formalism, I should say. But now applied to the free pure spinor action. So I'm going to do the ordinary, I'm going to do what's very similar to ordinary pure spinor formalism, but I'm just going to look at an abelian theory, non-interacting theory. So I'm looking at something just like psi, maybe Q is a bad word, d psi. So psi here is like a pure spinor field, now associated to this GR25, and I'm going to run this pure spinor formalism, which I won't say much about. But this spits out an 11-dimensional multiplet, twisted multiplet. And this is going to be my ansatz for twisted 11-dimensional supergravity. So twisted now by the minimal Q. There's a version of the non-minimal Q.
Does it mean that if you take the gravity known 11 dimension?
If I take the gravity, then?
In gravity in 11 dimension, you introduce SL5 indices, M and N bar.
Yeah,
from 1 to 5.
That's right.
Makes 10, and you have another one for the 11th dimension. Because you have to write 32 components.
Yeah.
Your spinor is a one form. One form is trivial. But the spinor indices, you have to write 32 components, and then you use SL5 to write this.
Yeah, so the psi here is it's an element of functions on, how should I say this?
I mean, holomorphic and anti-holomorphic.
Yeah, exactly. Yeah.
And then you will get 16 and multiply by 2.
Oh, I can't really follow from. I'm just gonna
No, that's what you do. That's what you do. You use so-called vector indices for the spinor indices, right?
Yes.
Using SL5 notation.
So as an SL5 representation, the spinor is the total exterior algebra over C5.
Yes.
Then you find that the 0, 1, and 2 powers are exact. The 4 and 5 are not closed, but the third one survives in cohomology. And then after a dualization, this is what Brian wrote.
And guess one has to do something similar for the 3 form. I have no idea of how to do it.
The 3 form is going to be here. The 3 form is going to be here.
This contains all of it.
This contains everything, yeah.
It contains everything.
So I'm gonna write down this twisted multiplet. Engwer and I computed this in a recent paper. And it looks very similar to the complex that Martin Rotana has taught. So I'm going to write down, it's an 11-dimensional thing. By multiplet, I really mean a local object now in 11 dimensions. It's going to look like it's going to be living over some 11-dimensional space. So what it looks like is the following. So let me set up some notation here. So this theory had 6 invariant directions. That means it's holomorphic still in a remaining 5 directions. So I'm always going to be choosing a splitting like this of my 11-dimensional manifold. Okay. And I'm going to have some sort of complex geometric notation. So for instance, I'm going to use this Dolbeau forms on C5. Hopefully everyone's okay with this. So these are sections of the C infinity sections on C5 of all the exterior powers of the anti-holomorphic tangent bundle, cotangent bundle. And then my notation for, I'm going to have this notation that looks like omega 1 comma star as well on C5. So if this thing resolves holomorphic functions on C5, this thing resolves holomorphic 1 forms on C5. Holomorphic 1 forms. But as a cochain complex, it contains all of the Dolbeau degrees. I always remember all the Dolbeau degrees. And also holomorphic vector fields are going to appear. So my shorthand for holomorphic vector fields is this polyvector field notation. So PV1 C5, it's a first power of the tangent bundle. That means a vector field. So this resolves holomorphic vector fields. And that's it. That's all I want to write. Okay. So all the fields are going to live in things that look like this. So one copy of the fields looks like PV1, comma star on C5. Well, that doesn't live on C5 cross R, but I can tensor this with sections, the de Rham complex of R. So now that's genuinely a local object on C5 cross R. So that implicitly everywhere, by the way, I have the del bar operator acting here. And I have the de Rham operator, I'll just call it D de Rham acting here. So when I say odd here, I mean the lowest component of this. This is a superfield. PV1 comma star contains Dolbeau things in all degrees. It's a superfield. This also has things in omega 0 and omega 1. This is a superfield. When I say odd here, I mean the lowest component is odd. So that means a vector field, a holomorphic vector field is odd. That's not crazy. Holomorphic vector field is my version of the ghost. It's the infinitesimal translation. So that better be odd. That better be a ghost. And then in the shifted even degree, I have PV0 star C5 tensor de Rham on R. And again, the same linear parts of the BRST differentials, del bar and D de Rham, act on this. But there's also a connecting map here, which now uses this SL5 structure. So this is the divergence. I'll write this as D sub omega. So this is the holomorphic divergence. So given any vector field on C5, I can take its divergence with respect to the standard holomorphic volume form on C5. And that was actually fixed in the beginning because I wrote everything as an SL5 representation. So I had this volume form in mind the whole time. So that's part of the fields. There's basically a copy sort of dual to this. So now I look at just Dolbeau forms on C5. This is the thing that resolves holomorphic functions, tensor de Rham forms on R. Then I can look at one comma star forms on C5, tensor de Rham forms on R. And this is just the holomorphic de Rham differential. Okay. So the claim is that this is the free limit of 11D twisted supergravity. We just started with this free action upstairs. So I'm going to read off some fields here and try to connect with maybe some fields you would expect to see. If you would all believe me that this is the twist of 11D supergravity.
I have a technical question. You start from a first order action.
It's just first order, yeah.
Here. And then, as we know in The dependence on the...
Sorry, it's not a first order action, it's quadratic. It's psi d psi.
Yeah, psi.
It's like a Chern-Simons.
So how do you get the square of the curvature of the three form, which has two derivatives?
Those are all exact.
Those are going to be rendered trivial after you twist.
Trivial?
Yeah. They're going to be Q exact. Exact for the holomorphic supercharge. This minimal supercharge kills those types of terms. So you're right. The linear part, this is just a free theory. It just involves first order differential operators.
And how do they get squared?
They do not. They do not.
It's the same as in holomorphic.
It's like holomorphic Chern-Simons. It's like holomorphic Chern-Simons. Yeah. Yeah, so let me read off some components because I think that might be useful for the crowd. So let's look at one of these mu type fields. So there's a mu type field which is like mu. You got some coordinates here. So top coordinate j bar, lower coordinate I. So dz bar, j bar. That's an anti-holomorphic one form. And then I can also contract this with a holomorphic vector field. So this is like a Beltrami differential. And because I said the lowest component was odd, this thing's an even field. And it's a component of the metric that survives. So because I'm using, it's SL5, I can use a Kähler structure. You can identify this with really a component of the metric in the untwisted theory. Okay. Then I have a lot of fields like this. So I have beta I bar, J bar, K bar. This is DZ bar. I won't say all this. Everyone see this field up there? So, oh, sorry. I should have named these things. So I tend to call this thing mu. I tend to call this thing beta. Just the superfield. So there's a ton of fields in each of these because they're graded. So I'll call this superfield mu, this superfield beta. This superfield I call mu. This superfield I call gamma. So beta here, it doesn't have any holomorphic one-form directions because it's a zero-star form, but it can have three anti-holomorphic. You could also have this topological direction, but let me write that down. Then we could also have something like gamma I, j bar, k bar. So gamma has one holomorphic form now. So it's like dz I, dz bar, j bar, dz bar, k bar. And I have a ton more of these. And if we count, because of my shifts, these fields are also all even in my twisted theory. They're all even. They're not ghost type. They're not odd. And these are components of the C field. Of the supergravity C field. So not all components of the C field survive. I bet you can't find a holomorphic 3 form around. Only some do, but there's a lot of them that do. Okay. And I want to also say that this is totally within the BV formalism. So all of the ghosts, all of the antifields, they're all here. They're all here in this complex. You could sort of see that in the beginning. I mentioned there's odd stuff here that just looks like a vector field along C5. That's part of the ghost that survived this twisted theory for infinitesimal diffeomorphisms.
What about the other one, nu? The last one?
The last one here.
Right. Nu, there.
The nu?
Right.
What about it?
You didn't write down the formulas.
You
write nu, beta, and gamma. What about nu?
Yeah, it has anti-holomorphic dependence. Personally, I can't tell you where it comes from in the supergravity theory right now.
For example, there will be parts of nu which, because they impose equations on things like this mu, will come from antifields in the untwisted theory.
Yeah. There's also potentially ghost stuff coming. Yeah.
For instance, why don't you have you have this 3 form here? Why don't you have a 2 form or 4 form and all that?
They're also
They're also there, right? These are superfields. They have all low directions.
So you mean that in the bosonic sector you will have all kinds of forms?
All kinds of forms,
with M or M bar indices.
Exactly, yeah.
But not every.
And how do they go away?
But not every, right? Because I only have holomorphic 0 forms and holomorphic 1 forms here. There's no holomorphic 2 forms around. I could also have any form degree in the topological direction.
So when you keep this, at the end of the day, I guess the only guy who should stay is the 3 form. So what happened to the 2 form that you may have as well as the 3 form?
Like the 2 form ghost.
That's a ghost.
It's there, right? It's being implemented. I'm even writing down the gauge symmetries here. This is like the linear BRST complex.
I'm talking about fields with ghost number 0.
There's a 2 form.
The reason why you don't have a 2 form.
I didn't know there was a field ghost number 0, 2 form in supergravity.
No, there is not. But here, why not? Since you can get everything.
You can't have a 2 form that's even. So I said the lowest component here is odd. So that is 0, 0, tensor 0 is odd. Therefore, the grading is just internal here. So it carries the usual sort of supergrading on Dolbeau forms and supergrading on de Rham forms. So any even form is also going to be odd.
How do you collect? You're listing some fields, but you get actually a number of supermultiplets.
The object written on the upper board is 1 supermultiplet, and it's the one that you know about. It's just the output of the.
It's 1. These fields in 1 multiplet.
Psi is the scalar supermultiplet. And out of the scalar, you get this complex.
Yeah, but I mean under this G of Q or whatever you call it.
It's just a scalar on that G of Q guy. Yeah, it's a scalar superfield on that G of Q. And out of that, you get this whole thing. Yeah.
So this is the one that looks like 1551. But he's taken the Dolbeau resolution of the holomorphic stuff. Because you have only holomorphic X's, right?
Oh, I see.
Okay. So I wanted to get to one of the punchlines of my talk. Well, I actually wanted to write down the action. So I just wrote down a free theory. I'm now going to propose an interacting version of this theory. So interactions. So let me just write down the action. So I'll write down the free action just to get you acclimated to. Oh, I erased that. Okay. Let me just write down the action. I should have not erased that. So remember, maybe whatever. So mu is PV1, comma star, tensor de Rham. Mu is PV0, comma star, tensor de Rham. Beta is an omega 0, comma star, tensor de Rham. And then gamma is an omega 1, comma star, tensor de Rham. And these things should have been parity shifted because their lowest components are ghosts. So let me just keep track of parity that way. So I'm going to write down the action. So the free action should look familiar if my linear BRST complex made any sense. So it looks like gamma del bar plus d de Rham mu. So that's that internal differential that I wasn't writing down. There's that internal gauge transformation, linear gauge transformations, which just tells you that the mu's and the gammas are holomorphic linearly on the shell, and that the mu's and the gammas are locally constant in the R direction, as any topological theory would be. And there's the same formula for the mu's and the betas. Mu, like that. But then there's that external differential that I explicitly wrote down, so that involves this divergence operator. So there's a term like beta d omega mu. as well. So if you like, this is imposing the constraint. It's a BF type theory so far. It's imposing the constraint that mu be divergence free. That's what this last term is doing. So that was the linear theory. So now I'm going to write down the interesting bit. So there's basically two types of terms. There's one term that looks like this. So it involves a power series in the field mu. It's quadratic in mu. And then there's a single gamma. And it's hit by a holomorphic derivative here. So what does this make sense? Let me just keep track of the holomorphic form. So gamma is a holomorphic 1 form. D gamma is a holomorphic 2 form. Mu is a vector field, so mu squared is a 2 vector field, a polyvector 2 field, so I can pair these together. That's an SL5 invariant thing to do. Then mu is just a function, and you just power series expand this until you can't do it anymore. So it's like a formal power series.
And the integral is done on M5.
Oh, I'm sorry. Yeah, thanks. So all these integrals are over C5 cross R, just a local Lagrangian. It's a Lagrangian on this. Yeah.
6 dimension.
Yeah.
Well, 11 dimensions.
11 dimensions, yeah. Yeah, thanks. That's not the only term. We're missing out on a very important term that, this is my favorite term. So it involves 3 gammas and just holomorphic differential operators. And that's just a cubic term. That to me looks like the Chern-Simons term for the supergravity C field. I told you components of gamma were the supergravity, what remained of the supergravity C field. And this is what remains of the Chern-Simons term. Any questions on this action? I'm going to now I'm going to compute something with it.
This action is derived from the twisting pure spinor machinery?
It's not yet.
That would be an interesting thing to do.
It's a very interesting question, yeah.
How did you arrive at it?
Thanks. What we used was we knew what it had to be on shell. We also knew what it has to reduce to. So apparently M theory has to reduce to type 2A string theory. Kevin Costello and C. Lee gave some descriptions of type 2A, twists of type 2A string theory using the topological string, so using like sort of the higher genus B model. They wrote down this action. It's exactly analogous to this Kodaira-Spencer gravity action, but it makes sense in much more generality. So they wrote down an action for type 2, the twist of type 2A. And what we found is that this thing does reduce to the type 2A string. So that's one check. The rest of this talk is going to be about like trying to convince you that it's the twist of supergravity. But that's one check. We can also reduce down, we can compactify in a Clavier 3 down to 5-dimensional, down to 5D. And we get the twist of 5D supergravity coupled to what we know is the twist of 5D vectors and hypers, for instance. So that's another nice check. And all of these terms in the action play a big role in those calculations. They're absolutely necessary.
Can you do also reduction from these backwards membrane?
Yeah. I'll talk about back reactions.
No. You know that there is this formula by Nathan about the 11-dimensional superparticle, where you can get an action like a CQC, okay, which is a structure like a Chern-Simons type of theory, which reduces it to at least at the linearized level. Can you obtain this action from there?
I mean, that to me sounds quite similar. Is it wildly different than this pure spinor approach? Or?
Yeah, it's a pure spinor approach for the 11-dimensional superparticle.
So that's something we definitely want to try to do, I think. This is, I mean, maybe Martin can comment. This sounds similar to this approach. But,
I don't know. What was the question?
Can you obtain this action from this 11-dimensional CQC action given by Nathan? Was the membrane?
No, because you will need this action for supergravity.
Yes, but this should give the action of supergravity, which is exactly what Nathan says.
You can take my action of supergravity and
It's not equivalent to what Nathan did?
Of course it's related, but
No, it's not equivalent.
oh, that was a membrane.
Yeah, no, but for the 11-dimensional superparticle, you can do it. Not, no, forget about the membrane.
Yeah, that's just particle.
Right. And well, at least it gives
doesn't give you an interaction.
No, but for the kinetic term, it's just
So perhaps we can discuss in the coffee break further?
Yeah, sure.
So the theorem is that this thing, so this action satisfies the master equation. This is a totally consistent gauge theory in the BV formalism.
How do you count Gauss number here?
How do I what?
Count Gauss numbers.
So this is just a Z2 graded BV theory. So I've taken the usual world of BV, in which Gauss has an integral degree, and I'm breaking that to Z2. It does not have a consistent Z degree.
Or maybe it does if the action doesn't carry Gauss number 0.
I don't think so, no.
Well,
I think so.
If the action doesn't carry Gauss number 0, then there's certainly a way of doing it, right? Because you could assign a Z grading in the free theory and then just assign the corresponding numbers to the terms in the action.
Maybe.
I don't think I can.
And those internal degrees don't contribute. It's just like even, yeah.
Even or odd, yeah.
But this equation, this master equation for this type of action is not automatically implemented. I mean,
This is a theorem.
No,
it's not automatic.
If you have a psi cube psi, and then the master equation is a cube psi, comma cube psi with the integral, it's not automatic.
No, but this action is not psi q psi. This is some infinite.
That was the free theory. I'm proposing. This is an interacting BV theory. These are quadratic terms. That's a free theory. These are.
Didn't you say that there was like comma integral or psi cube psi?
That was how we got the linear theory, and now I'm proposing interacting theory, which does not come from pure Spinors yet.
Okay, it's interacting. I agree. Okay.
Sorry, are you going to tell us the nonlinear supersymmetries or the symmetries of that action?
Probably not, because I'm running out of time.
In principle, yes.
Okay, we'll stop asking questions.
So the first thing I want to tell you is a relationship of this interacting theory to a algebra that Martin wrote down. So,
sorry, but if S, this relation means that you have a closed symmetry, but since you play with supergravity in 11 dimension, you must have antifields of rank 2. So how do they occur in your expansion of, I think the field was called phi?
Maybe I can propose the following. The talk can go for another, since there have been a lot of questions, 10 minutes, if people are okay with that, and then there will be time to speak at length after that. Does that seem fine? Okay, Brian?
Can I ask a question?
So I want to say something about gauge symmetry. So in the BV formalism, all of the gauge symmetries are encoded by the BV fields together with their ENT fields. So that is, the cohomology of this complex is equipped with a Lie structure, really an L infinity structure, induced by the BV action. In this Lie algebra, L infinity algebra should be thought of as the universal gauge symmetries of the model. This is what BV does for you. So I'm going to do this on just this flat space now. So remember, we're just on C5 cross R. So the way I'm going to compute this is to first just take let's first take just the linearized cohomology. The linearized BRST cohomology. So I erased the complex, but it's encoded by those first two lines up there. And it's pretty easy to write down. So I can apply a version of the Poincaré lemma just for de Rham cohomology first. So that's using this internal de Rham differential. There's also a holomorphic version of that. So what I end up getting out, if I take the linear BRST cohomology, I get holomorphic vector fields on C5. Those are holomorphic vector fields on C5. That's the PV1 part. And notice there's no more de Rham direction, because the de Rham direction is not acyclic, but it's just one-dimensional constraint degree 0. So linearized BRST cohomology, no more degrees of freedom in the topological direction that was expected. There's still this operator, which is divergence, and it just maps now to holomorphic functions on C5. So that was the top line. Bottom line, very similar. I look at holomorphic functions again. Let me write it like O. And that maps to holomorphic one forms. So I've taken part of the, really I'm doing some spectral sequence here where I'm taking the Del-Bar cohomology first, but there's this remaining differential at this next page in the spectral sequence. And I can take the cohomology of this without too much difficulty either. So this thing is quasi-isomorphic to, now, divergence-free vector fields on C5. That's what this differential imposes. The kernel condition is that this is divergence-free. There's nothing left here. That goes away. What happens on the bottom line? Well, the bottom line, this is just another version of the Poincare lemma. One forms, modulo exact one forms, that's the same thing as closed two forms on C5. So this is even, and this is odd, because now I'm doing this Lie grading. So I just get closed two forms on C5, and that's not it. There's still another copy of constants here, again by the de Rham Poincare lemma. So there's a copy of constants there. Cool. And this was just cohomology. I didn't tell you what the BV structure is, but let me, or the Lie structure is, but let me tell you that now. So I'm going to still abuse notation and call this mu. I'm going to call this guy down here alpha. I only had holomorphic one forms in the original fields I wrote down. In this Poincare lemma, I've really applied a differential. So here in the original thing, alpha is like a component of d gamma. So it's the sort of differential of one of these gamma fields. It's a holomorphic two form now. And then I'll just call this thing C.
Sorry, shouldn't the Orden-Liebman assignment be opposite?
So the point is that there's an isomorphism of omega 1 mod exact.
But isn't alpha and gamma
as fields? As fields, yes. But to see the gauge algebra, you would shift the fields up by one.
But the action doesn't make
Well, so this is viewing it not as a theory, but as a Lie algebra.
So the gauge symmetry should be shifted from the fields. So things in odd degree in the fields are the gauge symmetries. That's the Lie algebra. So you have to parity shift everything to get the.
well.
Just think about ghosts like in gauge theory, right? They're odd, but what has the Lie structure? It's not.
Sure, but what is gauge theory? What is equations of motion? I mean, you never know until you.
Well, it's just that it's still the BV form. So in any BV formalism, give me a BV space of fields. Its parity shift has an L infinity structure.
Okay, let me just ask, what do you mean by the vectors being odd?
So it's a
even, sorry.
It's a super Lie algebra because I started with a super theory. It's a Z2 graded theory. So this is a Z2 graded algebra. And these are my things that are even, and these are my things that are odd.
Never mind. It's not the fields.
It's the gauge symmetry. These are the gauge symmetries.
Okay, this is the correct.
C is not coming to this.
C is the zero mode of what's called OC5. It's the constants inside.
It's just like constants, right? Because there's constants in that cohomology left over.
These fields are the two forms, the one forms and zero forms appearing in the reduction symmetries of the three forms.
Yeah, it's the on-shell degrees of freedom after taking linearized cohomology. I've solved the linear equations of motion right now in the twisted theory. That's what I've done. I could have phrased it like that from the beginning and not as a cohomology calculation. So what's the Lie structure? So you can read this off from the I just read the action, but you can read this off from the action. And I had infinitely many terms in the action, right? There was this power series that appeared. So a priori, you would have expected an L infinity structure. But it turns out, after applying cohomology, a lot of those higher terms become trivial. So there's this thing called Hamatapi transfer we learned about yesterday. Starting with any Lie algebra or DG Lie algebra, its cohomology has the natural structure of a graded Lie algebra, but you can also Hamatapi transfer an L infinity structure on it. So I'm just going to write down the bare bones Lie structure that you have on the cohomology. And you should recognize the appearance of some terms in the action here. So we have these two elements mu and mu prime in the cohomology. The Lie bracket, no surprise, Lie derivative. I'm writing down the algebra that Martin wrote down. You'll see in a second. So a mu and alpha field, no surprise, you can act by Lie derivative on alpha. It's a two form. So these both come from that. It turns out that these really both come from that term that's like 1 over 1 minus mu squared d gamma. So one term is quadratic in the mu's and spits out something that's anti-field to gamma, but that's another mu field. And similarly for that one. But then there's this additional term, which is gamma, d gamma, d gamma. And this corresponds to a Lie bracket, which is alpha alpha prime, is just alpha wedge alpha prime. And this is now thought about as a vector field, which I can again use the SL5 structure to do that. So this is a closed 2 form, wedge them together, closed 4 form. Its dual is a vector field, which you can show as divergence free because of the closedness condition. And if you don't do any Hamatapi transfer, if you just take the naive structure, anything bracket with C is just 0. C is like just a central term. And there's no other brackets, so C does not appear in any other brackets. But if you do the Hamatapi transfer, because you started with an interesting L infinity structure, if you do the Hamatapi transfer, what you generate is a central extension. So by the way, so this algebra here, what's the punchline? This algebra here forms the algebra E510. But we have this extra copy of constants around that weren't touched at all. So it's literally just a direct sum of Lie algebras, super Lie algebras. Nothing's happening. Hamatapi transfer does something sort of interesting. It induces a central extension, but it's really an L infinity central extension. So what it does, it's a 3-area bracket. It's like mu prime, alpha. This is a 3-area bracket. And now it involves C, so it's going to hit a C. So what you do is you take mu wedge mu prime. That's a PV2, which I can pair with a 2 form. Of course, those things are dual to each other. That's a function, and I can evaluate that function as 0 to get a constant. So I just take the constant coefficient of that Taylor of that polynomial or holomorphic function. So really, at the level of the Hamatapi transfer structure, this is a central extension of E510. So central extension E510 are the universal gauge symmetries, I would call them, of this twisted 11-dimensional supergravity. It was very important that I used all of the terms in the action as well. I'm probably done, right? Or do I have?
You're roughly done.
Yeah, I think it's time.
Okay, then let's thank Brian for his talk. And if there are questions, we have some time. We've done all questions. Everything's been done. Any questions from the online world?
Hey, Pavel.
You're just setting Z, like all of your Z's, like all the elements of C5.
What's that?
Z is parameterizing C5, right? So you're just taking that.
Yeah. This is a holomorphic function on C5, and you evaluate at 0. Yeah. So I want to maybe so this central extension is related to the M2 Brane extension of the 11-dimensional supersymmetry algebra. So it's if you were to do if you know anything about this M2 brane extension, it's an extension of the 11D supersymmetry algebra. You can twist that as well. In the same way I talked about twisting, you can take the Q cohomology. You do homotopy transfer on that, you get some twisted M2 brane algebra. And you see a very similar term like this. In fact, it's the same type of term. Yeah, so that's one way to think about this thing.
In this sense, the twisted algebra that you wrote down maps to E5 top.
Yeah.
Right. And this is like centrally extending both sides of that inclusion.
Yeah, I can say it like this. So, so we know we have this M2 brane guy. You know what it is? Great. It's a central extension of the 11D supersymmetry algebra, which we can twist. So we can look at its Q cohomology. So if I do homotopy transfer here, I get some L infinity algebra on the cohomology of this. And the claim is that this L infinity algebra maps to the central extension of E510.
That's a honest linear map, or that's a...
No, this is an L infinity map too. I'm using too many squiggle arrows.
Sure.
So it's essential to be compatible with this M2 brane extension to consider this extension, if you like. This extension is not so crazy. Like, it's very close to, you know, if you're doing like sort of symplectic vector fields on a holomorphic symplectic surface, you know that there's a short exact sequence involving holomorphic functions on X, like this, by the constants. So this is just taking a holomorphic function and looking at its Hamiltonian vector field. I claim this extension is exactly of that ilk. It's like the same sort of thing. In fact, if you were at Kevin's talk, you can sort of deform this 11D supergravity even further by doing something called the omega background. And if you do that, you find something basically exactly like this.
There's something funny about this term because it contains two vectors. Well, what I would say, at least from the beginning, was vectors.
Yeah, these are like translations.
Translations, and one spinor, one
alpha is coming from
part of an 11 measure spinor.
It's like a ghost for the ghost of the 3 form.
Oh, really?
Yeah.
It's not. I would have thought it was the local supersymmetry.
It's hard to trace back exactly. I mean, part of the advantage of doing this calculation in this way is that it goes very fast. You just get the answer.
They're in the same supermultiple.
Right, so it comes from the same supermultiplers, but you don't precisely know, because sometimes things in that supermultiplet will piece together in interesting ways, right? So like parts of the Gravitino will team up with parts of the 3 form.
Okay.
And that's a little bit hard to...
Yeah, okay. So make it... Right. So, but normally, I mean, the central extension builds on a gamma 2 with 2 vector indices and 2...
For the M2 brane.
Yeah, and 2 spinor indices.
It's like usually it's a Fourier operation, right?
Yeah, and here you have 2 and 1 instead of 2 and 2. So that's very confusing, I think.
Well, it also decreased arity by 1, right?
So it may... Okay, so it contains hidden singlet also.
Maybe. So this,
exactly.
This 3-area operation.
That's what it means to
twist term in the
Yeah. Fine.
Lemont, I think, has a question.
Did you try to do n equal 1 in 4 dimensions, which is much easier?
Did I try to do anything in what?
N equal 1 in supergravity, n equal 1 in 4 dimensions.
If we had a pure spinor language for it, I think you could try it, yeah. So I know what it has to be based on compatibility with this conjecture. I can just compactify.
No. Just n equal 1 in 4 dimensions has only 4 supersymmetry. It's much easier. It's completely truncated. Not only it's lower dimension, but you have a different...
What are you asking to do with 40 n equals 1 supergravity?
Yeah, I mean, this structure should also exist in the simplest case, which is supergravity n equal 1 in 4 dimensions.
There is a twist of n equals 1 supergravity in 4 dimensions.
Of course, there is, yeah.
So
and it's done explicitly. It's written with all possible details in the literature.
The twist?
The twist of n equal 1 in 4 dimensions.
Yeah,
So
I'd love to see. Do you have a reference? Or that'd be great to see. I'd love to.
Yeah, I have the reference. Okay. I'll give you. Because, see, what happens is that supergravity is, there are many things we ignore. But for instance, in cases like n equal 1 in 4 dimensions, we know that there are different systems of auxiliary fields, all minimal, there are 3, okay? And then these things should appear, because it means that in this structure, there are choices to be done. Because if you take the simpler case, you have choices. You have different systems of auxiliary fields. Minimal, new minimal, and so on.
Mm-hmm.
Then, the thing that, because the thing I don't follow in what you're saying is that it's very precise, but it's also kind of vague, because it's hard to see where are the fields that we use when we do computations in supergravity in 11 dimensions.
I agree with that. Yeah. I agree with that.
Then going to 4 dimensions, where we know all possible details, will be very instructive. I guess SL5 totally becomes SL2. I don't know. It's just one.
So there, I like a description of 40 n equals 1.
I'll give you a reference, because then you can extract.
So there would be, I think, a way of doing that by, for example, putting this theory on a G2, or let's say Clebia 3 times a circle, and then you know which multiplets are supposed to be there in the compactified theory that you get.
Maybe.
And you know also the twists of the matter parts of that, so you could just compare the results, and you would get, as you say, one version of the 40 n equals 1.
I could write down an action. It's actually a lot easier. It's not. There's a version of the action that just keep it. In fact, for the twist of 40 n equals 1, it describes the moduli of Clavier surfaces in the same way that this is sort of connected to the moduli of Clavier structures. But there's this extra time direction, of course. And this Chern-Simons term sort of messes that up as well. But
is there a sense in which twisting commutes with dimensional reduction?
We have for like non-gravity theories, there's a theorem like that, if you take what we believe to be dimensional reduction as a mathematician, but yeah. I don't think there's like an accepted definition for reduction of a supergravity theory yet, but we have some idea of what it should be. Yeah.
Can I ask you something, again, very, probably more philosophical, better than an actual question. Like, can you say that the pure Spinor formalism is a functor from the category of like modules or like sheaves of modules over the importance?
I would say so.
So it's okay. So from sheaves of modules of
really nice one,
on an importance variety to the category of SUSY multiplet.
Yeah.
Right?
Yeah.
And so what are the arrows in the category of SUSY multiplet?
What are the arrows?
Yeah, the arrows.
So to me, a supersymmetric multiplet is going to be some like local object in spacetime. So it's going to be built from vector bundles, complexes of vector bundles. If you just
so it's just
ordinary. Okay. I mean the category of things you get certainly sits inside the category of chain complexes of vector bundles with differential operators mapping between them that have homotopy actions of the supersymmetry algebra that you started with that are compatible with the natural axioms of translation on the sections of these bundles. So that's one version of the category of multiplets if you want. But you get something more than that, which is that what this functor does is if you take, you're working in the category of modules over the structure sheaf of this variety. And the image of the structure sheaf is in fact itself an algebra. And anything else that you get is a module over that algebra in a natural way. So in a sense, it's like a functor from a category of sheaves of one kind to a category of sheaves of another kind. but where those sheaves also have this more traditional multiplet structure. I don't know if that's.
Sure.
I think you're asking exactly the right question, because I think, yeah, there's a thing you would like to say, which is that, can you ask whether this is an equivalence of categories?
Exactly, I was thinking about something like that.
Yeah, I think it depends a little bit on how you define the target category and what you demand.
Exactly. I mean, honestly, that would be fantastic. So I think something like that would be groundbreaking. Thank you very much, by the way. It's great.
Any further questions? So if not, we'll take a slightly less than 30-minute coffee break, and then Owen will start his talk at 5:15. Let's thank Brian one more time.
This is you. Yeah.
It's great.
Great. I can show you it. It's nice to compare. It's very easy. It's very simple. Instead of having exactly.
Well, can we get some coffee?
Yeah, I'll take a look. And we can come to
1, 2, 3.
Angmar? Angmar? Okay.
Hi, Owen. How's the sound?
The sound's okay for me.
We hear you great.
Great.
We're just getting your slides up, or if you want to share those from your...
I'm an old school guy. I don't do slides. I'm gonna do like a board talk.
Oh yeah, but you have a thing that needs to be shared, right?
Yeah, so I need to share my screen. So
exactly.
I have my computer up as well. I can, if you for some reason want to see my face while I'm talking, I can.
We're gonna see both of it. Yeah, we're gonna see it all.
Okay. I don't think you want to see it all. Okay, so let me share my screen.
Okay, so we've got your screen, but not your face.
I know you're missing that.
Yeah. It'll come back.
So I'm logged in as two different people, so you could pin my face on the side if you wanted or something.
Yeah, we've got you.
Okay, great.
Awesome. I think the technical stuff is pretty much ready.
Okay. So do you want me to start?
Yeah, well, I'll introduce you. Welcome back, everybody. We're very happy to have Owen Gwilliam joining us from Amherst, Massachusetts, to talk about higher deformation quantization of Kapustin-Witten theories.
Okay, thank you very much for the invitation. Sorry I couldn't be there in person. It's a lot harder to evade things like teaching and committee work when you don't actually leave. So sounds like it's going really well. It's nice to see so many people there actually interacting in person. So yeah, thank you again. So I'm going to talk about some joint work with Chris Elliott and Brian Williams, the famous Brian Williams who spoke just before this. So it's about certain four-dimensional gauge theories sort of popularized by Kapustin and Witten, and we're going to do what I'm going to describe what I mean by higher deformation quantization along the way. So let me start the talk. Okay. And maybe I can ask a question before I start. Does the screen is it legible? Like I can change the color of the background or something if that would be easier to see.
White would be better.
White would be better. Okay. Like that kind of white, this kind of white, that kind of white.
I think the second kind of white, maybe.
Yeah, well, but the dark, either a dark background with a light pen or the other way around.
Okay, I'll do this. All right. That's something you can't do at a real blackboard. Okay. So let me sort of say, this is a mixed audience, and honestly, I'm a mathematician, so I don't have a great sense of everyone's background. So let me sort of like broad theme of the research I want to discuss is that I think it's a good time for mathematicians to start thinking about what people sometimes have called the dynamics of 4D gauge theories. So this was a topic, so I want to revisit these dynamics of 4D gauge theories with some new mathematical tools. So I have in mind, when talking about dynamics, things related to sort of important phenomena in n equals 1, n equals 2, n equals 4, supersymmetric Yang-Mills. So why might we want to do this? So why? And I'm going to speak as just a mathematician here. There were big consequences back in the 90s about this stuff, like the Seiberg-Witten invariants, which were a big deal for people who care about four manifolds. But mathematicians mostly ignored the actual physical arguments. We just sort of took suggestions and ran with them. So I think there's some opportunities here if we can make it more mathematical. So maybe there's some opportunities some things that we might benefit from. Secondly, let me talk about how I want to pursue this. So I really want to emphasize, we're going to do something a little bit, I'm going to talk about something that's a little bit different than the way mathematicians have usually engaged with these kinds of topics. So we're not just going to take hints from physicists about what some duality predicts and then go and do our usual math on it. So what we're really going to try to do is, first off, when I said revisit, one of the things I mean is that we're going to construct theories using the foundations, so these new mathematical foundations for QFT, Euclidean QFT, due to Kevin Costello. So he's developed a nice machine that sort of builds on insights from people like Kontsevich and Albert Schwartz and Catania Felder, Axelrod Singer, really systematized. It's given a way to build a lot of theories, especially build perturbative theories mathematically. And I want to emphasize that when I'm saying revisit these dynamics, we're not going to directly do the SUSY theories. We're going to focus on twists. So twisted field theories of supersymmetric Yang-Mills. So the nice thing about these is that these are either topological theories or holomorphic. So the equations of motion look like, pick out holomorphic sections of bundles, or they're sort of a mixture of the two. So these all have, the nice thing about the twists is that they're geometrically meaningful and well behaved. So even if they're not physically useful for mathematicians, they're quite compelling. So let me be specific. This paper with Chris and Brian is this particular case of this theme. So for this talk, for this talk and for the paper, we're thinking about pure n equals 4 supersymmetric Yang-Mills on R4. And we're interested in sort of, well, there is maybe a better way. With its three-dimensional family of twists. So if you want to, you can sort of picture this three-dimensional family as there's a special point that's holomorphic. You can do a further deformation. There's a two-dimensional family of deformations that we might call B-twists, sort of a flavor of B models. And then up here in 3 space, there are these families that are sort of A-type twists. So there's this three-dimensional family, and we're gonna study this family of twists. If you don't know what I mean, that's okay. I'll write down that family later in the talk. So just as a side remark, mathematicians are interested in this primarily because Kapustin and Witten gave a compelling argument about how these topological twists related to what's called the geometric Langlands correspondence. So they related S duality for the sort of A and B twists, among the A and B twists, to geometric Langlands correspondence, which is a really important project in mathematics, very deep, long-going project. So this is a motivation for mathematicians, and I want to emphasize, like, we won't like use or touch S duality or Langlands duality in this talk. The moment I'm going to focus on, we're just focusing on more sort of foundational things here, sort of just figuring out what the 4D theory is and not really sophisticated things like dualities, although of course in the long run we'd love to get there. So let me just sort of say, like, give a preview of the results I want to talk about so that you sort of know where we're heading. So we do the following. So maybe the first big thing is just to say that we construct and analyze Batalin-Volkovisky quantizations of these twisted theories. So there's a three-dimensional family of theories, and we show how to quantize all of them in a very uniform way. So, like, these are really nice theories, as you would expect, based on the fact that n equals 4 supersymmetric Yang-Mills is very nicely behaved perturbatively. So, like, there are no counter terms needed. We give a really nice renormalization, or really what we do is we use a beautiful framework that Brian Williams introduced, and we get an exact one loop quantization for all of them. So it's a very, like, there's just a great answer, very complete, pretty manageable. This may not be surprising to the physicists, but it's certainly not something that mathematicians have grappled with before. And it's really nice to sort of work through carefully. So we hope it's fruitful for people. I'll remark, and we'll talk about this later, that we actually don't just do it around the sort of trivial vacuum, but we work over we also introduce another set of parameters, this certain moduli of classical vacua, which you can work with. Okay, so first off, we just do this sort of perturbative constructions. We set up the Feynman diagrams, show they behave well. The second thing we do, which is probably the most novel thing, is we explore the higher algebraic structures that emerge. So the higher algebraic structures of the observables. So when you construct a field theory in the BV formalism, you get an interesting cochain complex, DG vector space of observables. You
mean the topological observables or all observables?
All observables.
Including those like F squared and this Wilson loop.
Sorry, be a little bit louder.
All gauge invariant observables.
Yeah, absolutely. All gauge invariant observables, but more than that, we write down a chain complex whose homology, would be the sort of usual gauge invariant observables. So we remember how observables are acted on by gauge transformations. We sort of keep track of all of that extra data. It's like the difference between knowing the kind of cohomology of a manifold versus actually having control on the cocycles and how they are related. Okay, so the point is that the observables here are, this is where the phrase deformation quantization is going to come in. So let me say, like, elaborate on this a little bit. So maybe I'll do green again. So for the topological twists among that three-dimensional family, the quantum observables form a very sophisticated and interesting kind of object that a mathematician the language comes from topology, but called framed E4 algebras. So I don't expect people to know what that means. I'll try to elaborate on that in the talk because it's not common. If you've ever heard of the little n disks algebras, then this is E4 means it's an algebra over the little 4 disks operad, if you're familiar with that. So just as a remark here, I guess. So if we're doing 4D theory, but if you were to do a 1D theory in the same way, then the observables, the classical observables, are commutative commutative corresponds to classical. When you quantize, if I'm just going to use this language, you'd get an E1 algebra, which is a way of saying associative. So this is the quantum side. So the point being that in the 1D setting, commutative deforms to E1, which is a version of associative, and we're doing a 4D theory, so we're going to get an E4 algebra on the quantum side. And in this sense, we're doing a deformation quantization. We're deforming from commutative to E4. Okay, so the E4 language is probably not familiar, but using some modern techniques in mathematics, we get a nice consequence. So one maybe easier to understand consequence is that each topological twist, when we quantize it, determines a fully extended, oriented, four-dimensional TFT in the style of a Tia, Baez, Dole, and Lurie. So there's a functor from some category of four-category of oriented Bordisms. I'll call this functor ZT into a target category, which I'll call Cat4. So this is some higher category whose objects are four categories, which you don't need to know what that is, but it's just, this is sort of a Tia Siegel style topological field theory. It's just a sort of richer version.
And it's oriented, not framed.
Yeah, for these topological twists I'm talking about. So for all the topological twists, I probably won't elaborate on this, but like in that three-dimensional space, there's a two-dimensional plane of topological twists that admit that work on oriented manifolds. The rest of the sort of quote-unquote topological twists, which involve sort of funny parameters, are just for framed things. Okay, so this, let me just sort of unwind what this kind of thing might do in a special case. Suppose you had a closed oriented three manifold. Then ZT of M3 is actually a kind of, it's a DG associative algebra, if you'd like. You could think about it as a category, but I think about it as a category of modules if you wanted. Okay, so that's a kind of, from the point of view of the 4D thing, there's sort of M cross R. There's sort of kind of canonical quantization story, and I'm seeing some DG algebra of operators. If you had a four manifold, maybe with boundary, so here's X, and maybe its boundary of X is M, then ZT of X is actually a module, DG module for this algebra. So yeah, so we'll see later that these algebras, at least for the B-type twists, really look like sort of differential operators on some moduli of flat G bundles. And this is sort of functions on a moduli of flat G bundles on X. So this is a kind of Fock algebra and a kind of Fock module here. Okay, great. So I'm going to add another page. Okay, so there's lots of directions to explore from here. So I just told you what happens in the 3D case, but suppose you took a closed oriented two surface, closed-oriented surface, two-manifold. You could imagine doing dimensional reduction along it. So you could look at ZT of sigma, and this is some E2 algebra, or if a physicist might be more familiar with the phrase Gerstenhaber algebra. So for each surface and Lie group G, you get an interesting Gerstenhaber algebra, or for the holomorphic twist, you actually get very interesting DG vertex algebras. So question, so we don't explicitly analyze these. But the nice thing, if you do this 2D case, is that you could start to compare to existing works. So question, how do our E2 and vertex algebras compare to those already known in the geometric Langlands program? So I think this is a very kind of fun question to think about, and we're hoping to work on it, but if other people are interested, we'd love to talk with them. So like we're just doing a very straightforward application of BV formalism, and we get back, say, vertex algebras. It'd be nice to know how they relate to the vertex algebras people are studying from a more representation theoretic point of view. Okay, so that was my extended introduction to the talk. The kind of output we get are these higher algebra structures after we've constructed the Feynman diagram. So now let me start the talk proper. But if there's any questions, maybe this is a good moment to start to ask. Okay. So let me start with the theories we study. Let me tell you what they are. So I'm just going to describe the twisted theories. I'm not going to explain how they show up as twists of n equals 4 supersymmetric Yang-Mills. There's a lot of people in the audience who are much more expert on that than I am. I'd say probably almost everyone's more of an expert than I am personally. So I'm just going to skip to the answer. But if you're there in person, you can like bug Brian all you want. Okay. So we're going to fix a complex Lie algebra G. This is sort of gauge Lie algebra with a non-degenerate invariant pairing. All right, like with brackets or whatever. I don't know. You can think about like SL2 or something if you wanted. Okay, so let me talk about the holomorphic twist first, because we're going to view everything as a deformation of the holomorphic twist. I'm going to try to describe it sort of carefully. So before I give a description of it, let me just sort of say it is a version of a holomorphic BF theory. So if you're happy with BF theories, then this is one of them. A holomorphic, that should be singular. BF theory, where we use not G as the Lie algebra, but we use a thing I'm going to write as G adjoin epsilon, which is G with an extension by an odd part. So epsilon has odd parity if you want. It's a kind of super Lie algebra. Secondly, if you're more geometrically oriented, so in geometric terms, in global geometric terms, the moduli of solutions to the equations of motion is a very nice moduli space. And here I'm imagining X as a closed complex surface. So it's 4-dimensional as a real thing, 2-dimensional as a complex thing. And this identification with the holomorphic twist with this Higgs, this shifted cotangent bundle of a Higgs moduli space sort of relies on that compactness. But this is a very important object, of course, in modern geometry. So hopefully it gives you some orienting sense of what I'm talking about. But let me write up the thing in BV terms. So in terms of BV, we have 2 copies of the Dolbeau forms. Bless you. On C2. So Brian was talking about this a little bit earlier. So Brian was also using these. So there's these 0-0 forms on C2. So tensor G, 0-1 tensor G, 0-2 tensor G. Okay, and then I'm going to have, so that's the 0 star forms like Brian was writing earlier. There's also the 1-0 term, 1-1, 1-2, and then there's going to be a copy of the 2-0, 2-1, 2-2. And so I'm putting this kind of grading at the top. This is a kind of ghost grading or cohomological grading. So the sort of the ordinary fields, the fields we think about, sort of the natural ones, are the ones living in degree 0. I'm going to view all these pieces as the sort of alpha fields in the BF theory, or the A fields in the BF theory. There's also the companion, the B fields, the sort of cotangent direction. And those start actually down here. So there's an omega 0-0 tensor epsilon G. There's an omega 0-1 tensor epsilon G, omega 0-2 tensor epsilon G. And then there's a sort of partner thing. And I'm just not going to write it all out. That extends over here. There's omega 2 bullet tensor epsilon G. Extends over here. Okay, and so these the BV pairing between fields, for instance, connects, say, the 0-2 field here with the 2-0 field here. So these are the sort of under the BV pairing, those are sort of conjugate variables. Sort of the 1-0 fields are connected with the 2. Jump the gun there. So 1-0 would go with 2-2. Sorry, 1. I did it right. Okay. So I just want to give you a sense of how the things are partnered up. Okay. So I've done this Z grading here, this integer grading, Z grading. I'm going to break it down to a Z mod 2 grading in the long run. So there's just sort of odds and evens, but hopefully this gives you a sense of where things live. Now, what's the action functional? So the holomorphic, for the holomorphic twist, sorry, I should say over here, these are, I'm going to view these as beta fields. The action functional looks like this. So an alpha field can have a component, in any of these things here. If I apply del bar to it, that actually is just moving horizontally in this picture. It just increases the second Dolbeau form degree. And then I look at pairing it with some beta form. And so the pairing is going to be 0 unless I don't care about, I only care about pairings if they give me a total 2-2 form that I can integrate over C2. Okay. I think it should be clear why this is a BF type action. So for instance, if you unravel the equations of motion, you can view an alpha 0-1 component as giving you a kind of del bar connection. And the equation of motion says that this thing, equation of motion says, let's call this del bar alpha 0-1. EOM, for instance, says that this thing squared equals 0. And then it'll also impose conditions about how various other fields have to be flat for that del bar connection or annihilated by that del bar connection.
This depends on anti-fields, right?
Yeah. So right. So I have like, absolutely. So here's sort of my maybe ordinary fields. I've got ghosts. I've got anti-fields. I've got, ghosts of ghosts.
And then at some point, you have to eliminate the anti-fields, and then.
This is it. This is all the field content. This ends up having all the properties you want of a BB theory.
Will you eliminate the anti-fields in functions of anti-ghosts or whatever?
What do you mean by eliminate?
Gauge fixing.
Gauge fixing. It's called gauge fixing.
In some sense, yeah. So when we do the, you don't have to do any gauge fixing at the classical level. At least from my point of view, what I've just described is a perfectly well-posed moduli problem. I can look at solutions to sort of, there's a setting in mathematics called derived geometry. From that point of view, this collection of data ends up defining a derived space. And there's no gauge fixing required there. If you want to ask certain questions about that derived space, you might choose to pick a gauge, like fix a gauge to do some computation. But that's akin to picking like a chain homotopy on a chain complex in mathematics.
But if you want to compute the observables, you have to do that.
No, you don't. You don't. Once you have a chain complex with this thing does give you a chain complex of observables. You can ask what the homology is, and you can pick different methods for computing homology. So there are further twists. So I really want to emphasize in this action functional, there's this del. I shouldn't have done that. I meant to do this. There's this del bar operator. But you can turn on other operators, notably the del direction. So turn on del operators. Deformations of the theory. So for instance, let me give you it. If I pick parameters T1 and T2 in C, then I get a deformation of the following kind. Call it S sub T1, T2, depends on alpha and beta. I take that holomorphic action before, and I add to it a modification. So this is going to be beta paired with T1 del Z1 alpha plus T2 del Z2 alpha. So, and here, when I write like del Z1, what I really mean is D by DZ1, DZ1. So that component of the del operator. And similarly for T2. So you can see I'm just deforming the quadratic term. If you pick both those parameters T1 and T2, you get a topological BF theory. This action functional looks like, so 1, 1 alpha beta becomes beta wedge d alpha, the Durand differential, plus 1/2 beta alpha alpha. Okay. Okay. If you keep, say, one of the parameters, like say you could keep t2 equal to 0, but you let t1 not equal 0, let's say, just say t1 equals 1, you get a mixed theory. So it's topological along the Z1 direction and holomorphic along the Z2 direction. So Kapustin put a lot of effort into talking about these. So we call these Kapustin twists. Okay. And I'm going to add one further deformation. So, okay, I should just remark. So these T1, T2 deformations, we're calling them B twists. And that's sort of terminology more or less borrowed from Kapustin and Witten. The A twists come from a further deformation. I take, so S, so here's, now U is going to be another parameter, ST1, T2U. Alpha beta is this thing we just defined, plus so remember the beta field was weighted by epsilon. I could strip off an epsilon, and then it's sort of an alpha type field, and so I can pair it with beta. Okay, so that's a B type. That's an A type twist. So this three-dimensional, you can see there's three parameters here: T1, T2, and U, and that's the family of theories we're going to quantize. So one of our collaborators, Chris, drew a really nice picture of this space. So there's a three-dimensional space of square zero supercharges that we're thinking about. This vertical plane here with his coordinate system, so T1 and T2, those are these B twists. So I guess I flipped the orientation when I drew it earlier. There's this two-dimensional space. The center is the holomorphic twist. There are these Kapustin twists where either T1 or T2 is 0. So there's this cross Kapustin twists. There's the B twists. All the rest of the stuff is A-type twists. And there's, of course, a special plane in here where T1 equals T2. And just to answer, I think it was John Huerta's question, these green ones are the ones, these are the topological twists where we can get a framed E4 algebra. So we get an oriented theory. Okay, great. Could I ask Angmar, how much time have I been talking? I don't remember exactly when I started.
I think you have 20 minutes approximately, or maybe slightly less.
Okay, cool, great. So let me just make a really brief comment about the moduli of vacua. And I mean here with classical vacua. So translation invariant solutions on R4. So let's think about the B twist where T1 equals 1 and T2 equals 1 and U equals 0. So sort of the best B twist. That's just a topological BF theory. Then translation invariant solution. Up to gauge transformations, alpha is 0, but you could have beta be some fixed matrix in the Lie algebra G, or I should say sort of G epsilon. And so that's sort of a constant solution. Two such solutions are, on the right-hand side, are equivalent if they're conjugate under the group G. So the upshot is that the moduli vacua for this B twist, I claim, is this stack. This is the quotient stack. And all I mean by that, that's a sort of fancy mathematical way of saying that you can run over the choice of this point in G, that's this G here, but you should sort of identify them in, you should, really what you should do is you should work over G and make everything be big G equivariants. If you do that, that's what it means to work with the quotient stack. If you do that, the nice thing about it is it remembers all the enhanced symmetries. Whereas if you forcibly take the literal quotient, you get something that doesn't remember those symmetries. So this is the moduli of B vacua. So a claim we just sort of assert in the paper and discuss is these vacua extend to the holomorphic and A twists. The twists are different, the vacua are different depending on which twist you're working in, but this is a sort of common class of vacua. And we actually will quantize both for a choice of twist and for a point in this stack. And if you've ever seen the n equals 4 moduli vacua, this is sort of different. So it sort of makes sense that under twisting, this vacua may change. Okay, so that was section 1. That was the theories we're interested in. So section 2 is just a sketch of how the quantization goes. Okay, so let me just point out something. So if you remember what the action functional has these terms that look like beta del bar alpha plus beta, and then you have these T1 del 1 alpha, T2 del 2 alpha plus U del epsilon alpha or beta. And then there's this beta alpha bracket alpha. So this part here is, of course, the quadratic term. And if you unwind, we take a Landau, we do a Landau gauge fix using del bar star. So the adjoint to the del bar operator. And what that ends up meaning is that sort of all of these things don't really affect the propagator in practice. So the propagator is naturally oriented from alpha to beta propagator. And the only vertex is this trivalent vertex. So 2 copies of alpha and 1 copy of beta. This means that only one loop diagrams appear when you try to construct the diagrammatic quantization. So you get diagrams like this. You kind of think about there being a wheel with an orientation, and then there are these trees that can come off. And the outer legs are just alpha dependent. Okay. So one of the things we rely on in our construction is that Brian Williams worked out a lot about how these, what happens when you do these use this Landau gauge fix for theories of this flavor, where your quadratic, the sort of important part of your quadratic term is a del bar operator. So Brian Williams showed holomorphic theories are really nice. That's not a theorem, that's like a summary, but what I mean by this is that there's no counter terms at one loop, and he sort of, he pins down the nature of the anomalies very clearly. So the analysis, all the Feynman diagrammatic stuff at one loop anyway, is well understood, and we just sort of explained why only one loop stuff shows up for these theories. So we can apply Brian's results and sort of have really good control of the theory. So thanks to Brian, we see that the QME is satisfied as the anomaly actually, so this is the part we have to do. The anomaly vanishes for this family of theories. We use his general results and then just look at the anomaly that you get very carefully. And since everything only involves one loop, all the twists quantize exactly at one loop. Okay, and that's true actually even for every vacuum X and G, and it's equivariant, so I can even say in this quotient stack. Okay, so that's a real quick summary of what we did with the constructive part. I'd like to now turn to the observables. So maybe just before I go on to the observables, I should just say that, so these are maybe, this is one of our theorems. Make this sort of statement 1, statement 2, is that these are sort of analogs of, I think, the really beautiful results about how, about the perturbative quantization of n equals 4. Although we don't use those results in any way, it'd be really nice to actually understand how those sort of long-standing results relate to the computations we do. That's at least out of my out of my realm of expertise. Oh, sorry, I wanted to show you. So this is this picture of the kind of a way to try to visualize the family of theories that we're quantizing. So there's this C3 direction of twists, or of supercharges, and here's the vacua. So the purple triangles are supposed to be this picture of the kind of vacua. If you've seen like nilpotent cones or something, maybe this can be a little bit reminiscent. And so there's a family of these things over every choice of twist, which we're sort of visualizing down here. Okay, so let me jump ahead down to observables. Okay, so a special feature of the BF type theories we're studying, it's true more than of a lot of other theories, is that the quantized action, so when we include the quantum corrections, the one loop correction, has the following form. There's the classical part, and then we just got a one loop correction. That was it. And now this term, if you looked at it, this was always, at least for the B twists, let's say for the non-A twist, this was linear in beta. So let's say U equals 0 here. And this was actually independent of beta. These the wheel diagrams just had alpha legs on the outside. So this is a really highly controlled situation. If you read our theorem carefully enough, actually, we show that this quantum correction is the same for all the twists. So even when U is not equal to 0, it's still independent of beta. So in the U non-zero, in the A twists, you get this one quadratic term in beta, but it's still polynomial. So everything's still polynomial in beta. So it's all polynomial in beta, although in principle, there's sort of possibly really high powers of alpha that show up. So there's a couple of consequences of this nice form. So one consequence is we can actually set h bar to 1, which is nice. And a thing that I really want to emphasize, that's maybe not, it's the sort of thing that's important to me as an algebraist, is that we can restrict to observables that are polynomial in beta. That may not be a thing that you obviously want to do, but let me explain that we do this in quantum mechanics. So we do something similar in quantum mechanics. We sometimes do this in quantum mechanics. So for instance, if our phase space is not an arbitrary symplectic manifold, but like a cotangent bundle, then we could think about the fiber-wise polynomial functions sitting inside of all functions on X, on cotangent bundle of X. Okay, so maybe as an example, you could think about
You may have frozen.
it's inside of all smooth, yeah?
Back now.
And the nice thing about that is that these space of fiber-wise polynomial functions emit a really nice deformation quantization. The left-hand side has a familiar deformation quantization, namely fiber-wise polynomial functions deform to differential operators on X. I think you guys all know this, but a differential operator only allows you to do polynomials in the derivative part. So to continue our example, this looks like smooth functions in R. You sort of formally adjoin a variable, maybe called the derivative, and then you mod out by the relation that the commutator of the derivative with a function is the derivative of the function. Okay. And differential operators are a very nice thing to study and work with. So we're going to do the analog in these higher dimensional field theories. So we sort of, we explain how to phrase this kind of setup for such higher dimensional field theories. So of these fiber-wise polynomial quantizations. So as an example, if M is a closed oriented 3 manifold, and we're doing the sort of nice B-twist, then when you think about the theory on M cross R, the classical B-twist picks out the cotangent bundle to the moduli of flat G bundles on M. So the solutions to equations of motion is this cotangent bundle of flat G bundles on M. We work perturbatively. Around the trivial connection, 0, triv connection. Flat G of M. So mathematically, I mean that I take the completion, that's this hat thing around 0, formal completion. And so the classical observables on M cross R is a quasi-isomorphic to the fiber-wise polynomial functions on T star flat G around this formal neighborhood. So that's one thing. So the second thing, which is the more interesting thing, is that that our quantization actually gives you a deformation quantization of this thing, which you can interpret as the differential operators on flat bundles. I should be a little bit honest here. This thing is an interesting derived space in the setting we're working. So there's some subtlety in figuring out what you mean by differential operators. And I would say that our definition is an acceptable answer for what you would mean. In that case. Okay. So a question that might be bothering you now, though, is how did we go from working on R4, that was where I gave all my initial theorems about quantizations, to a claim about something like M3 manifold cross R. Like I used very specific methods for R4. How did that now scale over to some interesting thing? I really want to emphasize we don't directly construct the perturbative theory on M cross R. What we do is we leverage the mathematical formalism what's known as factorization homology, which is a kind of multiplicative or non-abelian generalization of ordinary homology. So I'll use this notation like this. Put a fact there. If I have a manifold like M cross R3, M cross R, I can take its values in, say, observables for the B twist. So this is observables on R4. Okay? And this, I define these observables for this thing to be this factorization homology. So there's a very factorization homology gives you this nice construction that goes from the category of oriented four manifolds to chain complexes. If I take this algebra, and it sends, so the maps here are embeddings, it sends a disjoint union of manifolds to a tensor product. And so if we took the special case maybe of two four balls like B and B prime sitting inside of a bigger ball, B double prime, I get some map from observables on B, tensor observables on B prime, to observables on B double prime. So this is what people call the E4 structure in math. But a physicist will recognize that this is some kind of operator product. I have an observable in this ball and in this ball. Together they give me an observable in the bigger ball. But there's a four-dimensional sort of structure to it, because I could move these balls around in this. Well, I'm not drawing the four-dimensional space, but if you were drawing the four-dimensional space, that's what you get. Yeah.
It's only local observables.
Sorry, can you say I didn't hear the beginning of the question.
Are these local observables?
The things on the balls you should think of as local observables, but thanks to this construction here, you can evaluate it on sort of any oriented four manifold. So you get, if you do it on like a circle cross R3, you can actually see like Wilson lines in there. Wilson loops.
The method of topological descent is being used implicitly here. This is sort of the mathematic version of topological descent.
Sorry, was that, so somebody was just giving a point of view on like how this works, or?
That was Brian, yeah.
I can't hear the audio.
So Owen, do you hear me when I speak into this microphone?
Couple.
Uh-oh.
Oops. Oh no. We are decoupled. We're decoupled.
factorization homology lets us see the possibility of connecting with the geometric Langlands program because, so for, among other things, people have already used a different version of factorization homology in this setting. So Bensby, Rochier, and Jordan have already used factorization homology in this setting, and there's further work afterwards in the GL setting. Factorization homology like this gives you a TFT. So you can try to compare with the 2D TFTs suggested. So after reducing, suggested by Kapustin and Witten via dimensional reduction. So that's a direction to try to go. Maybe the main takeaway is just that the mathematical formalism of dealing with QFT has made some progress recently. And so I think there's some interesting opportunities to see what these new formalisms have to say about some really important classical questions by classical, I mean just things that existed when I went to grad school. So stuff that happened in, say, the 90s about dynamics of gauge theories. So that's it. Thank you for listening. I think I went over time, but nobody stopped me. So thank you.
All right, thanks a lot. Thanks a lot, Owen. Do you hear us?
Am I frozen?
You were a minute ago. Do you hear us now?
Now I can hear you, yeah.
Okay. Any questions?
Yeah. Do you hear me?
Can I speak up?
I can hear you.
Okay. Just a naive question, because you draw this diagram, this loop diagram, and I simply could not reconstruct how you get only external alphas from the vertices you draw. There's one loop diagram with these external tree diagrams, because you had a tree with two incoming alphas and one outgoing beta, and then just one propagator going from alpha to beta. How can you get like a tree diagram like you draw with these vertices? I mean, it was just a sketch you were drawing, but I'm kind of curious.
So the point maybe is that the graph you draw, the Feynman graph, will be directed. And maybe the way I drew it was not totally illuminating, but when you, maybe I'll switch, which it's freaking me out. It's like, can you hear me? Can you hear me? Can you hear me? Can you hear me?
Infinitely.
Was that us? Just one of you needs to be muted, but I think it's good now.
This is the same one.
Okay, can you hear me now? Ah, God, okay. Okay, hopefully this is better.
I think that's working now.
Oh my God. Okay, I tried to be too clever. But can you hear me?
Yes. No. Now we can't, though.
Muted.
I think you muted yourself, maybe?
You get it, don't you?
Yeah, now I get it.
If it's one vertex.
I mean, it was just a sketch, right?
The arrow would go in, it would be 2 alphas and 2 beta, but it goes the other way and becomes null.
Okay.
That's essentially it.
Owen?
I gotta go to the other room.
So I think Owen will be back.
So I clearly can't operate 2 devices at the same time. Am I audible now? I apologize.
You are now audible, yeah.
I don't know what happened. Like I turned off the sound and I muted my Zoom, but it like kept making noises. All I wanted to say was you should just ask Brian. I feel like at this point I'm pretty flustered, and it's really easy combinatorics to make the graph with that information. But it might be easier if somebody can talk with you.
All right. Unless there are any other questions for Owen, maybe we can let him go. Thank him one more time for a great talk. Next up is the last talk for the day, which will be Vera. So we'll need just a minute to switch things around. Vera, will you have slides?
I have something, yes.
Perfect. Okay, we see them.
Let me try.
Yes, I think it's working well.
Can you hear me?
Yes, we hear you.
Okay.
And do you hear us okay? The room?
Actually quite okay, yes.
Good, very good. Okay, so if you're ready, we can go ahead and get started. Sorry about the delay. We're very happy to have for the last talk of the day Vera Serganova from Berkeley. She's going to tell us about volumes of super-Grassmannians and splitting supergroups. Excuse me.
Okay. So the sound is okay?
Yeah, it's very good.
Well, thank you for inviting me. It's unfortunate that because of time difference, I can't attend many talks. What I'm going, so I'm certainly not a physicist at all, and what I'm going to do related to representation theory of supergroups and superalgebras, but some questions are interesting for physicists, I think. Let me start with the motivation. So one of the interesting features of representation theory of supergroups and these superalgebras is the absence of complete reducibility. Not every representation of a supergroup is completely reducible, splits into irreducible, sum of irreducible summands. The reason behind this is kind of very easy. One of the reasons is that just a supertrace of a scalar operator or the identity operator might be 0. And the famous while unitary trick doesn't work very often in the super case. So for example, if I study representation theory of super unitary group, UMN, one of the things which is used is taking average over the group. And if we consider hard measure or invariant volume form on the supergroup UML, so the volume of the supergroup is most always, unless it's a usual group, which doesn't have fermionic variables at all, the volume is going to be 0. So it makes sense, therefore, to look for homogeneous spaces, for example, homogeneous spaces with respect to this group UMN, and check when they do have 0 volumes and when they don't. And one natural place to look is actually the super Grassmannian. And it is interesting that this question was open when the volume of a super Grassmannian is 0 or not. There was a conjecture by Ted Voronov some time ago, and there were even some papers which contradict this conjecture, but in fact, I think this conjecture is true, and I'm going to talk about it in particular. But I was interested in this problem of computing volumes of super Grassmannians in relation to representation theory of supergroups, and somehow certain methods which appear in representation theory in positive over the fields of positive characteristic work very well for supergroups as well. So, and that's what I'm going to talk about. And let me start with the super Grassmannian. So it has 4 indices because we are talking now about superspaces, and it has 2 dimensions, P and Q, and we look at the manifold of all superspaces of given dimensions inside bigger superspace. The most important, however, for most calculations is what is called superdimension. And the superdimension is the difference of even and odd dimension, bosonic and fermionic dimension. And in most answers, only this superdimension will appear. So super Grassmannians, as a usual Grassmannians, has a lot of structures and properties, and let me just mention some of them. For example, if I look at bosonic part underline supermanifold, it's just a direct product of 2 usual Grassmannians. And it's compact. So here, the dimension of super Grassmannian is given by this formula. We can, of course, take the subspace, the complementary spaces, and we have sort of duality between 2 Grassmannians, like in the usual case. So we have a structure of homogeneous space, meaning that this supergroup, UMN, acts on the super Grassmannian, and this is the stabilizer subgroup. So, and what is more important, maybe, and more special for this, is that in fact, we can realize a super Grassmannian as a coinjoid orbit. So if we look at the Lie algebra of superunitary group, we can think about the orbit of any particular element there. And as in classical case, we have canonical symplectic form. And in fact, the action of the group on super Grassmannian is actually Hamiltonian. So we have Hamiltonian action. So And this Hamiltonian action, Hamiltonians of vector fields are just given by the elements of the Lie algebra. And the next, I would like to talk about volume forms, because in this case, I'm to compute the volume of any super manifold. What I actually have to do, I first have to introduce the volume form, and this is and then take the Bayesian integral. So Bayesian is this thing. It behaves as well as the determinant, so it's multiplicative. And the beauty of the story is that it's multiplicative as well, although now it's a rational function, or not a polynomial on the matrix coefficient. And we can look at something which is called volume form in supermanifold, that basically some tensor field on a supermanifold, which behaves like this when we change coordinates. And so now, if you have a function on Rmn with compact support, you can integrate it with respect to, or you can think about this as a volume form, as function times the canonical volume form. And to compute the integral, what you're doing, you first integrate it over bosonic part, take the usual integral, and in order to its convergence, you need a compact support. And then you look at the highest term with respect to the bosonic. That means that you take all and fermionic variables, and you look at the highest coefficient. So there is something subtlety with taking the Bayesian integral, which was understood a long time ago. Somehow, I think it's still worth to say something about it. But first of all, what we need. So first of all, we need the orientation of the underlying usual manifold. And second, if we want to compute the integral over compact manifold, what you have to do to take the global integral, you need some partition of unity, because the invariance of the Bayesian integral is only for functions with compact support. So here is an example where there is no invariance. If it's a very simple situation when you just take open integral from 0 to 1, and you try to integrate the canonical form, and you just make this simple change of variables, and the integral changes. And that's why what you really have to do, you have to take the partition of unity and write down your function, as a sum of functions with compact support, and then integrate. And that's why the problem of computing such seems an easy problem of computing volume of Supergrassmann is not so easy, because of course you can write down your volume form in local coordinates, but it's not compactly supported. And if you change this coordinate, the result changes, because that's not really what you have to do. Now let me also explain how I get the invariant volume form. Actually, the truth is that whenever I have a symplectic manifold, and super manifold as well, with Hamiltonian action, when you always have a canonical volume form, it could be written in this, so symplectic form and super manifold has Darboux coordinates can be written like this, and then this is the corresponding volume form, which I denote by little omega. So from this and the fact that Grassmannian is a symplectic supermanifold, we know that it has invariant form with respect to the group UMN, unitary supergroup. And of course, it's not unique. It's up to rescaling. At the moment, I'm mostly interested in the case when the volume is 0 or not. Okay, so here is, I'm just repeating myself, saying that it's all very often 0. So here is this conjecture. It is a nice conjecture that the volume of super-Grassmannian can be expressed in terms of Barnes function, G Barnes function. This is certain generalization. It's a function, meromorphic function of one variable. And it's a certain generalization of gamma function. And here I wrote values of it. So it's just, you see, it is actually, if I look at the integer values of this Barnes function, it is 0 for negative n. And it's just double factorial for positive, more or less. And here is a conjecture of Ted Voronov that the volume of the Grassmannian up to some coefficient here is the following ratio of Barnes functions. So I didn't manage yet to understand how normalization is working, and I'm not completely sure I have a proof of his conjecture at the moment, but certainly what I do know that I can compute where this volume is not 0 and when this volume is 0, and this computation is consistent with this conjecture. Okay, so I should mention that most of this work is joined with Alex Sherman. And so here is the answer. The super-Grassmannian has a non-zero volume if and only if the following is true. So if you look what was done in the previous slide here, so there is these numbers A and B, and they are more or less a super dimension. So, and the point is, if I look at these 3 super dimensions of a subspace, super dimension of a complementary space, and the super dimension of the whole big unpaired space, they must have the same sign, or they must be all non-negative or non-positive, and then the volume is non-zero.
I'm sorry, Vera, can I ask a physicist question first?
Yes, I'm not sure I can answer, but please, yes.
No, just about intuition. So you say that many times compact supermanifolds have 0 volume. So why is that?
You integrate over fermionic.
Maybe one of the reasons is that
But I mean, it's supposed to be non-degenerate.
Yeah, sometimes in the Berezinian, when you expand the Berezinian, okay, you find out that it doesn't depend.
Yeah, you expand the Berezinian very often. You know, actually, the work of Ted Voronov was jumping from his correspondence with Witten, who had a conjecture that any symplectic supermanifold is going to be 0 volume form, because what you're looking at is it's a very high coefficient, psi1, psi-n, the top coefficient. And by some strange reason, it's very often is 0. But probably there is another thing, you know, it is related to supertrace in a way. So when you look at a unitary group, it has like, you look at an underline. My group, it's a product of two groups, UM and UN. Somehow they cancel. But I'm not sure I have a very good explanation why this is so mathematically, but I'm not sure I can answer about intuition.
That is this kind of cancellation you expect when the dimensions are the same, maybe. I mean, when n is equal to m.
That's the amazing thing. No, it's almost always so. I mean, it's not such a difficult argument to check. Maybe because the group is splitting and you can write down the global form and it doesn't have the highest coefficient at all. I think that's one of the reasons here. And I will going to explain what is the reason, the other reason, because I'm going to talk about Schwarz-Zaboronsky formula, and it also gives you an explanation. But also think about it. We know that representation theory of unitary supergroup is not completely reducible. It's very easy to see. However, if we do have volume form, which gives you non-zero volume, you must have this splitting, this complete reducibility thing, just because you define like in the classical case. So that's maybe another explanation why. Okay, so Gwilliam said that the main tool for this computation, which we made, is this localization formula due to Schwarz and Zaboronsky, and their recent preprint, relatively recent paper in archive by person who calls Zakarevich. I think he's Dan Fried, student who wrote this paper, who studied this in more detail. And what is this formula? This is a formula, this is stationary phase integration. It's localization formula. Here what it is. You start with a supermanifold with a fixed volume form and you look at the odd vector field on this supermanifold. And look at the zero locus. If you have a function, we can define the Hessian function. And we have defined at every singular point of my vector field, I can define this coefficient. Let us assume this formula has a generalization for any, where if this set of zeros of vector fields is any supermanifold, but we are interested in the case when our field has just isolated singular points, just finitely many 0 points on your supermanifold. So here what we get, if I have a quadratic form and a volume form in a superspace, I can build something out of them. So this is signature of, so if I have a quadratic form in the superspace, its even part is the usual quadratic form which has signature, and its odd part is actually a symplectic form and it has a Pfaffian. And that's what I'm doing here. I divide. You can say that this is a specifically taken square root of Berezinian of the form. Okay. So here's the theorem. Suppose I have oriented compact supermanifold with given volume form, and assume I have a vector field, which is an odd vector field, such that when I take a supercommutator with itself, it acts compactly on my manifold. Suppose also the volume form is preserved by this action, and the set of zeros, so the zeros are isolated points, so even in the odd direction, I don't have any zeros. Okay, find a certain odd function f on the manifold such that x squared of f is 0. The set of singular points of xf coincides with 0 points of the vector field. And then the integral of our volume form can be written as a sum of contribution and fixed points of the action of my vector field. So if you look at it, so one important thing is that if such a vector field doesn't have singular points, and automatically the volume is 0, right? So think about now returning to the question of the unitary group. Take some vector field coming from the action of the unitary group, and the action, it doesn't have 0 points, right? It doesn't have zeros, doesn't have singular points, because the action is transitive, the group. And so it follows from Schwarzer-Baronsky formula that there's no contributions here, and the integral is 0. So the situation I'm talking about, I must have the supermanifold, even a 0 superdimension, even dimension is equal to odd dimension. So actually the chance that the volume is not 0 happens exactly in this situation. Yeah, so here is a kind of classical example which tricked this, inspired this work of Schwarzer-Baronsky. And this is for a very famous formula, which is a Duster-Matt-Hickman formula. So whenever I have usual symplectic manifold, not super manifold, actually, whenever I have a usual manifold, there is super manifold related to it, which is obtained. So this is M, is the superization of the tangent bundle. In this case, the usual forms, differential forms, and our manifolds that are functions on the supermanifold M. And if M0 was symplectic, I do have, I can get a vector field like this. So I start with some compact vector field on M0, the usual vector field, and I lift it to a vector field on M, a supermanifold, by taking the de Rham differential plus contraction. And satisfies this condition here. And I take the Hamiltonian. I take this function here. I think it should be omega 0 here. And I try to compute this integral. And the result which we are going to have in this case is exactly coinciding with famous Duster-Matt-Hickman formula. So it is just a particular case. So how I'm computing this? How I'm computing this volume? So again, the point is I have a Hamiltonian action. I can choose a specific vector field which I want, and I look, it is at singular point. If I'm liking their isolated single points, I can compute the volume. I compute contributions and compute the volume. So if the condition of the theorem is not true, I'm just looking at some specific element of the Lie algebra here, which is an odd vector field. And I can just find a very particular vector field for which I do not have contribution, exactly as I explained for the group itself. So it is 0. Then there are two particular cases. And then the volume is not 0. So look at what are these cases. Here the super dimension of subspace and the super dimension of the whole space are 0. And here the super dimension of the complementary space is poorly odd or poorly even. It actually doesn't matter. So I'm starting with certain element, very particular element, generic element. Of my group, odd group, and gives me then it gives me the vector field. So I should explain something here which I forgot to write down, that K. So I think about my manifold as G mod K in this case. So this is UM N quotient U. Okay. So there is a very simple way to compute. I start with a vector field lying in the stabilizer of some particular point, and I can check when it has finitely many zeros, and it's very easy to check. But if the point is picked up generically, if the vector field is picked up generically, then it has isolated singular points. And moreover, in one case, namely this case, it's just one point, one isolated point. It's easy to see that the contribution there is not 0. So the volume is not 0. These cases is much more involved because you really have to work out and see, but it's not difficult to see again, because the action is Hamiltonian, but contribution and the space is homogeneous, the contributions are all the same in Schwarz-Zarinsky formula, and therefore the volume is not 0. So this was kind of surprising because it was somehow unclear if this volume was 0 or not, and Ted was actually assumed conjectures that it is not 0, and it is not, although some people were originally thought that it is 0. Okay, so here is the last step, and it's not so difficult to explain how I go to the more general case, because so you see, I can use this idea of the double bundle. Whenever I have a bundle, I can take partial flag variety F as a bundle over one Grassmannian and with fiber another Grassmannian. And if volume of the base and the volume of a fiber are not 0, then we can multiply them together. And what is written here is very particular computations which we need to do to go to from the previous case, cases described here, from these two cases to the more general case. So we also can make this calculation for so-called Q Grassmannian, and I think the Q, the supergroup Q plays a very important role in some applications in physics. This is a group of such matrices of size NN, where A is even in this word. And we can talk about, and that means that we have a super space of super dimension 0 for the fixed order isomorphism, the isomorphism which switches a parity. And we look only of subspaces inside this space which are invariant under this odd structure. And I think that it has a compact version as well. So we can think about, so what I defined before was a complex group, but you can always go to the real part of it as a compact group. And the answer is kind of interesting when the volume of a super Grassmannian Q Grassmannian is not zero, when at least one of these two numbers is even. And this kind of result. It's acting by the same method using Schwarz-Zaborensky formula. But there are some drawback. It's kind of interesting that this Q Grassmannian is not coadjoint orbit, but it is in a joint orbit, and that means because there is no duality between a joint and coadjoint representation in this case, what you get is an odd symplectic manifold. So actually on this manifold, you have this Batalyan-Volkovsky formalism. So it's probably very interesting Grassmannians. Okay, so this is all I wanted to say about volumes, I think. Yeah, and now I would like to talk about application to representation theory. So this is in a framework of algebraic supergroups. So we're now looking at algebraic groups over complex numbers like GLMN over C or OSP over C. And about thinking about representation theory, there are three ways to think about it. I just would like to mention it. So there is, we can define the affine algebraic supergroup as a certain factor from the category of commutative rings, supercommutative rings to groups. You can think about it also as a Harris-Chandra pair. Namely, you have the usual group here, and you have Lie superalgebra here. And of course, there is a third way to think about it. Just think about commutative, finitely generated superalgebras, Hopf algebras of functions on the supergroup. This is supercommutative ring. So what we would like to study in this case is a category of finite dimensional representations of a supergroup. So let me remind that from the theory usual algebraic group, there are so-called reductive groups, and all simple groups are reductive, like SLN, etc. And they have this semi-simplicity of complete reducibility property. So every object in the category of representation is a direct sum of simple or irreducible objects. And in a super case, this is quite rare. In fact, we have such complete reducibility only if our supergroup is a direct product of several copies of orthosymplectic group 1 to n and some usual reductive algebraic group without odd variables at all. So for example, LMN, as soon as Mn is not zero, is never reductive. And so this actually what I come up with. I was suggesting to consider groups which are called quasi-reductive. And that just means that this group here is reductive. Its underlying group is a reductive group. So if I look at look at the category of finite dimensional representations of quasi-reductive group. It has many nice properties. I don't want maybe to talk in detail, but one of the things which is happening in this situation, I know G0, I induce from G0 to G. And since I induce only in the direction of fermionic variables, I get again something finite dimensional. So it actually means that what we get here is so-called Frobenius category. What is so good about this Frobenius category? So there are some examples of Frobenius categories, like just finite groups in positive characteristic, instead of finite groups over C, where there is a complete reducibility. Finite groups in positive characteristic, because there is a very developed and not so easy theory of representations, and it seems like a lot of properties are the same. It's also kind of important that if we have a pair of quasi-reductive supergroups, one line inside another, then the coset space G mod K is affine. And therefore, the induction factor is exact. For example, if I would like to study cohomology G mod B of a line bundle, I get something which is not completely reducible in general. But because G mod B is a projective supermanifold. But here, the supermanifolds which appear are affine, and we can study induction and restriction factor between them. And so here is my main definition and the motivation why I started to computing this volume. So suppose I start with such pair, K in G, quasi-reductive, like gel AB in GLMN. And I induce from the trivial representation. What does it mean? That actually I'm looking at the functions on this coset space. So there, of course, are constant functions. And the question is, can I split these constant functions as a direct summand? In other words, if Vera is the map from these are functions on G mod K, to C, which is an invariant splitting. So it is equivariant with respect to the action of a supergroup. So, and we are in very good situation that we do have such equivariant splitting. But if you think a moment what it is, it means that I actually should start with, so what such the thing is, it's actually clearly should be an integration over G mod K and should be invariant. So it is clear that the question is, so we call the group detecting if we have such a splitting, and it seems like it has a lot of application to find such splitting subgroups. So there are several different ways to define the detecting subgroup, and the first one, as I defined on the previous slide, it also says that if I induce from any G module, and I get a bigger G module, M splits as a direct summand for any representation of G. And if I look at the X, so we always have a restriction map, and we have the corresponding restriction map between X group, and these maps are injective for all I. So here is important examples. So if you look just for a finite group or a ground field of positive characteristic, then one can show that any detecting subgroup. Detecting subgroup is the one which contains a p-zero subgroup. So in a way, I can say that smallest detecting subgroups and supergroups should play the same role as zero subgroup in the finite group theory. So there is a nice projectivity criterion, but I didn't talk much about projective modules. But the point is, whenever I start with the group and the module is projective and I restrict, I always get a projective module in this framework of quasi-reductive group. But the question is, when K is detecting, and only if K is detecting, I can go opposite way. I restrict to subgroup and it is projective, then over G, it is also projective. So there's a transitivity seen. If K is detecting in H and H is detecting in G, then K is detecting in G. So there is one important application to the tensor category methods. So you see the category of representations of supergroup, quasi-reductive supergroup in particular, but in general, algebraic supergroups is rigid monoidal symmetric category. And there is a notion of semi-simplification. If your category is not semi-simple, then you can canonically construct a semi-simple category by quotienting by these negligible morphisms. Negligible morphisms are the maps, linear maps between, G-equivalent linear maps between representations such that if I go back with any other such map, the supertrace is zero. So this more recent result, not very difficult actually, with Ina and Weisenblatt and Alex Sherman, that the detecting subgroup behaves nice with these negligible morphisms. And in particular, in this theory of semi-simplifications, restriction map to negligible subgroup, and to detect a subgroup induces a functor between semi-simplification of categories. Okay, so here I will call an odd element of my Lie superalgebra semi-simple. If I take its square, then it is a semi-simple element. And we have a nice criterion which should ring a bell with the previous geometric construction, that if we start, if the group is detecting, I look at all semi-simple odd elements in the Lie algebra, and I consider the action of G0 here, then every orbit intersects with K1. So K1 is sitting inside G1. So we have here G0 action, and every semi-simple orbit must have a representative on K1. And what we can prove now is the following result, which should clearly remind you super-Grassmannians. And that in the case of GLMN, the product of two GLPQ and GLM minus P and minus Q inside GLMN is detecting only if and only if the Grassmannian has a non-zero volume. And the proof is that basically basically I take the integral of, so the map, the splitting map is just the integral. I'm very lucky here because the Grassmannian is already homogeneous space over the compact group, over compact unitary group. And so therefore, I get this integral here, which gives me a UM equivariant map as desired. In order to have a splitting, I needed, when I integrate my constant function, which is not zero, I don't get a zero, I get something proportional to the volume of the Grassmannian. And so there is the standard unitary trick. If something is equivariant over unitary group, when it is equivariant over general linear group, this is very easy to see. So that basically is a proof now that this is a splitting. So, and now there is this transitivity thing, right? That if H and K is detecting, K and G is detecting, and H and G is detecting, and therefore I can get, using all this, we can get this result. So there is a notion of a defect of supergroup, which works for any supergroup, but for GLMN, defect is just the minimum of dimensions M and N. And so inside there, I can put several copies of SL1 once, and they are already detecting. Now let me go to this situation, to this analogy of finite groups. So let us take back. So there is such a thing which is called green correspondence. What I present here is just a small part of this. There is more general statement. I just don't think I should talk right now here about it. So suppose G is a finite group, and we work over a ground field of positive characteristic. And suppose H be a Silo subgroup, P Silo subgroup. So it's a group of order P to the N. P to the N is the maximum power of P, which divides the order of the group. And let us consider the normalizer of this group. So in this situation, we do not have complete reducibility, but we have indecomposable pieces, right? Every module uniquely up to isomorphism, every representation is a direct sum of indecomposable pieces. And so there is a very nice correspondence between indecomposable representations of G of non-zero dimension and indecomposable representation of K of non-zero dimension. So what does it mean that dimension is zero? It is as a dimension in the field. That means that P divides the usual dimension of our representation. So in this example now, we understand what is a Silo subgroup. It is this thing. And we can take the normalizer. And it is nice because the normalizer is basically semi-direct product of symmetric group and this subgroup here. And this is just a diagonal thing. For example, if I take GL22, then I have here GL11 as a block and another GL11 as a block. And then if I take, I look at the normalizer, what I can do, I can switch them, and that gives me S2 in this case. Okay, so this is the group we are talking about. And then this is a very recent result, that whenever I have an indecomposable representation over GLN of non-zero super dimension, when exactly one, restricted to K, when the one in the composable K components, we have exactly one with non-zero super dimension. And in this way, again, absolutely analogously to this green correspondence, we have bijection between indecomposable representation of GL and N and indecomposable representations of this group GL11N semi-direct product with Sn. So if you want, you can say that SL11 N is the Silus analog of Silus subgroup for GL and N. Well, so we have some other applications, but maybe actually we have now conjecturally more general version of this green correspondence. So there are some questions which I would like to tell in the end. So first of all, so we computed, we understood the volume of super Grassmannians related to general linear group or unitary group and to this group Q, but there is also the groups OSP, which are very interested. I think people are interested in the representation theory of these groups, and we have super Grassmannians for them, such as Lagrangian Grassmannians. And the question is, can we figure out the volumes in this case? And there is really some obstacle to it, which is kind of interesting. So whenever I have a complex group, it has a real form, what we call, such a group which if we complexify it back, we get the original group. In the classical theory, every simple Lie group has a unique compact form as a salt result of Cartan. And in super cases, it's not so. For example, this group here doesn't have a real compact form. And therefore, it is not completely clear even how to define in the right way what is the volume, which form we should consider, okay? But somehow there is a feeling, there is a way to go around it. There is some theory of, more general theory of real forms where we can try to define the volume, form, and Bayesian integral, but this is not done yet. So this is more algebra geometric question, which I probably, so as I said, the important thing is to study action of G0 in the odd part of the Lie algebra and study the orbits, and it seems that there is a connection there. Also about these detecting subgroups, in fact, we know them for the case there is a notion of defect. So the small dimensions like OSP, for example, 3 to n, or with exceptional supergroups, we can prove that the SL11 sitting inside is a detecting subgroup. And actually every detecting subgroup must contain a SL11. So in general, this is an open question as well. Okay. Sorry, that's all I wanted to say. Thank you.
Thank you so much for a nice talk. Do we have any questions?
Thanks. Can you say something about this more general theory of real forms? Is this like the so-called graded real forms?
Okay. So yes, it seems to be very. So it actually comes from maybe point of view of tensor categories. If you look at super vector spaces, say over complex numbers, you can take you can think about the category of a real category, real form of this category. This is a developed theory in There's this paper of Ettinghoff and Gilaki where they start look at the real forms of tensor categories. And the point is that you can consider what I call H vector. And this is like, so of course I can just look at super vector spaces, Z2 graded vector spaces over R. But what I can do, I call it H vector spaces. And they're kind of interesting. They have V0. So I think about vector spaces like this, V0 plus V1. And I assume that the 0 is real. Vector space. And V1 is quaternionic, actually. So there is a quaternionic structure on V1. And in a way, you can define the tensor product of such representation and such vector spaces, and you get a structure. And then you can look, in this framework, you can look at the corresponding Lie superalgebra. And you can take, so you take a complex algebra. And in order to classify all real forms in the usual sense, you look at involutions, which are ciscilinear involutions, which commute with multiplication by complex number with complex conjugation. And you look at these, just the fixed points of this involution. So sigma squared is identity. And so this is the usual form. But you can also take second form, where you assume that sigma squared is not an involution, but the gradient operator, delta. Delta is identity on even part of superalgebra and -1 on the odd part. And quite remarkably, for most of this classical list of the superalgebras and the even exceptional one, we do not have compact forms for this usual type. But we don't always have a compact form of this type. And all this Cartan theory works very well for this setting. I can also, there was a recent paper by Fioresi and Gavarini where they developed even what are supermanifolds in this case. So they are nice. They are actually coming from vector bundles on the usual real manifolds with quaternionic structures. But what I don't understand is the theory of volume forms and the integrals and all this. Sorry, it took so long to answer this question. But that's what I mean. I think it's a very interesting subject.
I agree.
I actually have seen physicist papers where they consider such things for OSP 1 to n. They consider analogous of spheres in these settings. Okay, that's it.
Other questions?
Can I ask you something? I'm not sure I got it right. Like you say, did you say that the Supergrassmannian is a symplectic supermanifold?
As a real manifold, I look at the complex, it's actually even Keller. Yes, it is symplectic supermanifold, yes.
Excuse me, what is your definition of symplectic supermanifolds? Like there's a non-degenerate, globally defined two-form?
Exactly, two-form, closed form.
Yeah, exactly. So that's interesting.
But you see, there is this thing, whenever you have coin joint orbit, then there is this Kirillov constant Soulier form, which is symplectic. And in super case, it works perfectly well as well.
Right. Right. No, because I mean, I don't know. I'm sort of surprised because, well, I don't know. For example, the super-Grassmannian, a super-Grassmannian is in general non-projected and non-split, so it has a very complicated, form of the transition function, right? And also, I mean, if we look at the simplest possible complex Grassmannian, they reduce the spaces of P1 cross P1. So.
Oh, okay. I'm sorry. I look at it as a real Grassmannian now. I mean, as a real manifold. It has dimension. P1 certainly has symplectic form, right?
Yeah, exactly. That's why I was like, surprised when.
Yeah, the point is, this is a Keller structure actually. On P1, you have both Riemann metric and symplectic form, and they are related, as they should be related. So, and the point is, yes, you can extend it to the super Grassmannian. Yeah.
Yeah. Okay. Because so I mean, over the complex super Grassmannian, so there is no, in general. Well, I would say there is no a globally defined closed two-form.
Analytic two-form over complex, yeah, there is no. You're right. Okay. But I'm talking about I think like P1, I think about it as a really Riemann sphere, as a two-dimensional real manifold. Because you see, when I take the integral, I think about this complex Grassmannian as a real manifold of double dimension.
All right, thank you. I need to think about it.
Thanks. Yeah.
Thank you very much.
Any more questions? Go ahead.
I have a question to organizers. Since most of the conference is during the night, can I watch the talks?
So it's been recorded.
Yeah.
In fact, it's streamed to YouTube, and the recordings are in YouTube. So if you look at the conference website, you should be able to find it.
But we apologize that the sound is not always perfect on YouTube. So yeah, there might be a couple of recordings completely without sound. We apologize to learning.
Okay.
At least most of them, I think, worked out.
Yeah, most of them. Yeah.
One more question, John?
So I have another question, which is, do you know anything about these semi-simple elements as algebraic varieties? Like, are there any?
Yeah, in some cases, certainly, yes. It's exactly one of the open questions I put. It's more or less about it. You can think about this as geometric quotient, GIT quotient, and in many cases it's a nice variety. So if you take the quotient of G1 by the action, so semi-simple are like stable in this GIT thing. In many cases, it's a nice variety. Like sometimes it's AN, where N is this defect. So wait, maybe yeah. So for a GLMN, for example, if M is less than N, you have something like CM. But then there are some interesting things because some orbit, so the GIT quotient, it doesn't catch every orbit. So for example, there is this homological vector fields such as the squares are zero elements. And they are pretty important in the whole story because you can take homology with respect to them. And then all lie in so-called self-commuting cone. But it has finitely many orbits, it's a spherical variety. But in general, I mean, if you just look at all semi-simple objects, this is something not very nice. But if you quotient by the action of the group, it's something nice.
Great, thanks.
Any other last questions? So if not, let's thank Vera for joining us from so far away for such a beautiful talk. That's it for the day. We'll start again at 9:30 in the morning.
And tomorrow you don't have.
Tomorrow it ends early.
I guess you figured out that you could just check the sketches on the yellow page.